When implementing Azure Virtual Networks, we're essentially creating a secure, isolated foundation for our cloud infrastructure. Let me walk you through the critical aspects of this implementation process and why each component matters for your organization's success. Let's start with network isolation, which forms the cornerstone of any virtual network implementation. When you create an Azure Virtual Network, you're allocating a specific CIDR block. Think of it as your own private section of the cloud. This isn't just about having your own IP address space, it's about creating a controlled environment where you can ensure security, compliance, and optimal performance for your applications. The beauty of Azure's approach lies in its flexibility. Your virtual network can be as simple or as complex as your needs dictate. For smaller deployments, you might opt for a straightforward setup with a single subnet. However, as your needs grow, you can implement more sophisticated configurations with multiple subnets, each serving different purposes. For instance, you might have separate subnets for your web servers, application servers, and databases, creating clear boundaries between different tiers of your application. DNS configuration in Azure. Virtual networks deserve special attention. Azure provides built-in name resolution services, but you're not limited to using them. You can implement your own DNS servers, which is particularly valuable when you need to maintain consistency with your on-premises naming conventions, or when you require specific DNS functionality. This flexibility ensures that your cloud resources can seamlessly integrate with existing systems while maintaining proper name resolution across your entire infrastructure. Cross-premises connectivity is where many organizations find tremendous value. Azure Virtual Networks support multiple options for connecting to your on-premises network. You might choose a site-to-site VPN for a cost-effective solution, or ExpressRoute for dedicated high-performance connectivity. The choice depends on your specific requirements for bandwidth, latency, and security. What's crucial is understanding that these connections aren't just pipes. They're secure tunnels that extend your network into the cloud while maintaining all your security policies and access controls. Speaking of security, the implementation of network security groups, NSGs, provides granular control over network traffic. Think of NSGs as your virtual firewall rules. They allow you to define precisely what traffic is allowed or denied, down to the individual port and protocol level. This granular control is essential for maintaining a strong security posture while ensuring your applications can communicate effectively. Routing in Azure Virtual Networks deserves careful consideration during implementation. Azure's system routes handle basic connectivity, but you can override these with custom routes when needed. This capability is particularly valuable when you need to direct traffic through security appliances or when implementing hub-and-spoke network architectures. The key is to plan your routing strategy carefully to ensure optimal traffic flow while maintaining security requirements. Peering is another powerful feature to consider in your implementation. Virtual network. Peering allows you to connect different virtual networks, even across regions, creating a seamless network fabric. This capability is invaluable when you're dealing with complex applications that span multiple regions, or when you need to maintain separation between different environments while still allowing controlled communication between them. One aspect that often gets overlooked during implementation is monitoring and diagnostics. Azure provides robust tools for monitoring network traffic, analyzing security rules, and troubleshooting connectivity issues. Implementing proper monitoring from the start will save countless hours of troubleshooting later and help you maintain optimal network performance. Load balancing is another critical component to consider. Azure offers both external and internal load balancers, allowing you to distribute traffic effectively across your resources. During implementation, you'll need to decide where load balancers fit into your architecture and how they'll help ensure high availability and scalability for your applications. As you implement these various components, remember that documentation is crucial. Maintain clear records of your network design decisions, IP address allocations, and security rules. This documentation will prove invaluable as your network grows, and when you need to troubleshoot issues or make changes in the future. Lastly, consider your scalability needs during implementation. Azure Virtual Networks can grow with your organization, but planning for this growth from the start will make future expansions much smoother. This might mean allocating larger address spaces than you currently need, or designing your subnet structure to accommodate future services. Remember, successful implementation isn't just about getting the technical details right. It's about creating a network infrastructure that supports your business objectives while maintaining security, performance, and manageability. Take time to understand your requirements thoroughly and plan accordingly. The effort you put into proper planning and implementation will pay dividends in the long run through improved reliability, security, and ease of management. Let's explore the versatile ways organizations can leverage Azure Virtual Networks to meet their specific needs. Understanding these scenarios is crucial for making informed decisions about your network architecture. First, let's discuss the private cloud-only virtual network scenario. This approach is particularly interesting for organizations starting fresh or developing new applications without legacy infrastructure dependencies. In this configuration, your virtual network exists purely within Azure, creating a dedicated, isolated environment for your cloud resources. Think of it as your own private data center in the cloud, but without the physical hardware constraints. Within a private cloud-only network, your virtual machines and services can communicate directly with each other in a secure environment. This internal communication is automatically encrypted and isolated from other customers' networks in Azure. For internet-facing services, you maintain complete control through endpoint configurations. This means you can precisely specify which services are accessible from the internet and under what conditions, maintaining a strong security posture while ensuring necessary accessibility. Moving on to our second scenario, extending your data center using virtual networks. This is where Azure's networking capabilities really shine, offering robust site-to-site VPN capabilities. Using industry-standard IPsec protocols, you create a secure tunnel between your on-premises VPN gateway and Azure. This connection effectively makes your Azure resources appear as if they're just another part of your local network. The beauty of this approach lies in its seamless integration. Your on-premises users won't need to learn new ways to access resources. Everything appears as part of the same network. This transparency is particularly valuable when you're gradually migrating workloads to the cloud or need to maintain hybrid operations. The site-to-site VPN ensures that data traveling between your data center and Azure remains encrypted and secure, meeting compliance requirements and maintaining data integrity. The third scenario focuses on hybrid cloud implementations, which represent perhaps the most flexible and powerful use of Azure Virtual Networks. This scenario goes beyond simple data center extension, enabling you to create sophisticated solutions that bridge cloud and on-premises resources in creative ways. You can connect cloud applications to various on-premises systems, including mainframes, Unix systems, and specialized hardware that can't be easily migrated to the cloud. Think about the possibilities this creates. You could keep your sensitive database on-premises while running your application servers in Azure, or you might maintain legacy systems locally while developing new features in the cloud. The hybrid approach allows you to leverage the best of both worlds, the security and control of on-premises infrastructure, combined with the scalability and innovation potential of cloud computing. A key strength across all these scenarios is Azure's support for multiple networking protocols and connection types. Whether you need basic HTTPS connectivity, dedicated fiber connections through ExpressRoute, or standard IPsec VPNs, Azure Virtual Networks can accommodate your requirements. This flexibility ensures that you can implement the exact type of connectivity that your applications and compliance requirements demand. Security is a fundamental consideration in each scenario. Azure provides comprehensive security features, including network security groups, application security groups, and DDoS protection. These tools allow you to implement defense-in-depth strategies, ensuring your resources are protected regardless of which scenario you choose to implement. When selecting between these scenarios, consider your organization's current needs and future growth plans. Ask yourself questions like, do you need to maintain any on-premises systems? What are your compliance requirements? How might your networking needs evolve over the next few years? The answers to these questions will guide you toward the most appropriate scenario for your situation. Remember, these scenarios aren't mutually exclusive. Many organizations implement multiple scenarios across different parts of their infrastructure. You might start with a private cloud-only network for development and testing, then implement a site-to-site VPN for production workloads, and finally add hybrid cloud capabilities as your needs evolve. The key to success is careful planning and a clear understanding of your requirements. Take time to assess your current infrastructure, future needs, and security requirements. Consider factors like latency requirements, data sovereignty rules, and backup strategies. This thorough evaluation will help you choose and implement the most appropriate virtual network scenario for your organization. Let's dive into the critical aspects of subnet implementation in Azure Virtual Networks. Understanding subnets is fundamental to creating an efficient and secure network architecture that meets your organization's needs. Think of subnets as the neighborhoods within your virtual city, the virtual network. Just as a city is divided into districts for better organization and management, your virtual network can be segmented into subnets to enhance security, optimize performance, and simplify management. Let me walk you through the key considerations and implementation details. First, let's address the fundamental rules of IP addressing in subnets. Every subnet you create must exist within your virtual network's address space, similar to how neighborhoods must exist within city limits. The address range you assign to each subnet must be unique and cannot overlap with other subnets. Imagine the chaos if two neighborhoods tried to use the same street addresses. This segregation is crucial for maintaining order and preventing routing conflicts in your network. A critical aspect that often surprises newcomers to Azure networking is the concept of reserved addresses. In every subnet, Azure automatically reserves 5 IP addresses for internal use. Let's break this down using a practical example. In a subnet with the address range 192.168.1.024, Azure reserves 192.168.1.0. This is your network identifier. 92.168.1.1. This becomes your default gateway. 192.168.1.2 and 192.168.1.3. These are reserved for Azure DNS 192.168.1.255. This serves as your broadcast address. Understanding these reservations is crucial when planning your subnet sizes. Always account for these 5 addresses in your calculations to ensure you have enough IP addresses for your resources. Now let's discuss some practical considerations that can significantly impact your subnet design. First, consider your service requirements. Different Azure services may have specific subnet requirements. For instance, if you're planning to use Azure VPN Gateway, you'll need a dedicated subnet specifically for this service. It's like reserving a special district in your city for government buildings. It serves a specific purpose and must meet particular requirements. Network virtual appliances present another important consideration. By default, Azure handles routing between all subnets in your virtual network. However, You might want to implement more sophisticated routing patterns using network virtual appliances. In such cases, you'll need to place resources in different subnets to control traffic flow effectively. Think of this as setting up specific traffic patterns in your city, where certain types of vehicles must follow designated routes. Service endpoints are another powerful feature to consider in your subnet design. They allow you to limit access to Azure resources like storage accounts or SQL databases to specific subnets. This is similar to creating restricted access zones in a city where only authorized residents can enter certain areas. You might create multiple subnets and enable service endpoints selectively, giving you granular control over resource access. Network security groups, NSGs, play a crucial role in subnet security. You can associate one NSG with each subnet, using it to control inbound and outbound traffic. These are like your neighborhood security checkpoints, determining what traffic can enter or leave the area. The rules you create in your NSGs should align with your security requirements while ensuring necessary communication paths remain open. Private links represent a modern approach to service connectivity. They provide private connectivity to Azure services, eliminating exposure to the public internet. When planning your subnets, consider how private links will fit into your architecture. This is particularly important for services that handle sensitive data or need to meet strict compliance requirements. A practical tip for implementation: always plan your subnet sizes with growth in mind. It's much easier to start with larger subnets than to try to resize them later. Consider your current needs, but also think about future expansion. Remember, you can always create additional subnets within your virtual network's address space, but resizing existing subnets can be challenging. Documentation is crucial when implementing subnets. Maintain clear records of your subnet allocations, including address ranges and their purposes, associated services and requirements, security group rules, routing configurations, service endpoints, and private links. This documentation will prove invaluable as your network grows and when troubleshooting becomes necessary. Remember, subnet design isn't just about dividing IP address spaces, it's about creating a logical, secure, and efficient network structure that supports your business needs. Take time to plan your subnet implementation carefully, considering both current requirements and future growth. A well-planned subnet structure will provide the foundation for a robust and manageable network infrastructure. Let me walk you through the essential process of creating virtual networks in Azure, focusing on the critical decisions and considerations that will impact your network's success. Creating a virtual network in Azure might seem straightforward, but it requires careful planning and understanding of several key concepts. The decisions you make during this initial setup will have long-lasting implications for your cloud infrastructure. Let's start with the most critical aspect: IP address space planning. This is perhaps the most important decision you'll make when creating a virtual network, primarily because it's permanent. Once you've established your network's IP address space, you cannot modify it. This immutability means you need to think carefully about both your current needs and future growth. When selecting your address space, your first consideration should be avoiding conflicts with your organization's existing networks. This is crucial because you might need to connect your cloud network with on-premises resources in the future. For instance, if your on-premises network uses the 10.0.0.0 to 16 range, you'll want to select a different range for your Azure virtual network. A common practice is to maintain a spreadsheet or documentation of all network ranges in use across your organization to prevent conflicts. The address space decision becomes even more critical when you consider hybrid scenarios. While you can initially create a virtual network for cloud-only operations, you might later decide to establish connectivity with your on-premises network. If you haven't planned your address space properly, this could lead to complex networking challenges, or even require you to rebuild your virtual network from scratch. Subnet creation is another fundamental requirement. Every virtual network must have at least one subnet, but you'll likely want to create multiple subnets to segment your resources logically. When planning subnets, remember these key points. Each subnet's address range must fall within your virtual network's address space. Subnet ranges must be unique within the virtual network. No overlap is permitted between subnet ranges. Plan subnet sizes to accommodate future growth. The actual creation process in Azure Portal is straightforward, but requires several key pieces of information. Your Azure subscription. This determines the billing and access control context. A resource group. This logical container helps organize your Azure resources. The virtual network name. Choose something meaningful that reflects the network's purpose. The region. Select an Azure region that makes sense for your resources and users. Speaking of regions, your choice of region can impact several factors: latency to your users or other resources. Available service features. Not all Azure services are available in all regions. Data residency requirements pricing. Costs can vary by region. When creating virtual networks programmatically or through infrastructure as code, you have additional considerations. Using Azure Resource Manager, ARM templates, or Azure CLI commands allows you to automate network creation, making it more repeatable and consistent. This approach is particularly valuable when you need to create multiple virtual networks with similar configurations. Resource limits are another important consideration. Azure sets default limits on networking resources, including number of virtual networks per subscription, number of subnets per virtual network, number of network interfaces, number of network security groups. While these limits can be adjusted by contacting Azure support, it's important to be aware of them during your planning phase. Remember that these limits can change over time, so it's good practice to regularly review the latest Azure networking documentation. A practical tip for implementation: create a naming convention for your virtual networks and subnets before you begin. A good naming convention might include environment, prod, dev, test, region purpose or application, sequential number if needed. For example, Prod Eastus Web 001 documentation is crucial during and after the creation process. Maintain records of IP address ranges, allocated subnet allocations and purposes, any special configurations, connected resources, security requirements, and implementations. This documentation will prove invaluable as your network grows and when troubleshooting becomes necessary. Remember, while you can create virtual networks at any time, including during VM creation, it's better to plan and create your network infrastructure deliberately rather than allowing it to grow organically. This planned approach ensures better organization, security, and manageability of your cloud resources. Let's explore the critical aspects of IP addressing in Azure, a fundamental component that enables communication between your resources both within Azure and with the outside world. IP addressing in Azure is built around two main types of addresses, private and public. Understanding when and how to use each type is crucial for designing an effective network architecture. Let me break this down into practical terms. Let's start with private IP addresses. Think of these as the internal phone extensions within your office. They're used for communication within your organization, but aren't directly accessible from outside. In Azure, private IP addresses enable communication within your virtual network and with your on-premises network when connected. Via VPN or ExpressRoute, private IP addresses are particularly important when you're setting up internal communication between resources in your virtual network, establishing hybrid connectivity with your on-premises network, implementing internal load balancers, configuring private endpoints for Azure services. Public IP addresses, on the other hand, are like your organization's public phone numbers. They enable communication with the outside world. These addresses allow your resources to communicate with the Internet and are essential for hosting public-facing web applications, enabling remote access to virtual machines, configuring public load balancers, connecting to Azure Public Services. Now let's discuss one of the most important decisions you'll make regarding IP addresses: choosing between static and dynamic assignment. This choice has significant implications for your infrastructure's stability and manageability. Static IP addresses, as the name suggests, don't change over time. They're particularly valuable in several specific scenarios. First, consider DNS name resolution. When you have services that other systems need to reliably connect to, a static IP ensures that DNS records remain valid without frequent updates. This is crucial for maintaining stable service availability. Security models that rely on IP addresses also benefit from static IPs. For instance, if you have firewall rules or access control lists that are based on IP addresses, having those addresses remain constant simplifies security management and reduces the risk of security gaps during IP changes. SSL/TLS certificates often need to be linked to specific IP addresses. Using static IPs here prevents the need to reissue certificates when addresses change, saving both time and money. This is particularly important for production workloads, where certificate management is critical. Firewall rules are another key consideration. When you're configuring security rules that allow or deny traffic based on IP ranges, static IPs ensure these rules remain effective without constant updates. This is especially important in regulated environments where security compliance is paramount. For infrastructure roles like domain controllers and DNS servers, static IP addresses are practically mandatory. These core services need to be consistently reachable by other resources in your network. Imagine the chaos if your domain controller's IP address changed unexpectedly. However, dynamic IP addressing also has its place. It's generally suitable for development and testing environments, stateless applications, resources that don't require consistent addressing, scenarios where automated IP management is preferred. When implementing your IP addressing strategy, consider these practical tips. Document your IP allocation scheme carefully. Track which addresses are static versus dynamic. Note the purpose of each static IP. Maintain records of when and why assignments were made. Use subnet segregation effectively. Consider separating resources with static IPs from those with dynamic IPs. This separation can simplify management and documentation plan for growth. Reserve ranges for future static IP assignments. Ensure your address spaces can accommodate expansion. Consider cost implications. Public static IP addresses incur additional charges. Plan your public IP usage efficiently. Implement proper monitoring. Track IP address utilization. Monitor for unauthorized IP assignments. Set up alerts for critical static IP resources. Remember, your IP addressing strategy should align with your broader network architecture goals. Whether you're building a simple development environment or a complex production infrastructure, thoughtful IP address planning will contribute significantly to your success. Let me guide you through the process of creating public IP addresses in Azure, focusing on the crucial decisions and configurations that will impact your resource accessibility and management. Creating a public IP address in Azure requires careful consideration of several key parameters. Let's break down each component to understand its significance and impact on your infrastructure. First, let's discuss the IP version selection. Azure offers three options. IPv4, the traditional addressing scheme, widely supported and commonly used. IPv6, the newer standard, offering vastly more addresses and improved features. Dual stack, implementing both IPv4 and IPv6 simultaneously. Your choice of IP version should align with your application requirements and client connectivity needs. The dual stack option provides the most flexibility, allowing you to support both protocols simultaneously. Next, let's examine the SKU options. Azure offers two SKUs for public IP addresses. Basic SKU, the entry-level option suitable for many standard scenarios. Standard SKU offers enhanced features and is required for certain Azure services. The SKU selection is particularly important because it must match the SKU of the associated Azure load balancer. This alignment ensures proper functionality and feature compatibility. Standard SKU addresses also provide enhanced security features, as they are closed to inbound traffic by default, unless explicitly allowed by a network security group. The assignment method is another critical decision point. You have two options: dynamic assignment. The address is allocated when the associated resource is started. The IP address can change if the resource is deallocated and restarted. Remain stable during OS-level reboots or stops. Released when the resource is deallocated. Ideal for development environments or temporary resources. More cost-effective for intermittent use static assignment. The address is allocated immediately upon creation. Remains consistent until the resource is deleted. Provides stability for DNS records and security rules. Important for production workloads requiring consistent addressing. Essential for SSL/TLS certificates bound to IP addresses. Required for certain compliance scenarios. There's an important caveat regarding IPv6 addresses. If you're using the basic SKU with IPv6, you must use dynamic assignment. This limitation doesn't apply to standard SKU addresses, which are always static for both IPv4 and IPv6. When implementing public IP addresses, consider these practical tips. Naming convention. Use a consistent naming scheme that reflects the environment, prod dev test, the associated resource, the IP version. Example: pip-prod web ZORY1 IPv4 resource organization. Group-related public IPs in the same resource group. Consider regional distribution for global applications. Maintain clear documentation of IP assignments, cost management. Monitor unused static public IPs. Consider dynamic allocation for non-critical resources. Review regional pricing differences. Security considerations. Always implement appropriate network security groups. Monitor and log public IP access. Regular security audits of exposed services, operational management. Set up monitoring for public IP availability. Configure alerts for unexpected changes. Maintain an inventory of public IP resources. Remember to consider future needs when creating public IPs. While you can change some parameters after creation, others are fixed. For instance, you can't change the SKU after creation. IP version changes might require recreation of the resource. Assignment method changes might be restricted when the IP is in use. A note on quota limits. Azure enforces limits on the number of public IP addresses per subscription and region. Monitor your usage against these limits and request increases well in advance of your needs. Let me walk you through the intricate details of associating public IP addresses with Azure resources, focusing on the critical decisions and considerations that will impact your infrastructure's functionality and security. Public IP addresses in Azure serve as the gateway for your resources to communicate with the Internet. Understanding how to properly associate these addresses with different resources is crucial for building reliable and secure cloud solutions. Let's start by examining the four main resource types that can be associated with public IP addresses. Virtual Machine Network Interfaces, NICs. Both dynamic and static IP addresses are fully supported. Direct association with the NIC provides consistent Internet connectivity, particularly useful for standalone servers requiring direct Internet access. Common in scenarios like web servers, remote access servers, or bastion hosts. Internet-facing load balancers. Supports both dynamic and static IP assignments. Associates with the front-end configuration, essential for distributing incoming Internet traffic. Critical for high availability scenarios and scalable applications. VPN gateways. Accommodates both dynamic and static IPs. Static IP support depends on the gateway SKU, Critical for establishing stable site-to-site VPN connections. Requires careful planning for hybrid connectivity scenarios. Application gateways. Supports both IP assignment types. Static IP availability varies by SKU. Essential for web application delivery and protection. Often used in conjunction with Web Application Firewall, WAF. Now let's dive into the SKU considerations, as they significantly impact your public IP implementation. Basic SKU characteristics. Offers flexibility with both static and dynamic IP assignment. Open to inbound traffic by default. No built-in zone redundancy. Cost-effective for simpler scenarios. Suitable for development and testing environments, compatible with a wider range of resource types. Standard SKU features. Restricted to static IP assignment only. Closed to inbound traffic by default for enhanced security. Zone redundant by default for higher availability. Limited to specific resource types, NICs and standard load balancers. Higher cost but with additional features. Recommended for production workloads. When implementing public IP associations, consider these practical guidelines. Security considerations. Standard SKU's default closed stance provides better security. Always implement appropriate NSG rules regardless of SKU regular security audits of exposed endpoints. Monitor and log access patterns availability. Planning zone redundancy requirements should influence SKU selection. Consider regional failover scenarios. Plan for maintenance windows. Implement health monitoring. Cost management. Track unused public IP allocations. Consider basic SKU for non-critical workloads. Monitor bandwidth. Usage review reservation options. For long-term use, operational considerations. Document all public IP associations. Implement proper naming conventions. Regular validation of security rules. Maintain an IP inventory. Implementation best practices. For virtual machines, consider using load balancers instead of direct public IPs. Implement jump boxes for remote access. Use NSGs to restrict access. Monitor for unauthorized access attempts. For load balancers, plan for proper back-end pool configuration. Implement health probes. Consider cross-region load balancing. Document load distribution rules. For VPN gateways, plan for redundancy where needed. Document connection. Configurations. Monitor connection health. Plan for scaling requirements for application gateways. Implement WAF policies. Plan SSL certificate management. Configure proper routing rules. Monitor application health. Remember these key points. SKU selection is permanent and cannot be changed after creation. Zone redundancy requirements should be considered. Early security stance differs significantly between SKUs. Resource compatibility varies by SKU. Let me walk you through the intricacies of private IP address allocation in Azure, focusing on how to effectively assign and manage these crucial network resources. Private IP addresses serve as the foundation for internal communication within your Azure virtual network. Understanding the allocation options and their implications is essential for building a robust and manageable network infrastructure. Let's start with the three main resource types that can receive private IP addresses. Virtual Machine Network Interfaces, NICs, support both dynamic and static allocation. Primary interface for VM network communication can have multiple IP configurations, essential for internal application communication, internal load balancers. Front-end configuration requires private IP, supports both allocation methods, critical for internal application distribution, enables high availability for internal services application gateways. Front-end configuration needs private IP, supports both dynamic and static allocation, important for internal web application delivery. Often used in multi-tier architectures. Now, let's examine the two allocation methods in detail. Dynamic allocation, Azure's default assignment method. System automatically selects the next available address. Example: if addresses 10.0.4 through 10.00.9 are taken, Azure assigns 10.00.10. Benefits include simplified management, automatic conflict avoidance, easy scalability, reduced administrative overhead, static allocation. Administrator selects specific address, must be within subnet's address range. Example: in a 10.0.0.0 to 16 subnet, you can assign any address from 10.0 to 10.0.2 phase FAM 2 Advantages include predictable addressing, consistent DNS references, simplified security rules, better audit tracking implementation, best practices, address planning, reserve ranges for static assignments, document allocation schemes, consider future growth, plan for different resource types. 2. Dynamic allocation strategy. Use for general purpose resources. Implement in dev test environments. Consider for scalable workloads. Monitor address utilization. Got static allocation strategy. Use for infrastructure services. Implement for database servers. Apply to domain controllers. Reserve for compliance requirements. Documentation requirements. Track all static assignments. Document allocation ranges. Maintain IP inventory. Record justification for static IPs. Practical implementation tips. For virtual machines, consider workload requirements. Plan for multi-NIC scenarios. Document IP dependencies. Monitor address usage for internal load balancers. Plan for high availability. Consider backend pool ranges. Document health probe configs. Monitor load distribution for application gateways. Plan subnet sizing carefully. Consider multi-site configurations. Document routing rules. Monitor performance metrics. Common scenarios and solutions. Infrastructure services. Use static IPs for domain controllers. Static allocation for DNS servers. Fixed addresses for monitoring systems. Consistent addressing for backup services. Application tiers. Dynamic IPs for web servers. Static IPs for database servers. Mixed approach for middleware. Consistent scheme across environments. DevOps environments. Dynamic allocation for CI/CD resources. Static IPs for critical services. Flexible addressing for test environments. Documented ranges for automation. Remember these key points. Address allocation method can be changed after deployment. Plan subnet ranges to accommodate both methods. Document all static assignments carefully. Monitor address utilization regularly. Let's explore the practical implementation of network security groups in Azure, focusing on 3 key deployment strategies that can significantly enhance your network security posture. Let's start with subnet level protection. When you implement NSGs at the subnet level, you're essentially creating a security boundary around an entire segment of your network. This approach is particularly effective when you have groups of resources that share similar security requirements. For instance, you might have a subnet dedicated to your web servers, another for your application servers, and a third for your database servers. By applying NSGs at the subnet level, you can enforce consistent security policies across all resources within each subnet. Moving on to NIC level security, this represents a more granular approach to network security. When you attach an NSG to a network interface card, you're implementing security rules that apply specifically to that individual virtual machine. This level of control is invaluable when you need to create exceptions or implement specialized security requirements for specific resources. Consider a scenario where most of your application servers follow standard security rules, but one server requires additional ports open for a specialized application. NIC-level NSGs allow you to accommodate these exceptions without compromising the security of other resources. A particularly powerful implementation strategy involves creating a DMZ, or demilitarized zone, using NSGs. In Azure, you can establish a DMZ by configuring a subnet with specific NSG rules that create a security buffer between your internet-facing resources and your internal network. This setup is crucial for organizations that need to expose certain services to the internet while maintaining strict control over access to internal resources. For example, you might place your web servers in a DMZ subnet with NSG rules that allow inbound HTTP/HTTPS traffic, but strictly limit communication with your internal application and database servers. When implementing NSGs, it's important to follow the principle of least privilege. Start by denying all traffic and then selectively allow only the necessary communication paths. Your NSG rules should be specific about source and destination IP addresses, ports, and protocols. Azure helps you manage this by processing NSG rules according to priority, with lower numbers having higher priority. This allows you to create a precise and predictable traffic flow pattern. Remember that NSGs support both inbound and outbound rules. While many focus primarily on inbound rules to protect against external threats, outbound rules are equally important. They help prevent unauthorized data exfiltration and can limit the impact of a compromised resource. For instance, you might want to restrict outbound internet access from your database servers to enhance security. A common challenge in NSG implementation is managing rule complexity. As your environment grows, you might find yourself managing multiple NSGs with numerous rules. To address this, consider implementing a naming convention and documentation strategy for your NSG rules. Each rule should have a clear purpose and be well documented. This becomes particularly important during troubleshooting or when making changes to your security configuration. For those who are new to NSG implementation, I recommend starting with subnet-level NSGs and gradually introducing NIC-level rules as needed. This approach helps maintain simplicity while providing the necessary security controls. As you become more comfortable with NSGs, you can explore more advanced configurations, such as service tags and application security groups, to further enhance your security posture. In terms of monitoring and maintenance, Azure provides robust logging capabilities for NSGs through Network Security Group flow logs. These logs offer valuable insights into your network traffic patterns and can help identify potential security issues or needed rule adjustments. Regular review of these logs should be part of your security maintenance routine. Let's dive into the crucial topic of Network Security Group rules in Azure. These rules form the backbone of your network security strategy, determining exactly how traffic flows through your virtual network infrastructure. First, let's understand the default rule structure that Azure provides. Every NSG comes with pre-configured default rules that you can't remove but can override. For inbound traffic, Azure takes a security-first approach by denying all inbound traffic by default, with two important exceptions. Traffic from within your virtual network and from Azure load balancers is automatically allowed. This default configuration ensures your resources are protected from unauthorized external access right from the start. For outbound traffic, Azure takes a more permissive approach while maintaining security. By default, you can communicate within your virtual network and reach out to internet resources. This setup facilitates normal operations while still giving you the control to restrict specific types of outbound traffic as needed. When it comes to creating your own rules, Azure provides a comprehensive set of parameters that you can configure. Each rule requires a unique name for identification and a priority number that determines its processing order. The lower the priority number, the higher its precedence in the processing sequence. For example, a rule with priority 100 will be processed before a rule with priority 200. The port and protocol settings allow you to specify exactly what type of traffic you're controlling. You can target specific ports like port 80 for HTTP traffic or port 443 for HTTPS, and choose protocols like TCP or UDP. This granular control helps you align your security rules with your application requirements. Source and destination settings in your rules define where traffic can come from and where it can go. You can specify individual IP addresses, IP ranges, service tags like Internet or Azure Load Balancer, or even entire virtual networks. This flexibility allows you to create precise traffic patterns that match your security needs. The action parameter is straightforward but powerful. You either allow or deny the traffic that matches your rule conditions. When combined with proper priority settings, you can create sophisticated traffic management schemes. For instance, you might have a higher priority rule that allows specific trusted traffic, followed by a lower priority rule that denies everything else. A key point to remember is that while you can't delete the default rules, you can effectively override them by creating your own rules with higher priority. This capability allows you to customize your security posture while maintaining the safety net of default rules. For optimal security configuration, I recommend following these best practices. Start with more restrictive rules, deny, and then add permissive rules, allow, as needed. Use clear descriptive names for your rules to make management easier. Document your rule configurations, especially for complex setups. Regularly review and audit your rules to ensure they align with your current security requirements. When troubleshooting connectivity issues, always remember to check both inbound and outbound rules, as communication often requires both to be properly configured. The Effective Security Rules view in the Azure portal can be particularly helpful in understanding how your rules are being applied. Let's explore how Azure evaluates and applies network security group rules, a crucial concept for understanding your network security posture. Let's break down the complex process of rule evaluation into clear, manageable concepts. Azure's evaluation of NSG rules follows a systematic approach that differs between inbound and outbound traffic. For inbound traffic, Azure first examines the rules at the subnet level, then moves to the network interface level. This order is reversed for outbound traffic, where NICE rules are evaluated before subnet rules. Understanding this evaluation order is crucial for predicting how your security rules will be applied. Let's consider a practical example. Imagine you have a web server in Azure that needs to accept HTTP traffic on port 80. If you have both subnet and NICE level NSGs, for inbound traffic, Azure will first check the subnet NSG rules for it to pass through. This demonstrates the importance of coordinating your rules across both levels. A key principle to remember is that each NSG is evaluated independently. When Azure processes the security rules for a virtual machine, it looks at all the NSGs associated with that VM's subnet and network interface. The final effective rules are a combination of these evaluations, following the precedence rules we discussed. Default rules play an important role in this evaluation process. When you don't associate an NSG with either a subnet or network interface, Azure applies its default rules. For inbound traffic, the default behavior is to deny all traffic except from within the virtual network and from Azure Load Balancer. For outbound traffic, the default allows communication within the virtual network and to the Internet. Priority numbers are crucial in determining which rules take precedence. A practical tip is to leave gaps in your priority numbering. For example, using 100, 200, 300 instead of consecutive numbers. This makes it easier to insert new rules later without having to modify existing ones. For instance, if you need to add a rule between priorities 100 and 200, you have plenty of room to use numbers like 150. Intra-subnet traffic is another important consideration. By default, Azure allows virtual machines in the same subnet to communicate with each other. However, you can modify this behavior by creating specific rules in your NSGs. This capability is particularly useful in scenarios where you need to segment traffic even within the same subnet. One of the most valuable tools for understanding your effective security rules is the Effective Security Rules view in the Azure portal. This tool shows you exactly which rules are being applied to your resources, helping you troubleshoot and verify your security configuration. I strongly recommend using this tool when setting up or modifying your NSG rules. Best practices for managing effective rules include: always document your rule configurations and their intended purposes. Regularly audit your rules to ensure they align with your security requirements. Use clear naming conventions for your rules. Test your configurations in a non-production environment first. Keep your rule sets as simple as possible while meeting security requirements. Remember, when troubleshooting connectivity issues, you need to consider both the source and destination NSGs, as traffic must be allowed through both to establish communication. The Effective Rules view can be particularly helpful in identifying where traffic might be getting blocked. Let's explore how to effectively configure security rules in Azure Network Security Groups. The Azure portal provides a user-friendly interface for creating these rules, but understanding the key configuration parameters is crucial for implementing effective network security. Let's start with the source configuration, which is fundamental for controlling inbound traffic. When configuring the source, you have several flexible options. You can specify any to apply the rule to all sources, use specific IP addresses or ranges for granular control, leverage application security groups for application-centric security, or use service tags for Azure services. For instance, if you're setting up a web server, you might want to allow inbound traffic from the Internet Service tag on port 80 or 443. Moving to destination configuration, which controls outbound traffic, you have similar options but with some key differences. You can target specific destinations using IP addresses, define rules for entire virtual networks, or use application security groups. For example, if you have a database server, you might want to restrict outbound traffic to only your specific application server's IP addresses. The service selection is where you define what type of traffic is allowed or denied. Azure provides a comprehensive list of predefined services, making it easy to configure common scenarios. Instead of remembering port numbers, you can simply select services like HTTPS, RDP, SSH, DNS, or FTP. Each service selection automatically configures the appropriate protocol and port ranges. If you need something specific that's not in the predefined list, you can create custom service definitions with your own protocol and port combinations. Priority assignment is crucial for determining the order in which rules are processed. Think of priority as a ranking system. The lower the number, the higher the priority. A best practice is to use increments of 100, like 100, 200, 300, when assigning priorities. This approach leaves room for inserting new rules between existing ones without having to reorganize your entire rule set. For example, if you need to add a rule between priorities 100 and 200, you can use 150. Here are some practical tips for configuring your rules. Start with the most specific rules at higher priorities, lower numbers. 2. Use service tags where possible to simplify management. 3. Document your rule priorities and their purposes. 4. Regular audit your rule configurations to ensure they remain appropriate. 5. Test new rules in a non-production environment first. When implementing these rules, consider the following scenarios. For a web application, you might create a rule with priority 100, allowing inbound HTTP/HTTPS traffic from any source. Follow it with a rule at priority 200, allowing inbound management traffic like RDP or SSH only from your management IP addresses. Set a rule at priority 300 for database traffic, allowing it only from your application security group. Finally, have a low priority rule, high number, that denies all other traffic. Remember, You can always use the Azure portal's Effective Security Rules view to validate your configuration and understand exactly how your rules are being applied. Let's explore application security groups in Azure, a powerful feature that simplifies network security management by allowing you to organize and protect resources based on your application architecture rather than IP addresses or subnets. Let's start with a practical scenario. Imagine you're running an online retail platform with web servers and database servers. Traditional network security would require you to manage multiple IP addresses and complex rule sets. Application security groups transform this approach by letting you think in terms of application components. The implementation process follows 3 key steps. First, we create our application security groups. In our retail platform example, we create 2 ASGs, WebASG for our web servers and DBASG for our database servers. These groups serve as logical containers that we'll use in our security rules. The second step involves assigning virtual machine network interfaces to these groups. Each web server's NIC gets assigned to WebASG, and each database server's NIC goes to DBASG. This assignment is dynamic. As you add or remove VMs, you simply assign them to the appropriate ASG, and they automatically inherit the security rules. The third step is where we configure our network security group rules using these ASGs. Let's break down a typical rule set. Our highest priority rule, 100, allows incoming traffic from the Internet to WebASG on ports 80 and 443 for customer access. The next rule, 110, permits traffic from WebASG to DBASG on port 1433 for database communication. A final rule, 120, denies all other access to DBASG, ensuring database security. This configuration offers several significant advantages. First, you no longer need to maintain IP addresses in your security rules. As your application scales and VMs come and go, the rules remain unchanged because they reference ASGs rather than specific IP addresses. Another benefit is subnet independence. Traditional network security often relies on subnet-based segregation, but ASGs free you from this constraint. You can group VMs based on their role in your application, regardless of their subnet location. Rule management becomes significantly simpler with ASGs. Instead of creating and maintaining separate rules for each VM, you create rules once for the ASG. The workload-centric organization is particularly valuable for modern applications. ASGs align with how we think about application architecture, in terms of tiers and components rather than network topology. This makes your security configuration more intuitive and easier to maintain. Let's consider some best practices when implementing ASGs. Create ASGs based on application roles rather than network location. Use clear descriptive names for your ASGs that reflect their purpose. Document your ASG assignments and rule configurations. Regularly review and audit your ASG memberships. Consider using ASGs in combination with traditional subnet-based security for defense in depth. When troubleshooting, remember that ASGs make it easier to understand and verify your security configuration. You can quickly see which VMs are in each group and what rules apply to them, simplifying the process of diagnosing connectivity issues. Let's go through each question and understand the correct answers and their explanations in detail. Question 1. Which security rule takes precedence? Correct. Answer. B. The deny rule takes precedence. Explanation. In Azure NSGs, rule precedence is determined by priority numbers, where lower numbers have higher priority. In this scenario, the deny rule has a priority of 150. The allow rule has a priority of 200. Since 150 is lower than 200, the deny rule takes precedence. This is a fundamental principle of NSG rule processing that ensures consistent and predictable traffic control. Always remember, lower priority number, higher precedence. Question 2. How do ASGs enhance network security? Correct answer, C. By grouping VMs according to their functions. Explanation: Application Security Groups, ASGs, provide several key benefits. They allow logical grouping of VMs based on workload or application function. They eliminate the need to manage individual IP addresses in security rules. They simplify rule management by applying rules to groups rather than individual VMs. They provide a more application-centric approach to network security. While options A, encryption, and B, antivirus, are important security measures, they are not functions of ASGs. ASGs focus on organizing and controlling network traffic based on application architecture. Question 3. What happens to unmatched traffic? Correct. Answer: B. Network traffic is denied. Explanation: Azure NSGs follow a secure by default approach. Any traffic that doesn't match explicit allow rules is automatically denied. This is handled by the default deny all inbound rule that exists in every NSG. The default rule has the lowest priority, highest number, to ensure it only applies after all other rules are evaluated. This security-first approach ensures that only explicitly permitted traffic can flow through your network. Key takeaways: Priority numbers. Always pay attention to priority numbers when creating rules. Lower numbers take precedence, allowing you to create a precise traffic control hierarchy. 2. ASG implementation. Use ASGs to simplify your security management by grouping related VMs together. This approach is particularly valuable in complex environments with many VMs serving different functions. 3. Default security. Remember that Azure's default deny stance provides a secure foundation. Build your allow rules on top of this foundation to create a robust security posture. Best practices: leave gaps between priority numbers, e.g. 100, 200, 300, to make it easier to insert new rules later. Document your rule priorities and their purposes. Regularly review and audit your security rules to ensure they align with your security requirements. Use ASGs to simplify rule management in complex environments. Always follow the principle of least privilege when creating allow rules. Today we'll explore Azure Virtual Network Peering, a powerful networking feature that allows you to seamlessly connect virtual networks in Azure. Think of VNet peering as building a high-speed private highway between two virtual networks, enabling them to communicate as if they were one network, while still maintaining their separate management and security boundaries. Let's start with the two types of VNet peering, regional and global. Regional peering connects virtual networks within the same Azure region. This is like connecting networks in neighboring buildings. It's straightforward and provides the lowest latency possible. You can implement regional peering in any Azure environment, whether it's the public cloud, China cloud, or government cloud regions. Global peering, on the other hand, extends your network connectivity across Azure regions. Imagine connecting offices in different cities. Global peering makes this possible within Azure's infrastructure. It's available in both the Azure Public Cloud and China Cloud, though it's important to note that global peering between different government cloud regions isn't supported due to compliance requirements. Now let's explore the significant benefits that make VNet peering such a valuable networking solution. First and foremost is private network connectivity. All traffic between peered networks stays on the Microsoft Azure backbone network. It never touches the public internet. This provides inherent security and privacy for your inter-network communications. Performance is another key advantage. Because VNet peering utilizes Azure's backbone infrastructure, you get a low latency, high bandwidth connection between your resources. This is particularly important for applications that require quick response times or need to transfer large amounts of data between networks. The simplification of network communication is a major benefit. Once networks are peered, resources in one network can directly communicate with resources in the other network. There's no need for complex routing configurations or additional networking devices. This simplification extends to data transfer across Azure subscriptions, deployment models, and regions. A particularly valuable aspect of VNet peering is its non-disruptive implementation. You can establish peering connections without any downtime for your existing resources. This zero downtime characteristic makes it ideal for production environments where service continuity is crucial. When implementing VNet peering, keep in mind these important considerations. Peering is non-transitive. If network A is peered with network B, and network B is peered with network C, network A cannot communicate with network C through the peering address spaces cannot overlap. Ensure your virtual networks have unique IP address ranges. You can peer networks across different subscriptions, enabling flexible organizational structures. Once peered, the networks maintain their independent management, allowing separate teams to manage their respective networks. Best practices for implementing VNet peering include: plan your address spaces carefully to avoid future conflicts. Document your peering connections and their purposes. Use naming conventions that clearly identify peered networks. Regularly review your peering configurations to ensure they align with your network architecture. Consider cost implications, especially for global peering with data transfer between regions. Let's explore VPN gateway transit in Azure Virtual Network Peering, a powerful feature that enables centralized connectivity management. In your cloud infrastructure, this capability is particularly valuable in hub-and-spoke network architectures, where a central hub virtual network provides shared services to connected spoke networks. Let's start with the fundamental concept. In Azure, each virtual network can have only one VPN gateway. However, through gateway transit, you can share this gateway with other peered virtual networks. Think of it as having a single, secure entrance to your building that can be used by multiple departments, rather than each department needing its own separate entrance. The hub-and-spoke topology is the most common implementation of gateway transit. In this architecture, you have a central hub virtual network that contains the VPN gateway and other shared resources. This hub network is then peered with multiple spoke networks. The spoke networks can use the hub's VPN gateway to access resources outside the peering relationship, such as on-premises networks through site-to-site VPN connections, other virtual networks through VNet to VNet connections, remote clients through point-to-site VPN connections. This arrangement offers several significant advantages. First, it's more cost-effective since you only need to deploy and maintain a single VPN gateway instead of one in each virtual network. Second, it simplifies network management by centralizing your connectivity infrastructure. Third, it provides a consistent and secure way to manage external connections. Gateway transit works with both regional and global virtual network peering. This means you can implement this architecture whether your spoke networks are in the same region as the hub or distributed across different regions. This flexibility allows you to design a network topology that matches your organizational needs while maintaining efficient connectivity. Security is a crucial aspect of gateway transit. When implementing this feature, you have fine-grained control through network security groups, NSGs. You can create rules to control traffic flow between peered networks, define which resources in spoke networks can access the gateway, implement different security policies for different spoke networks, monitor and audit gateway transit traffic. Let's consider some best practices for implementing gateway transit. Plan your address spaces carefully to avoid overlap between hub and spoke networks. Document your gateway transit configurations and their purposes. Use clear naming conventions for your network resources. Regularly review and audit your security configurations. Monitor gateway usage and performance. Consider implementing additional security measures like Azure Firewall in the hub network. Common scenarios where gateway transit proves particularly valuable include organizations with multiple departments needing shared internet access, companies connecting cloud resources to on-premises networks, enterprises with distributed regional offices requiring centralized connectivity, development environments needing controlled access to shared resources. When troubleshooting gateway transit, remember to check both the peering configuration and the NSG rules. The Allow Gateway Transit option must be enabled on the hub network, and Use Remote Gateways must be enabled on the spoke networks. Let's walk through the process of creating virtual network peering in Azure, focusing on the requirements, implementation steps, and how to verify your peering status. This is a crucial skill for network administrators working with Azure infrastructure. Let's start with the prerequisites. Before you can create a peering connection, you need the appropriate permissions. The network contributor or classic network contributor role is required. This role ensures you have the necessary permissions to manage network resources in Azure. If you're using a custom role, make sure it includes the necessary permissions for peering operations. You'll also need 2 virtual networks to create a peering connection. These networks must have non-overlapping IP address spaces. This is a critical requirement that prevents routing conflicts. For example, if VNet A uses 10.00.0.0/16 and VNet B uses 10.1.0.0/16, they can be peered because their address ranges don't overlap. The implementation process follows a 2-way setup pattern. Think of it like establishing a handshake between networks. First step, you initiate the peering from the first virtual network, let's call it VNet A, to the second virtual network, VNet B. When you complete this step, the peering status will show as initiated. At this point, the connection is only halfway established. Traffic can't flow between the networks yet. Second step, you then create the reciprocal peering from VNet B back to VNet A. This completes the handshake, and when successful, the status of both peerings will change to connected. Only then can traffic flow between the virtual networks according to your configured rules. Monitoring the peering status is crucial for troubleshooting. Here are the key states you'll encounter. Initiated. The initial state after creating the first peering connection. Connected. The final state indicating successful bidirectional peering. If using classic deployment model, you might also see updating status during transitions. Some important points to remember when creating peering planning considerations. Ensure your address spaces are properly planned. Verify you have the necessary permissions. Document your peering configurations. Implementation. Best practices: use clear naming conventions for your peerings. Create both peering connections in close succession. Verify the connected status on both sides. Test connectivity after establishment. Common troubleshooting. Steps: check permissions if peering creation fails. Verify address space overlap. If configuration is rejected, confirm both sides of the peering are properly configured. Monitor the peering status in the Azure portal. After the peering is established and shows connected on both sides, virtual machines in the peered networks can communicate with each other based on your configured network security rules. However, remember that this communication capability doesn't automatically override any existing network security group rules. Today, we're going to explore how to extend virtual network peering capabilities in Azure beyond their basic limitations. This is crucial knowledge for building complex enterprise-grade network architectures in the cloud. Let's start with a fundamental characteristic of VNet peering. It's non-transitive. This means if network A is paired with network B and network B is paired with network C, there's no automatic communication path between networks A and C. Think of it like introducing friends. Just because you know both Alice and Bob doesn't mean they automatically know each other. To overcome this limitation and build more complex network architectures, Azure provides three powerful mechanisms: hub and spoke networks, user-defined routes, and service chaining. Let's explore each of these in detail. The hub and spoke network architecture is like creating a central airport hub with multiple connecting flights. In this model, you have a central hub virtual network that hosts shared services and infrastructure components like network virtual appliances, NVAs, and VPN gateways. Multiple spoke networks connect to this hub through peering. This approach offers several benefits: centralized security and monitoring through the hub, efficient resource sharing across spokes, simplified management of common services, cost-effective use of shared resources. User-defined routes, UDRs, are like creating custom road signs in your network. They allow you to override Azure's default system routes and define custom paths for network traffic. In the context of peering, UDRs can direct traffic to specific virtual machines in peered networks, route traffic through network virtual appliances, send traffic to VPN gateways, create complex routing scenarios that go beyond basic peering. Service chaining complements UDRs by allowing you to create sophisticated traffic flows through virtual appliances or gateways. Think of it as creating a specific sequence of security checkpoints that traffic must pass through. This enables scenarios like forcing all interspoke traffic through a firewall in the hub, implementing sophisticated security inspection, creating advanced networking patterns with multiple service points. Here's a practical example of how these mechanisms work together. You set up a hub network with a firewall, NVA, and VPN gateway. Multiple spoke networks peer with the hub. You use UDRs to route all interspoke traffic through the hub's firewall. Service chaining ensures traffic follows your defined path through the security appliances. Best practices for implementing these extension mechanisms include: plan your address spaces carefully to avoid future conflicts. Document your routing configurations thoroughly. Monitor traffic patterns to ensure optimal performance. Regularly review and audit your security configurations. Consider scalability when designing your hub and spoke architecture. Common challenges and solutions: scaling beyond peering limits. Use multiple layers of hub and spoke networks. Implement regional hubs for geographic distribution. Utilize transit networks for complex connectivity requirements. Performance optimization. Place frequently communicating resources in the same region. Monitor network virtual appliance performance. Use appropriate SKUs for your gateways and appliances. Security considerations. Implement network security groups at multiple levels. Use service tags for simplified security rules. Regular security audits of routing configurations. Let's analyze each question and understand the correct answers in detail. Question 1. When virtual networks are successfully peered, what's the peering status for both virtual networks in the peering? Correct answer, B. Connected explanation. The peering status progression works as follows. When you initially create peering from the first VNet to the second, the status shows as initiated. Only after establishing the reciprocal peering connection does the status change to connected for both networks. Connected status indicates a successful bidirectional peering relationship. This status is crucial for verifying that your peering is properly configured and functional. Both VNets must show connected for traffic to flow between them. Question 2. What approach enables peered virtual networks to share the gateway and get access to resources? Correct answer, C. Gateway. Transit explanation. Gateway transit is the correct solution because it allows spoke networks to use the hub network's VPN gateway, enables centralized management of external connectivity, provides cost-effective sharing of gateway resources, supports both regional and global peering scenarios, allows multiple VNets to access shared resources through a single gateway, point-to-site connectivity is for individual client connections, and transitivity isn't a feature of VNet peering. Peering is non-transitive. Question 3. How is Azure Virtual Network peering best described? Correct. Answer. A. Traffic between virtual networks is kept on the Microsoft backbone network. Explanation. This is the correct description because VNet peering keeps all traffic on Microsoft's private network infrastructure, provides high bandwidth, low latency connectivity, offers better security by avoiding public internet, works across regions, global peering, doesn't disrupt existing resources or require same region deployment. Key takeaways. Status verification. Always check for connected status on both sides. Monitor peering status through Azure Portal or API. Use this status as a primary troubleshooting indicator. 2. Gateway sharing. Gateway transit is a powerful feature for hub-spoke architectures. Enables efficient resource sharing. Reduces complexity and costs. Provides centralized connectivity management. 3. Peering characteristics. Private, secure communication over Microsoft backbone. Supports both regional and global connectivity. No resource disruption during setup. High performance and reliability best practices. Regularly monitor peering status. Document gateway transit configurations. Plan address spaces carefully to avoid conflicts. Implement appropriate security measures. Consider cost implications of global peering. Azure system routes form the backbone of network traffic management in the cloud environment. They operate as an intelligent traffic control system, ensuring data packets reach their intended destinations efficiently and securely. Let's explore how this crucial component of Azure networking functions in real-world scenarios. Within your Azure infrastructure, system routes automatically manage several types of communication. When data needs to travel between virtual machines in the same subnet, system routes ensure this happens seamlessly. For virtual machines in different subnets, these routes coordinate the traffic flow while respecting any security boundaries you've established. This automatic management extends to internet-bound traffic and communications with your on-premises networks through VPN or express route connections. The magic happens through route tables, which act as the central nervous system of your network traffic management. Each route table contains a set of rules that define how packets should be directed through your virtual network. These rules can point to various destinations: virtual machines, network gateways, virtual appliances, or the Internet. When a packet needs to travel from one point to another, Azure consults these rules to determine the optimal path. Consider a practical example. Imagine you're running a multi-tier application with web, application, and database layers. The web tier needs Internet access to serve customers, while the database tier should only communicate with the application tier. System routes, through their associated route tables, automatically handle this traffic segregation. The web tier subnet can have routes allowing Internet access, while the database tier subnet's routes might restrict traffic to only the application tier subnet. Route evaluation follows a specific precedence order, ensuring consistent and predictable behavior. When multiple routes exist, Azure examines them from most specific to least specific. This means custom routes can override system routes when necessary, giving you precise control over your network traffic patterns while maintaining the convenience of automatic routing for standard scenarios. Each subnet in your virtual network can have its own route table, providing granular control over different parts of your network. This flexibility allows you to implement varying routing behaviors across your infrastructure while maintaining a coherent overall networking strategy. For instance, you might want different routing rules for development and production environments, or specific routing patterns for different application components. If a matching route cannot be found for a packet, Azure drops it by default. This security-first approach ensures that only explicitly allowed traffic flows through your network. However, Azure's default routes handle most common scenarios automatically, meaning you only need to create custom routes for specific requirements or unique architectural needs. This combination of automatic management and customization capabilities makes Azure System Routes a powerful tool in your cloud networking arsenal. While the system handles routine traffic management automatically, you retain the ability to implement custom routing when your architecture requires it, striking an ideal balance between convenience and control. User-defined routes, commonly known as UDRs, represent Azure's flexible approach to custom network traffic management. While Azure's system routes handle most networking scenarios effectively, there are situations where you need more precise control over your network traffic flow. This is where UDRs come into play, offering granular control over network packet routing. The power of UDRs lies in their ability to define custom paths for network traffic through what we call next hop targets. Think of next hop targets as the next destination in a packet's journey through your network. These targets can be various Azure resources: a virtual network gateway for connecting to on-premises networks, another virtual network for inter-network communication, the Internet for external access, or a network virtual appliance, NVA, for specialized network functions. Let's explore a practical scenario. Imagine you're running a security-conscious enterprise application in Azure. You want all Internet-bound traffic from your application subnet to pass through a firewall appliance for inspection before reaching the Internet. Using UDRs, you can create a route that directs all Internet-bound traffic to your firewall NVA first, rather than allowing direct Internet access. This creates an additional security layer for your outbound traffic. Route tables play a crucial role in implementing UDRs. Each route table can be associated with multiple subnets, allowing you to apply consistent routing rules across different parts of your network. However, it's important to note that each subnet can only be associated with one route table. This one-to-many relationship helps maintain clear and manageable routing hierarchies in your network architecture. A significant advantage of UDRs is their integration with network virtual appliances. NVAs can perform specialized network functions like firewalling, WAN optimization, or load balancing. By combining UDRs with NVAs, you can create sophisticated network architectures that meet specific security or performance requirements. For example, you might deploy an NVA between two subnets to inspect all inter-subnet traffic, using UDRs to ensure packets flow through the NVA. One particularly appealing aspect of UDRs in Azure is that there are no additional charges for creating route tables. This means you can implement complex routing scenarios and make frequent routing adjustments without worrying about increasing your cloud infrastructure costs. The freedom to customize your network routing without additional costs enables you to focus on designing the most effective network architecture for your needs. In complex network scenarios, UDRs often work alongside system routes to create comprehensive traffic management solutions. For instance, you might use system routes for routine internal communication while implementing UDRs for specific traffic patterns that require special handling. This hybrid approach allows you to maintain the simplicity of system routes where appropriate while adding custom routing where needed. Remember, while UDRs provide powerful customization capabilities, they should be implemented thoughtfully. Each custom route adds complexity to your network configuration, so it's important to document your routing decisions and maintain a clear understanding of your traffic flow patterns. Regular review and optimization of your UDRs ensure they continue to meet your evolving network requirements while maintaining security and performance. Service endpoints represent a crucial advancement in Azure networking, fundamentally changing how your virtual network resources interact with Azure services. This feature bridges the gap between your virtual network and Azure services by allowing you to use private IP addresses while maintaining secure and direct communication paths. At its core, a service endpoint transforms how your virtual network identifies itself to Azure services. When you enable service endpoints, you're essentially extending your virtual network's identity to the Azure service you want to connect with. This extension creates a secure and direct pathway for communication, eliminating the need for public internet exposure. One of the most significant advantages of service endpoints is the shift from public to private IP addressing. Traditionally, Azure service traffic from a virtual network would use public IP addresses as source IPs. However, with service endpoints enabled, this traffic switches to using virtual network private addresses. This change eliminates the need for reserved public IP addresses in your IP firewalls, simplifying your network configuration while enhancing security. Service endpoints shine in their routing optimization capabilities. In scenarios where you've implemented forced tunneling to route internet traffic through on-premises or network virtual appliances, service endpoints provide a way to optimize Azure service traffic. They allow this traffic to flow directly to the service on the Microsoft Azure backbone network, bypassing any forced tunneling configurations while maintaining security and performance. The implementation of service endpoints is remarkably straightforward. Configuration happens at the subnet level, with no additional overhead required for endpoint maintenance. This simplicity extends to infrastructure requirements. You don't need NAT devices, gateway appliances, or reserved public IP addresses to establish and maintain these service endpoints. However, it's crucial to note some important considerations when implementing service endpoints. The switch from public to private IPv4 addresses can impact existing Azure Service Firewall rules that rely on public IP addresses. It's essential to review and update these rules before enabling service endpoints to ensure uninterrupted service access. Additionally, you might experience a brief service interruption during the initial configuration of service endpoints. Security benefits are particularly noteworthy. When you combine service endpoints with virtual network rules, you can completely remove public internet access to your Azure service resources while still allowing traffic from your virtual network. This configuration creates a highly secure environment where your resources are accessible only through authorized private network paths. Think of service endpoints as building a private highway between your virtual network and Azure services. This highway bypasses the public internet entirely, runs on Microsoft's backbone network, and ensures your traffic takes the most direct and secure route possible. This direct routing not only improves security, but can also enhance performance by avoiding unnecessary network hops and potential internet-related latency. Azure Service Endpoints provide secure and direct connectivity to a wide range of Azure services, each offering specific benefits and capabilities. Let's explore the key services that support service endpoints and their unique characteristics. Azure Storage serves as a fundamental service endpoint option available across all Azure regions. This integration provides an optimized route to Azure storage services, with each storage account supporting up to 100 virtual network rules. This makes it ideal for organizations requiring secure and efficient access to their storage resources. For database services, Azure SQL Database and SQL Data Warehouse implement a sophisticated firewall security feature. This allows precise control over database communication from specific subnets within your virtual networks. Similarly, Azure Database for PostgreSQL and MySQL support service endpoints where these database services are available, extending your virtual network's private address space to these database servers. Azure Cosmos DB takes security a step further by allowing you to restrict access to specific subnets within your virtual network. Once you enable the service endpoint for Cosmos DB, you can create granular access controls by adding specific subnets to your Cosmos DB account. This ensures that only authorized networks can access your Cosmos DB resources. Key Vault integration with service endpoints provides a crucial security layer for your secrets and certificates. This integration allows you to restrict Key Vault access to specified virtual networks and IPv4 address ranges, effectively creating a secure enclave for your sensitive information. For messaging services, both Azure Service Bus and Event Hubs support service endpoints across all Azure regions. This integration is particularly valuable for workloads running on virtual machines within virtual networks, as it provides secure access to messaging capabilities with traffic secured at both ends of the communication path. The implementation of these service endpoints follows a consistent pattern, though each service has its unique configuration requirements and documentation. It's important to note that the initial setup can take up to 15 minutes to complete, and you should plan accordingly when implementing these endpoints in your environment. Azure Private Link represents a revolutionary advancement in cloud networking architecture, fundamentally transforming how organizations connect to and secure their Azure services. This comprehensive service delivers private connectivity to Platform as a Service, PaaS offerings, customer-owned services, and Microsoft partner services, while maintaining the highest levels of security and network isolation. Let's explore the depth and breadth of this powerful networking solution. At the heart of Private Link's functionality is its ability to keep all traffic contained within Microsoft's global network infrastructure. This containment provides an unprecedented level of security and performance optimization. Unlike traditional networking approaches that might expose services to the public internet, Private Link creates a secure, private channel for all service communications. This approach eliminates the security risks associated with public internet exposure while maintaining the simplicity and scalability that organizations require in their cloud infrastructure. The global nature of Private Link sets it apart from many other networking solutions. There are no regional restrictions to consider. You can establish private connections to services running in any Azure region worldwide. This global accessibility doesn't compromise security. Instead, it enhances your ability to build truly global applications while maintaining strict security controls. Organizations can confidently deploy services in different regions and connect to them privately, regardless of the geographical distance involved. One of the most powerful aspects of Private Link is its ability to integrate services directly into your virtual network through private endpoints. When you map your network to a private endpoint, the associated service essentially becomes part of your virtual network. This integration creates a seamless experience where services appear to be running locally within your network, even though they're actually Azure PaaS services. This capability extends beyond just Microsoft services. You can use Private Link to deliver your own services privately to your customers' virtual networks, creating new possibilities for secure service delivery. The architectural simplification that Private Link brings is remarkable. In traditional networking setups, connecting to cloud services often requires a complex array of networking components. Gateways, NAT devices, express route circuits, VPN connections, and public IP addresses. Private Link eliminates the need for all of these components when accessing supported services. All traffic routes through the private endpoint, creating a streamlined, secure, and easy-to-manage networking environment. From a security perspective, Private Link offers robust protection against data exfiltration. When you map private endpoints to Azure PaaS resources, you create a controlled environment where only specifically mapped resources are accessible, even in the event of a security incident within your network. This granular control significantly reduces the attack surface and helps prevent unauthorized data access. Organizations can implement precise access controls and maintain clear visibility over all service connections. The integration capabilities of Private Link extend well beyond basic connectivity. When working with on-premises networks and peered virtual networks, Private Link provides seamless access through private peering or VPN tunnels. Since all traffic stays on the Microsoft network, there's no need to establish public peering or rely on internet connectivity for workload migration to the cloud. This makes Private Link an ideal solution for organizations with strict security requirements or those operating under rigorous regulatory frameworks. Private Link's cross-tenant functionality deserves special attention. It enables organizations to unify their experience across different services and Azure tenants. The ability to send, approve, or reject connection requests directly, without complex permission schemes or role-based access controls, streamlines the process of establishing secure service connections across organizational boundaries. From an operational perspective, Private Link significantly simplifies network management. The service automatically handles many aspects of connectivity, reducing the operational overhead typically associated with managing secure network connections. This automation extends to DNS resolution, routing, and network security, allowing networking teams to focus on higher value activities rather than routine configuration tasks. The scalability aspects of Private Link are equally impressive. As your organization grows and your service requirements evolve, Private Link can scale with you. Whether you're connecting to additional services, expanding to new regions, or increasing your workload, Private Link maintains its performance and security characteristics without requiring significant reconfiguration or architectural changes. For organizations concerned about compliance and data sovereignty, Private Link provides strong controls and clear boundaries for data flow. Since all traffic remains on the Microsoft backbone network, organizations can more easily demonstrate compliance with various regulatory requirements regarding data transmission and privacy. This aspect is particularly valuable for organizations operating in highly regulated industries or regions with strict data protection laws. Let's go through each question and understand the correct answers along with detailed explanations. Question 1. Which statement best describes Azure routing? Correct answer. When the next hop type is none, traffic is dropped. Explanation. This statement accurately describes a fundamental aspect of Azure routing behavior. Let's examine why this is correct and why the other options are incorrect. When the next hop type is none, traffic is dropped is correct because this is a built-in security feature of Azure networking. When no valid route exists or when the next hop is explicitly set to none, Azure automatically drops the traffic to prevent potential security risks. Administrators can create system routes is incorrect because system routes are automatically created and managed by Azure. Administrators can create user-defined routes, UDRs, but not system routes. Azure gateways are needed to route traffic between subnets is incorrect because Azure automatically routes traffic between subnets within the same virtual network without requiring any gateways. Question 2. What's a valid next hop type? Correct answer. Internet explanation. The Internet is a valid next hop type in Azure routing. Let's analyze all options. Internet is correct because it's one of the standard next hop types in Azure routing. When you want traffic to be routed to the public Internet, you use this next hop type. Load balancer is incorrect because it's not a next hop type. While load balancers are important Azure resources, they aren't classified as next hop types in routing tables. ExpressRoute is incorrect because it's not a next hop type by itself. While ExpressRoute connections are used for private connectivity, the actual next hop type would be Virtual Network Gateway when routing traffic through ExpressRoute. Valid next hop types in Azure include Virtual Network, Gateway, Virtual Network, Internet, Virtual Appliance, None. Virtual Network Service Endpoint Question 3. How can you extend the company's private address space with direct connections to Azure resources. Correct answer: virtual network endpoints. Explanation: virtual network endpoints are the correct solution for extending private address space with direct connections to Azure resources. Here's why. Virtual network endpoints is correct because they allow you to extend your private network's addressing to Azure services, creating direct, private connections to Azure resources without exposing them to the public internet. User-defined routes is incorrect because while UDRs help control traffic flow within your network, they don't extend your private address space or create direct connections to Azure resources. Virtual appliances is incorrect because while they can help manage and secure network traffic, they don't inherently extend your private address space or create direct connections to Azure resources. Azure Load Balancer stands as a fundamental networking component in the Azure ecosystem, providing high availability and network performance optimization for your applications. This sophisticated service acts as an intelligent traffic distributor, ensuring your application resources are utilized efficiently while maintaining optimal performance and reliability. Let's dive deep into understanding this crucial Azure service. The architecture and components. At its core, Azure Load Balancer operates through 4 essential components that work in harmony to deliver efficient load balancing. 1. Front-end IP configuration. This component serves as the entry point for all incoming traffic. The front end can be configured with either a public IP address for internet-facing applications or an internal IP address for internal network traffic. This flexibility allows you to implement load balancing solutions for both external and internal scenarios. The front-end IP configuration essentially determines how your load balancer is exposed to the network and what type of traffic it can handle. 2. Backend pools. Backend pools represent the collection of resources that will receive and process the distributed traffic. These typically include Azure virtual machines or instances within Azure Virtual Machine Scale sets. You can organize your backend resources based on various factors such as application tiers, functionality, or performance requirements. The load balancer ensures that traffic is distributed efficiently across all resources in the backend pool according to the defined rules and health status of each resource. Health probes. Health probes are crucial for maintaining service reliability. They continuously monitor the health status of all resources in your backend pools. These probes send periodic checks to each backend resource and expect specific responses to determine if the resource is healthy and capable of receiving traffic. If a resource fails to respond appropriately to health probes, it is automatically removed from the traffic distribution until it. 4. Load balancing rules. These rules define how traffic should be distributed across the backend resources. They specify important parameters such as protocol, TCP or UDP, source and destination ports, backend pool associations, health probe configurations, session persistence settings. The rules can be customized to match your specific application requirements and traffic patterns. Types and implementation scenarios. Azure Load Balancer comes in 2 primary variants. Public Load Balancer, designed for internet-facing applications, provides outbound connections for virtual machines inside your virtual network. Maps public IP addresses to virtual machines in your back-end. Pool enables external access to your applications while maintaining security and performance. Internal Load Balancer operates within your private network, handles traffic between resources in your virtual network, supports scenarios where private endpoints are required, enables creation of multi-tier applications with secured backend tiers. Both types can be used simultaneously in a combination configuration, allowing you to create complex application architectures with both public-facing and internal load balancing requirements. Performance and scaling. One of the most impressive aspects of Azure Load Balancer is its ability to scale to millions of TCP and UDP application flows. This massive scalability ensures that your applications can handle substantial traffic volumes without degradation in performance. The service automatically scales with your application's needs, requiring no manual intervention or configuration changes. Implementation considerations. When implementing Azure Load Balancer, consider the following best practices. Traffic pattern analysis. Analyze your application's traffic patterns. Determine the appropriate load balancing rules. Configure session persistence if required. Plan for both inbound and outbound scenarios. Health probe configuration. Set appropriate probe intervals. Define suitable timeout values. Configure proper health check endpoints. Implement comprehensive health check logic. High availability. Planning. Distribute resources across availability zones. Implement redundant backend resources. Configure appropriate failover scenarios. Monitor load balancer metrics. Security considerations. Implement network security groups. Configure appropriate access controls. Monitor and log load balancer traffic. Regular security assessment and updates. Operational management. For optimal operation of Azure Load Balancer. Monitoring. Track performance metrics. Monitor resource health. Analyze traffic patterns. Review load. Distribution maintenance. Regular health probe verification. Backend pool. Resource optimization. Rule configuration updates. Performance tuning troubleshooting. Health probe failure investigation. Connection problems. Resolution performance. Bottleneck identification. Load distribution optimization. Cost optimization. While implementing Azure Load Balancer, consider choosing the appropriate SKU based on your needs, optimizing back-end pool resources, monitoring and adjusting capacity as needed, implementing proper scaling policies. Azure Load Balancer serves as a crucial component in building highly available and scalable applications in Azure. Its flexible configuration options, robust health monitoring, and impressive scalability make it an indispensable tool for modern cloud applications. Understanding its components and capabilities allows you to implement efficient load balancing solutions that meet your application's specific requirements while maintaining optimal performance and reliability. The implementation of a public load balancer in Azure represents a sophisticated approach to managing and distributing incoming internet traffic across multiple virtual machines. This critical networking component serves as an intelligent traffic cop, ensuring optimal resource utilization while maintaining high availability and performance for your web applications. Understanding traffic flow. In a typical public load balancer implementation, the traffic flow follows a well-defined path. Initial request phase. Internet clients initiate requests to your application, typically targeting a public IP address. For web applications, these requests commonly arrive on TCP port 80, HTTP, or port 443, HTTPS. The public IP address serves as the front end of your load balancer, providing a single point of contact for all incoming traffic. Load balancer interception. As traffic reaches the public IP address, Azure Load Balancer intercepts these requests. This interception phase is crucial, as it's where the magic of load balancing begins. The load balancer examines incoming requests and prepares to distribute them according to configured rules. Distribution process. The load balancer then distributes these requests across multiple virtual machines in your back-end pool. This distribution isn't random, but follows specific load balancing rules you've defined. These rules can consider factors such as current server load server response times, active connections geographic location, custom health metrics implementation components. To successfully implement a public load balancer, several key components must be properly configured. Public IP configuration. Assign a static public IP address. Configure DNS settings if required. Set appropriate idle timeout values. Configure IP version. IPv4, IPv6 backend pool. Setup. Add virtual machines to the pool. Configure network interfaces. Set up availability sets. Define scale sets if needed. Health probe configuration. Define probe protocol. HTTP, TCP. Set probe intervals. Configure timeout values. Specify success criteria. Load balancing rules. Define protocols and ports. Configure session persistence. Set idle timeout duration. Specify floating IP settings. Practical implementation steps. Initial setup. Plain text copy. Create resource group. 2. Create virtual network. 3. Create subnets. 4. Deploy. Virtual machines. 5. Configure network security groups. Load balancer configuration. Create public load. Balancer assign. Public IP configure. Front-end IP. Create back-end pool. Add VMs to pool rule. Configuration. Define health probes. 2. Create load balancing rules. 3. Set port. Mappings. 4. Configure session persistence. Optimization and management. For optimal performance of your public load balancer. Monitoring. Track performance metrics. Monitor health probe status. Analyze traffic patterns. Review distribution effectiveness. Security. Implement network security groups. Configure access controls. Monitor suspicious traffic. Regular security audits. Maintenance. Regular health checks. Performance optimization. Configuration. Updates. Capacity planning. Common implementation scenarios. Web application. Tier multiple web servers. HTTP, HTTPS. Traffic session persistence. SSL offloading application gateway. Integration layer 7 load balancing URL-based routing. SSL termination web application. Firewall multi-region deployment. Geographic redundancy. Traffic distribution. Disaster recovery. Performance optimization. Best practices. High availability. Use availability. Sets implement redundancy. Configure proper health probes. Plan for failover performance. Monitor back-end health. Optimize rule configuration. Balance load distribution. Regular performance testing. Security. Implement proper NSGs. Regular security updates. Monitor access patterns. Configure appropriate logging. Scalability. Plan for growth. Implement auto-scaling. Monitor capacity. Regular performance reviews. Troubleshooting considerations. When implementing a public load balancer, be prepared to address common issues. Connectivity problems. Check NSG rules. Verify health probe configuration. Review load balancing rules. Monitor back-end health performance issues. Analyze traffic patterns. Check resource utilization. Review distribution rules. Monitor response times. Configuration. Errors. Verify IP configurations. Check port mappings. Review health probe settings. Validate rule configurations. The implementation of a public load balancer, while complex, provides essential benefits for your Azure infrastructure. It ensures reliable, scalable, and efficient distribution of incoming traffic while maintaining high availability and performance. By carefully considering each component and following best practices, you can create a robust load balancing solution that meets your application's needs and provides an excellent user experience. Internal Load Balancer in Azure serves as a crucial component for managing traffic within private networks, offering sophisticated load balancing capabilities without exposing resources to the public internet. This service is particularly valuable for multi-tier applications, line-of-business systems, and scenarios requiring secure internal communication between services, implementation scenarios, and use cases. Within virtual network load balancing, the most straightforward implementation involves balancing traffic between virtual machines within the same virtual network. This scenario is common in multi-tier applications where you need to distribute workload across multiple back-end servers. For example, Web servers communicating with application servers. Application servers communicating with database servers. Microservices communicating with each other. Cross-premises virtual network implementation. This scenario enables load balancing for hybrid environments where on-premises resources need to communicate with Azure resources. Key aspects include direct connectivity through VPN or ExpressRoute seamless integration with on-premises networks. Consistent load balancing for hybrid workloads. Maintains security and privacy. Multi-tier application architecture. Internal load balancers excel in multi-tier applications where back-end tiers shouldn't be internet-facing. Consider a typical 3-tier application. Front-end tier, public-facing. Application tier, internal. Database tier, internal. The internal load balancer manages traffic between these tiers while maintaining security boundaries. Line of business applications. For internal business applications, the internal load balancer provides secure access for internal users' integration with existing infrastructure, no additional hardware requirements. Simplified management hybrid load balancer. Configuration. Combining public and internal load balancers creates sophisticated architectures. Public load balancer for internet traffic, internal load balancer for back-end communication. Segregated traffic management enhanced security control. Technical implementation details. Network, configuration, virtual network setup, subnet configuration, private IP allocation, network security groups back-end pool management, VM registration, health probe definition, port configuration, service integration, load balancing rules, protocol selection, TCP, UDP, port mapping, session persistence, distribution algorithms, key implementation considerations, security, network isolation, access control implementation, traffic flow monitoring, security group configuration, performance health probe optimization backend pool, scaling traffic distribution patterns, resource monitoring availability, redundancy planning, failover configuration, health monitoring, disaster recovery, practical implementation, steps, initial setup, create virtual network, configure subnets, define security groups, deploy backend resources, load, balancer, configuration, create internal load balancer, assign, private IP configure, front-end setup, backend pool, rule configuration, define health probes, create balancing rules, configure ports, set distribution method testing and validation, verify connectivity test failover scenarios, monitor performance, validate security implementation benefits, enhance security, no public internet exposure, network isolation, controlled access, secure communication, improved performance, efficient traffic distribution, optimize resource usage, reduced latency, scalable architecture, simplified management, centralized control, automated health monitoring, easy scaling, integrated maintenance, cost efficiency, no additional hardware, optimized resource usage, reduced complexity, simplified licensing, best practices, design considerations, plan network topology, define security boundaries, consider scaling requirements, document dependencies, implementation guidelines, use consistent naming, implement proper tagging, configure monitoring, setup logging, operational management, regular health checks, performance monitoring, security audits, capacity planning, troubleshooting and maintenance, common issues, connectivity problems, health probe failures, performance degradation, configuration errors, monitoring requirements, traffic patterns, resource utilization, health status, performance metrics, maintenance tasks, regular updates, configuration, reviews, security assessments, performance optimization. The implementation of an internal load balancer requires careful planning and consideration of various factors. Understanding the different scenarios and requirements helps in creating a robust and efficient load balancing solution. that meets your organization's needs while maintaining security and performance standards. Regular monitoring and maintenance ensure continued optimal operation and adaptation to changing requirements. Azure Load Balancer offers 3 distinct stock keeping units, SKUs, Basic, Standard, and Gateway, each designed to meet different operational requirements and use cases. Understanding the differences between these SKUs is crucial for implementing the right load balancing solution for your specific needs. Detailed SKU comparison. Basic SKU. The Basic SKU represents the entry-level offering in the Azure Load Balancer family. While it provides essential load balancing capabilities, it comes with certain limitations. Health Probes docked supports. HTTP and TCP Health Probes limited probe configurations. Basic health monitoring capabilities front-end. Configuration supports inbound front-end only. Limited to simple scenarios, basic port forwarding capabilities, security features. Open by default to all traffic optional network security group. NSG, control basic security configurations. Availability. No zone redundancy. Support limited to single availability. Set basic availability guarantees. Standard SKU. The standard SKU is the recommended choice for new deployments, offering a comprehensive feature set and enhanced capabilities. Health Probes supports HTTPS, HTTP, and TCP. Health Probes advanced probe configurations. Enhanced health monitoring capabilities, front-end. Configuration supports both inbound and outbound front-ends. Multiple front-end configurations, advanced traffic routing options, security features. Closed by default to inbound flows, mandatory NSG integration, enhanced security model. Internal traffic allowed within virtual network availability zones, zone redundant deployment options. Zonal frontends for inbound and outbound traffic, enhanced availability guarantees. Gateway. SKU. The gateway. SKU is designed for high-performance scenarios and third-party network virtual appliance NVA integration. Performance optimized for high throughput, enhanced scaling capabilities, advanced performance monitoring. Availability high availability, design advanced failover capabilities, robust reliability features. NVA support seamless integration with third-party NVA's advanced networking capabilities, enhanced routing options. Implementation considerations. New deployments. For new implementations, consider the following factors. Use standard SKU as the default choice plan for zone redundancy requirements. Consider security requirements. Evaluate performance needs existing deployments. When working with existing deployments, evaluate upgrade paths to standard SKU. Assess impact on existing applications. Plan migration strategies. Consider downtime requirements. Security planning. Security considerations vary by SKU, basic SKU, default open access. Manual NSG configuration. Basic security features. Standard SKU, default closed access. Required NSG configuration, enhanced security features, performance planning. Performance considerations by SKU, basic, SKU. Limited scaling options, basic performance metrics. Standard SLA, standard SKU, advanced scaling, enhanced metrics, higher SLA guarantees. Gateway SKU, maximum performance, advanced monitoring, premium SLABIS practices. SKU selection, choose standard. SKU for new deployments. Consider Gateway SKU for high-performance needs. Use Basic SKU only for legacy applications. Security implementation. Plan NSG configurations in advance. Implement proper access controls. Regular security assessments. Monitor security metrics. Availability. Planning leverage zone redundancy. Where available, plan for disaster recovery. Implement proper health probes. Monitor availability metrics. Cost optimization. Evaluate SKU pricing models, plan for scaling requirements, monitor resource utilization, optimize configurations. The choice of load balancer SKU significantly impacts your application's security, availability, and performance. Understanding the capabilities and limitations of each SKU enables you to make informed decisions aligned with your application requirements and business objectives. The standard SKU, being the most feature-rich and secure option, should be the default choice for new implementations, while the gateway SKU serves specific high-performance scenarios. Backend pools represent a fundamental component of Azure Load Balancer, serving as the destination for distributed traffic. These pools contain the IP addresses of virtual network interface cards and ICs connected to the load balancer, effectively creating the foundation for scalable and reliable application delivery. Understanding backend pool. Configuration, SKU-based capabilities. Basic SKU configuration. The basic SKU provides essential backend pool functionality with specific limitations. Maximum pool capacity. 300 distinct backend pools, resource constraints, limited to single resource type combinations. Configuration options, restricted to either a single availability set or a single virtual machine scale set. Scaling limitations, basic horizontal scaling capabilities. Management complexity, simpler management but limited flexibility. Standard SKU configuration. The standard SKU offers enhanced flexibility and scaling capabilities. Maximum pool capacity, 1,000 distinct backend pools. Resource flexibility, support for mixed resource types. Virtual network scope. All resources must reside in a single virtual network. Scaling capabilities, advanced horizontal and vertical scaling options. Management features, comprehensive management and monitoring tools. Resource type, integration, available. Resource types. Backend pools can include various Azure compute resources, individual virtual machines, direct VM integration, individual IP management. Granular control, custom configurations, availability sets, high availability grouping. Fault domain distribution, update domain alignment, redundancy management virtual machine scale sets, automatic scaling, load distribution, instance management, performance optimization, implementation considerations, resource selection. When configuring backend pools, consider application requirements, scaling needs, availability requirements, performance expectations. Network configuration. Important networking aspects include virtual network planning, subnet design, IP addressing scheme network security groups, capacity planning. Key capacity factors, expected traffic volume growth projections, resource utilization, performance targets. Best practices, resource organization, group similar resources to. Maintain logical separation. 3. Consider maintenance needs. 4. Plan for scaling, monitoring, and management. Configure health probes. 2. Monitor performance metrics. Set up alerts for regular maintenance security. Implementation. 1. Network security groups. 2. Access controls. 3. Traffic monitoring. 4. Security updates. Implementation steps. Initial setup, SKU. Selection, evaluate requirements. Consider future needs. Review limitations. Assess cost resource. Preparation, create virtual machines. Configure availability sets. Set up scale sets, network configuration pool. Configuration, define pool parameters. Add resources, configure health probes. Set distribution rules, validation. Test connectivity. Verify distribution, monitor performance, check. Health status, operational management. Daily operations. Monitor health status, track performance metrics, manage resource allocation. Handle alerts, maintenance tasks. Update configurations. Scale resources. Optimize performance. Security patches, troubleshooting. Health probe issues, connectivity problems. Performance degradation. Configuration errors. Scaling. Considerations. Horizontal. Scaling, add, remove instances. Update pool configurations, adjust load distribution, monitor performance. Vertical. Scaling. Upgrade resource sizes, enhance capabilities, optimize performance, review costs, advance configurations. High availability, multiple availability zones, geographic distribution, failover planning, disaster recovery, performance optimization, load distribution rules, session persistence, health probe, tuning, network optimization, security enhancement, access controls, traffic filtering, monitoring compliance requirements. The proper configuration of backend pools is crucial for achieving optimal load balancer performance and reliability. Understanding the capabilities and limitations of different SKUs, along with best practices for resource organization and management, enables you to create robust and scalable load balancing solutions. Regular monitoring, maintenance, and optimization ensure continued effectiveness of your backend pool configurations. Health probes are a critical component of Azure Load Balancer, serving as the monitoring mechanism that ensures traffic is only directed to healthy backend instances. These probes continuously evaluate the health status of your application endpoints, enabling dynamic and automatic management of your service availability. Types of health probes. HTTP Health Probe. The HTTP probe provides application-level health monitoring through HTTP requests. Configuration details. Protocol. HTTP. Default interval. 15 seconds. Default. Timeout. 31 seconds. Success criteria. HTTP 200 response. Failure action. Remove from rotation implementation. Considerations. Define appropriate health check endpoints. Implement proper response handling. Configure meaningful health checks. Monitor response times. TCP health. Probe. TCP probes verify connectivity by establishing TCP sessions. Technical specifications. Protocol. TCP connection. Check port listener. Success criteria. Successful TCP session. Failure criteria. Connection refused. Cases. Basic connectivity verification. Port availability checking, protocol level monitoring, network layer health checks. Guest agent probe. While available, this option is not recommended for primary health monitoring. Limitations. Dependency on VM. Agent limited health verification, basic functionality only. Not suitable for production configuration. Parameters. Core settings. Each probe requires configuration of several key parameters. Port configuration. Specify backend. Port ensure port accessibility. Configure security rules. Monitor port status URI settings. HTTP. Define health check path, implement endpoint logic. Return appropriate responses. Handle request timeouts. Interval. Configuration. Set check frequency. Balance responsiveness. Consider resource impact. Optimize for performance. Unhealthy threshold. Define failure count. Set appropriate limits. Consider recovery time balance sensitivity. Implementation. Best practices health check. Design 1. Create dedicated endpoints. 2. Implement meaningful checks. Node 3. Include dependency verification. DO. Monitor performance impact. Response handling. 1. Quick response. Times taught. Proper status codes. 3. Error handling. 4. Timeout management monitoring and alerting. Track probe status. 2. Set up notifications. 3. Monitor trends. 4. Analyze patterns. Operational considerations. Maintenance tasks. regular endpoint verification, performance optimization, configuration updates, health check, refinement troubleshooting, probe failure investigation, connectivity issues, timeout problems, response errors, performance impact, resource utilization, network overhead application load response times, advanced configurations, custom health checks, application-specific logic, deep health verification, dependency checking, performance metrics, high availability, multiple probe points, redundant checks, failover scenarios, recovery procedures, security considerations, access control network, security authentication, encryption, implementation scenarios, web application, HTTP probe on port 80.443, health endpoint, 15-second interval, 2 failure threshold database service, TCP probe on DB port, connection verification, 10-second interval, 3 failure threshold microservices, multiple probe types, service-specific checks, custom intervals, varied thresholds, monitoring and management health metrics, probe success rate response, times failure patterns, recovery statistics, performance, analysis, resource impact, network utilization, latency patterns, optimization opportunities, maintenance procedures, regular validation, configuration review, performance tuning, security updates, recovery, handling automatic recovery, instance removal, health restoration, traffic resumption, performance monitoring, manual intervention, issue investigation, configuration, adjustment service, recovery, root cause analysis. Health probes are essential for maintaining service availability and ensuring optimal load balancer performance. Proper configuration and monitoring of health probes enable automatic handling of back-end instance health, providing reliable and efficient application delivery. Regular review and optimization of probe configurations ensure continued effectiveness of your load balancing solution. Azure Load Balancer rules define the intelligent traffic distribution patterns for your infrastructure, ensuring optimal resource utilization and application availability. These rules create mappings between front-end IP address and port combinations to back-end resources, establishing the foundation for effective load balancing, core components, and configuration. Before implementing load balancing rules, 3 essential components must be in place: front-end configuration, IP address and port; back-end pool, destination resources; health probe, monitoring mechanism. Rule configuration. Parameters. The configuration of load balancing rules involves several critical settings. Basic settings, IP version. Selection, choose between IPv4 or IPv6 based on your network requirements. Front-end configuration, specify the IP address and port that clients will connect to. Protocol selection, define TCP or UDP as the Transport Protocol Backend Pool Association. Link to the appropriate back-end resource pool. Port mapping, configure the destination port for back-end services distribution. Algorithm. Azure Load Balancer employs a sophisticated 5-tuple hash algorithm for traffic distribution, considering source IP address, source port destination, IP address destination, port protocol type. This hash-based approach ensures equal traffic distribution among available servers while maintaining session consistency within transport sessions. Session persistence options. The configuration of session persistence is crucial for many applications. Azure offers 3 modes. None, default. Requests distributed across all available instances. No session affinity maintained. Maximum distribution efficiency. Suitable for stateless applications. Client IP requests from same IP directed to same instance. Session state maintained based on source IP. Ideal for client-specific caching, suitable for simple web applications. Client IP and protocol. Combine source IP and protocol for persistence, higher granularity in session management. Enhanced session state maintenance perfect for complex applications. Practical applications. Session persistence becomes crucial in several scenarios. E-commerce applications. Shopping cart maintenance user session, tracking transaction consistency order, processing flows. Banking applications. Security session management. Transaction consistency user authentication state. Financial data processing enterprise applications. User workflow maintenance document processing states. Multi-step operations service consistency. Integration with NAT rules. Load balancing rules can work in conjunction with network address translation, NAT rules, enabling scenarios such as remote access RDP access to specific VMs SSH connectivity management interfaces, administrative functions service exposure, specific port mapping service isolation, controlled access security enhancement, implementation, best practices, planning phase, assess application requirements, determine session persistence needs plan port mappings, consider security implications. Configuration implement logical naming conventions, document rule configurations, verify health probe settings, test distribution patterns, monitoring, track rule effectiveness, monitor session distribution, analyze traffic patterns, evaluate performance metrics, maintenance, regular configuration, reviews, performance optimization, security updates, rule refinement, troubleshooting considerations. When implementing load balancing rules, watch for uneven traffic distribution session persistence issues, port conflicts, health probe failures, performance bottlenecks, configuration mismatches. By carefully considering these aspects and implementing appropriate load balancing rules, you can ensure optimal application performance and availability while maintaining necessary session states and traffic distribution patterns. Regular monitoring and maintenance of these rules ensure continued effectiveness of your load balancing solution. Let's examine each question and understand the correct answers along with detailed explanations. Question 1. What's the default distribution type for traffic through a load balancer? Correct answer. 5-tuple hash detailed explanation. Azure Load. Balancer uses a 5-tuple hash by default for distributing network traffic. This sophisticated hashing mechanism considers 5 key components. Source IP address. Client's originating IP address first component of the hash helps maintain consistency. Source port. Client's originating port, provides additional uniqueness, enhances distribution accuracy. Destination IP address, target service IP load balancer front-end service identifier. Destination, port.service, port number application, endpoint, protocol-specific routing. Protocol type, TCP or UDP transport protocol connection handling. Why this matters. Ensures even distribution, maintains session consistency, optimizes performance, provides predictable routing. Why other options are incorrect. Source IP affinity. This is a session persistence option. Not the default distribution method, requires explicit configuration. Limited use cases. 3-tuple hash. Not used in Azure Load Balancer, insufficient distribution factors. Less granular control, limited effectiveness. Question 2. Which configuration is required for an internal load balancer? Correct answer. Virtual machines must be in the same virtual network. Detailed explanation. Internal load balancers require all virtual machines to be in the same virtual network for several important reasons. Network isolation. Maintains security boundaries. Enables private communication. Controls traffic flow, ensures resource access. Private IP addressing. Internal address space. No public exposure, direct routing. Network efficiency, security benefits, controlled access. Network segregation. Protected resources, limited attack surface. Why other options are incorrect. Virtual machines must be publicly accessible. Contradicts internal LB purpose. Security risk not required, actually undesirable. Virtual machines must be in an availability set. Optional configuration, not mandatory for internal LBR, relates to high availability. Separate consideration. Implementation considerations. Network planning. Subnet design. IP allocation. Security groups. Route tables configuration requirements. Virtual network setup. Subnet configuration. Backend pool setup. Health probe definition best practices. Network segmentation. Security implementation. Performance optimization. Monitoring setup. These answers help clarify the fundamental concepts of Azure Load Balancer configuration and requirements. Understanding these aspects is crucial for implementing effective load balancing solutions that meet both technical and business requirements while maintaining security and performance standards. Let's dive into Azure Load Balancer rules, a critical component for distributing network traffic effectively across your cloud infrastructure. These rules form the backbone of how your applications handle incoming requests and maintain session persistence. The foundation of any load balancer configuration starts with three essential components. First, we have the front-end IP and port configuration, which serves as the public face of your application. This is where all client requests first arrive, and it's crucial to configure it correctly to ensure proper traffic handling. Second, the backend pool definition determines which resources will actually process these requests. These could be virtual machines, cloud services, or other resources. Third, health probe settings continuously monitor the status of your backend resources, ensuring that traffic is only directed to healthy instances. When it comes to configuration settings, we have several important options to consider. The IP version selection between IPv4 and IPv6 affects your application's accessibility and compliance with modern networking standards. Protocol selection between TCP and UDP determines how your traffic is handled at the transport layer. Port mapping allows you to define how front-end ports correspond to back-end services, enabling flexible architecture designs. One of the most powerful features is session persistence, which comes in three distinct types. The None option allows any virtual machine to handle incoming requests, providing maximum flexibility and equal distribution. The Client IP affinity ensures that requests from the same IP address are always handled by the same back-end instance, crucial for maintaining state in certain applications. The most specific option, IP plus protocol, maintains consistency based on both the client's IP address and the protocol used. The 5-tuple hash is a sophisticated mechanism that Azure Load Balancer uses to determine how to distribute traffic. It considers 5 key components: source IP, source port, destination IP, destination port, and protocol. This comprehensive approach ensures consistent and predictable traffic distribution while maintaining session persistence when required. Let's look at a practical example. E-commerce platforms heavily rely on session persistence to maintain shopping cart states. When a customer adds items to their cart, it's crucial that subsequent requests are directed to the same back-end server that holds their session information. This ensures a seamless shopping experience and prevents cart inconsistencies or data loss. Best practices for implementing load balancer rules include setting appropriate health probe intervals, recommended 15 seconds, implementing proper timeout values based on your application's requirements, carefully considering session persistence needs based on your application architecture, monitoring backend pool health status regularly, planning for scale by properly sizing your backend pool. Remember that load balancer rules are not just about distributing traffic, they're about creating a reliable, scalable, and efficient application infrastructure. The correct configuration of these rules can significantly impact your application's performance, availability, and user experience. When implementing health probes, consider these key factors: protocol selection, HTTP, TCP, based on your application type. proper probe intervals to balance responsiveness and overhead, appropriate health check endpoints that truly reflect your application's status, timeout settings that align with your application's response patterns. Security considerations shouldn't be overlooked. While load balancer rules primarily focus on traffic distribution, they play a crucial role in your overall security architecture. Properly configured rules can help protect your back-end resources from direct exposure and contribute to your defense in-depth strategy. Let's explore Azure Application Gateway's routing capabilities, which provides sophisticated traffic management for your web applications. These routing mechanisms offer flexible ways to direct incoming requests to appropriate back-end servers based on various criteria. Path-based routing stands as one of the primary routing methods, allowing you to direct traffic based on URL paths in the requests. Imagine running a multimedia platform where different types of content require different handling. With path-based routing, requests to videos can be automatically directed to servers optimized for video streaming, while images requests go to servers specialized in image processing. This specialization ensures optimal performance for each content type. Multi-site routing represents another powerful capability, enabling you to host multiple websites on a single application gateway instance. This approach is particularly valuable for organizations managing multiple web properties or running multi-tenant applications. For instance, you can configure your gateway to route requests for contoso.com to one set of back-end servers while directing Fabricom.com traffic to another pool. This separation maintains clear boundaries between different applications while efficiently utilizing gateway resources. Traffic redirection capabilities add another layer of flexibility to your routing configuration. A common implementation is automatically redirecting HTTP traffic to HTTPS, ensuring secure communication between clients and your applications. This feature proves invaluable for maintaining security standards without requiring changes to client applications or user behavior. HTTP header rewriting enables sophisticated request and response manipulation. You can modify URLs, query parameters, and headers based on specific conditions. This capability proves particularly useful when implementing A/B testing scenarios, maintaining backward compatibility, standardizing request formats across different client types, managing security headers efficiently. Custom error pages represent a significant enhancement to user experience. Instead of displaying generic error messages, you can present branded error pages that maintain your application's look and feel while providing helpful information to users. This customization helps maintain professional appearance even when errors occur. The real power of application gateway routing comes from combining these features. Consider these practical scenarios. Content delivery. Optimization. Use path-based routing to direct different content types. Implement header rewriting for Content Delivery Network (CDN). Integration. Configure custom error pages for service unavailability. Multi-tenant application. Hosting. Employ multi-site routing for tenant separation. Configure SSL termination for secure communication. Implement header rewriting for tenant identification. Security enhancement. Automatic HTTP to HTTPS. Redirection, SSL, TLS termination at the gateway. Header manipulation for security policy enforcement. Best practices for implementing application gateway routing include: always implement HTTPS redirection for secure communication. Use URL-based routing when content requires specific handling. Configure meaningful custom error pages. Implement proper health monitoring for back-end pools. Regularly review and update routing rules. Document routing configurations thoroughly. Common challenges and solutions. Performance optimization. Use path-based routing to direct traffic to optimize server pools. Implement caching where appropriate. Monitor routing performance metric security considerations. Enable SSL termination at the gateway implement proper, redirect rules, configure, appropriate security headers, maintenance and monitoring, regular review of routing rules, monitor back-end health status, track routing metrics and logs. Remember that effective routing configuration requires careful planning and understanding of your application's requirements. Regular monitoring and adjustment ensure optimal performance and user experience. Let's explore the essential components of Azure Application Gateway and understand how they work together to manage and secure your web application traffic. Each component plays a crucial role in ensuring efficient traffic flow and application availability. Starting at the entry point, we have the front-end IP address. This component serves as the gateway's public face, accepting all incoming client requests. You can configure it with either a public IP address, a private IP address, or both, though you're limited to one of each type. This flexibility allows you to maintain both internet-facing and internal-only applications through the same gateway. Before requests reach deeper into your application infrastructure, they can optionally pass through the Web Application Firewall, WAF. The WAF acts as your first line of defense, implementing OWASP Core Rule Set 3.0 to protect against common web vulnerabilities. It scrutinizes incoming traffic for various threats, including SQL injection attempts, cross-site scripting attacks, command injection, HTTP protocol violations, malicious bots, and crawlers. The next component in the chain is the listener, which comes in two flavors, basic and multi-site. Basic listeners focus on URL path-based routing, while multi-site listeners can also consider the host name in their routing decisions. Listeners handle crucial security aspects like TLS/SSL certificate management, ensuring secure communication between clients and your application gateway. Routing rules form the intelligence center of your application gateway. They create the essential binding between listeners and back-end pools, determining how to interpret and direct incoming requests. These rules encompass various settings: HTTP configuration details, SSL settings for back-end communication, session persistence options, connection management parameters, timeout configurations. Back-end pools represent the destination for your traffic, containing the web servers that actually process requests. These pools can include various resource types: Azure Virtual Machines, Virtual Machine Scale Sets, Azure App Services on-premises servers. Each pool utilizes load balancing to distribute traffic effectively across its resources. Health probes continuously monitor the availability of servers in your back-end pools. They operate by sending requests and evaluating responses. A response code between 200 and 3999 indicates a healthy server. The default probe timeout is 30 seconds. Custom probes can be configured for specific requirements. Let's examine how these components work together in a typical request flow. Client request phase. Request arrives at front end. IP/WAF examines requests for security threats. Listener accepts validated request. Processing phase. Routing rules analyze request details. Rules determine appropriate backend pool. Health probe information influences server selection backend. Communication. Request forwards to selected server. Server processes request and response returns through gateway to client. Best practices for component configuration include front-end IP configuration. Use private IP for internal applications. Implement proper DNS records for public IP. WAF implementation. Start in detection mode before blocking regular review of WAF logs. Custom rules for specific threats. Listener. Setup. Proper SSL certificate management. Appropriate protocol selection. Clear hostname configurations. Routing rules. Logical rule organization. Proper timeout settings. Efficient path-based routing backend. Pools. Appropriate pool size. Server capacity planning. Regular maintenance Windows health probes. Custom probe paths when needed. Appropriate timeout values. regular probe, interval adjustments. Understanding these components and their interaction is crucial for efficient traffic management, proper security implementation, optimal performance configuration, effective troubleshooting, scaling decisions. Let's explore the correct answers and understand the reasoning behind each one. Question 1. Request routing criteria. Correct answer: the host name, port, and path in the URL of the request. Explanation: Azure Application Gateway uses URL-based routing to direct traffic, specifically examining the host name for multi-site configurations, the port number specified in the request, the URL path. This routing method allows for sophisticated traffic management, such as directing different paths to specialized backend pools, supporting multiple websites on a single gateway, implementing path-based load balancing. The region location isn't a routing criterion, as routing decisions are made based on request characteristics, not server location. User authentication information might be used for other purposes, but isn't the primary routing criterion. Question 2. Load balancing strategy. Correct. Answer: requests are distributed to each available server in a backend pool in turn via a round-robin technique. Explanation: Application Gateway implements round-robin load balancing because it's simple and effective for most scenarios. It ensures fair distribution of requests. It doesn't require complex server monitoring. It works well with health probes. The other options are incorrect because Application Gateway doesn't monitor server load for distribution. It doesn't wait for server responses before routing decisions. The round-robin approach is built into the gateway's design. Question 3. Security implementation. Correct answer: install Azure Web Application Firewall, WAF. Explanation: WAF is the correct choice because it specifically protects against web application threats. Implements OASPA core rule set, protection guards against cross-site scripting, SQL injection, command injection, malicious bots and crawlers. Why the other options are incorrect. Internal load balancer focuses on traffic distribution, not security. Azure firewall, network level security, not application level protection. Best practices for implementation. WAF configuration. Start in detection mode, gradually enable blocking rules. Regular rule updates, monitor false positives load. Balancing, configure appropriate health probes. Set suitable timeout values. Monitor backend pool. Health routing. Implement clear URL patterns. Configure appropriate listeners. Regular route maintenance. These answers align with Azure's best practices for application security, traffic management, load balancing, high availability. Azure Virtual Networks represent the foundation of your cloud networking infrastructure. Let me walk you through the key concepts and components that make Azure networking both powerful and flexible. Starting with IP addressing, Azure uses private IP ranges that you're likely familiar with from on-premises networks. These include the 10.0.0.08, 172.16.0.0 CR12, and 192.168.0.016 ranges. When designing your Azure network, you have complete control over which private IP ranges to use. But here's a crucial point. You must avoid any overlap with your on-premises network IP ranges if you plan to connect them. Looking at our network diagram, let's explore the architecture from top to bottom. At the perimeter, we have the Azure Firewall, which acts as your centralized network security service. This cloud-native firewall provides crucial protection for your workloads and can scale automatically with your traffic demands. Within the virtual network, we implement network segmentation through subnets. Notice how we've separated our front-end and back-end resources into different subnets. This separation is a security best practice that allows you to implement distinct security rules for different types of resources. Front-end components, like web servers, typically need different security rules than back-end components, such as databases. Let's talk about CIDR notation, which is fundamental to network design in Azure. When you specify a network range like 192.168.0.024, the number after the slash indicates the subnet mask. Azure offers remarkable flexibility here. You can create subnets as small as 29, with 8 IP addresses, or as large as MOT2, with over 1 billion IP addresses. However, most production environments typically use ranges between 16 and 24, depending on their scaling needs. A key advantage of Azure networking is its built-in security features. Network security groups, or NSGs, act like virtual firewalls at the subnet and network interface levels. They contain security rules that allow or deny inbound and outbound traffic. These rules are stateful, meaning if you allow outbound traffic, the response traffic is automatically allowed back in. When planning your Azure network, consider these critical best practices. Always plan your IP address space carefully, especially if you'll need to connect to other networks later. Use network segmentation to isolate different types of resources. Implement defense in depth, using both NSGs and Azure Firewall. Consider your subnet sizes carefully. It's easier to start with larger subnets and subnet them further than to try to expand them later. Remember, Azure networking is highly flexible and can scale with your needs. You can start small and expand your network as your requirements grow. The key is to plan your initial architecture with future growth in mind. Let's go through each question and understand the correct answers and their explanations. Question 1. What are some of the typical components involved in a network design? Correct answer: B. A virtual network, subnet, firewall, and load balancer. This answer is correct because these components form the fundamental building blocks of a modern cloud network architecture. Virtual network, VNet, serves as your network boundary in the cloud. Subnets allow you to segment your network for better security and organization. Firewalls protect your resources from unauthorized access. Load balancers distribute traffic across multiple resources for better performance and reliability. While options A, dedicated leased line, and C, dedicated network security group, are networking components, they are individual elements rather than a comprehensive set of components needed for a complete network design. A leased line might be used for hybrid connectivity, and a network security group is part of the security architecture, but neither represents the full scope of typical network components. Question 2. Which of the following IP address ranges is routable over the Internet? Correct answer: B. 215.11.0.0 to 215.11.255.255. This is the correct answer because the 215.11.xx range is a public IP address range that can be routed over the Internet. All other options represent private IP ranges that are specifically reserved for internal network use. Let's examine why the other options are not routable over the Internet. 10.0.0.0 to 10.255.255.255, option A, is a private IP range, Class A. 172, 16.0.0 to 172.31.255.255, option C, is a private IP range, Class B, 192.168.00 to 192.168.255.255. Option D is a private IP range, Class C. These private IP ranges were established by RFC 1918 specifically for use in internal networks and are not routable over the Internet. This design helps conserve public IP addresses and provides organizations with predictable internal addressing schemes. Key learning points. A complete network design requires multiple components working together. Two public and private IP addresses serve different purposes. Private IP addresses are for internal network use only. Public IP addresses are required for Internet routing. Understanding the difference between public and private IP ranges is crucial for network design, security planning, troubleshooting connectivity issues, implementing hybrid cloud solutions. Today, let's delve into Azure's IP addressing system, which provides both public and private IP addressing capabilities. Understanding these concepts is crucial for designing robust cloud infrastructure. Let's start with public IP addresses. In Azure, public IPs come in two SKU types, basic and standard. The basic SKU offers flexibility with both dynamic and static allocation, while the standard SKU mandates static allocation for enhanced reliability. Think of basic SKU as your entry-level option. It's open by default, but recommended to be secured with network security groups. The standard SKU, on the other hand, is like having enterprise-grade security features built in. It's secure by default and requires explicit configuration to allow inbound traffic. Looking at our slide's left section, you'll notice the key use cases for public IPs. These addresses can be assigned to virtual machines when they need direct internet connectivity, load balancers for distributing internet traffic, VPN gateways for connecting to on-premises networks, and application gateways for web traffic management. The standard SKU includes some impressive features worth highlighting. It's zone redundant, meaning your resources maintain high availability across Azure's availability zones. The static allocation ensures your IP address remains consistent throughout the resource's lifecycle, particularly important for services that other systems need to connect to reliably. Moving to private IP addresses on the right side of our slide, we see the familiar private address ranges 10.00p08, 172.16.00 and 192.168.0. 0.16. These are your internal network addresses, invisible to the Internet. In Azure, you can allocate these addresses either dynamically through DHCP lease or statically through DHCP reservation. Think of dynamic allocation like getting a temporary parking spot that might change when you leave and return, while static allocation is like having your own designated parking space that's always reserved for you. One crucial aspect of Azure networking that often surprises newcomers is the subnet rules. Azure automatically reserves the first 3 IP addresses and the last IP address in each subnet. These addresses are used for internal Azure services and protocol conformance. It's like having dedicated lanes on a highway. They serve specific purposes and can't be used for regular traffic. At the bottom of our slide, we see the 3 main resource types that can receive IP addresses in Azure. 1. VM network interfaces. These are like network cards for your virtual machines. 2. Load balancers, which distribute traffic across multiple resources. TAL, application gateways, which manage web application traffic. A key best practice to remember is that when planning your IP addressing scheme, always think ahead. Consider future growth, potential connections to other networks, and your security requirements. It's much easier to plan for scale than to restructure your IP addressing later. Let's examine each question and understand the correct answers along with their detailed explanations. Question 1. Which of the following resources can you assign a public IP address to? Correct answer: A. A virtual machine. Here's why this is correct. Virtual machines can be assigned public IP addresses to enable direct communication with the Internet. This is commonly used for scenarios such as hosting web servers or providing remote access. You can assign either basic or standard SKU public IPs to VMs depending on your requirements, while the other options are incorrect. Azure Data Lake, option B, doesn't require a direct public IP assignment. It uses endpoints for access control and is secured through Azure Active Directory. Azure Key Vault, option C, is a managed service that uses private endpoints or service endpoints for secure access. It doesn't need and cannot be assigned a public IP directly key concepts. Public IP addresses in Azure are assignable to specific resource types. Virtual machines, load balancers, application gateways, VPN gateways. Managed services typically use different networking mechanisms for access. Question 2. What must a virtual machine have to communicate with the other resources in the same virtual network? Correct answer: C. Network interface. This is correct because a network interface, NIC, is the fundamental component that enables network connectivity for VMs. It acts as the bridge between the VM and the virtual network. Every VM must have at least one network interface to communicate with any other resource. Why the other options are incorrect. Load balancer, option A, is used for distributing incoming network traffic across multiple resources. It's optional and not required for basic network communication. Network security group, option B, is a security component that filters network traffic. While important for security, it's not required for basic network communication. Important points. 1. Network interface properties can be assigned both public and private IP addresses. Must be in the same region as the VM. Can have security rules applied through NSGs. 2. Network interface requirements. Must be connected to a subnet within a virtual network. Can have multiple IP configurations. Supports both IPv4 and IPv6 addresses. Understanding these components is crucial for designing Azure network architecture, troubleshooting connectivity issues, implementing secure network configurations, planning resource deployment. Let's explore virtual network peering, a fundamental feature in Azure networking that enables seamless communication between virtual networks. Think of peering as building a private highway between two cities. It provides direct, high-speed connectivity without going through public routes. Looking at our network diagram, you can see two virtual networks connected through peering. This connection allows resources in both networks to communicate as if they're in the same network, but with some important characteristics to keep in mind. First, let's understand the two types of peering. Regional peering. This connects virtual networks within the same Azure region. It's like connecting buildings in the same city, straightforward and with minimal latency. Global peering. This connects networks across different Azure regions. Think of it as connecting offices in different cities while maintaining private communication. A crucial concept to understand is reciprocal connections. When you set up peering, you need to establish the connection from both sides, like a two-way street. While the Azure portal handles this automatically, if you're using PowerShell or CLI, you'll need to configure both sides manually. Now let's talk about some key limitations and considerations. Non-transitivity. If network A is peered with B and B is peered with C, A cannot communicate with C directly. Each connection must be explicit, IP address spaces. Just like you can't have two buildings with the same street address, peered networks cannot have overlapping IP ranges. Cross-subscription support. You can peer networks across different subscriptions, which is particularly useful in enterprise scenarios. Gateway transit is a powerful feature that deserves special attention. Imagine it as a central station that everyone can use. One network, the hub, maintains the gateway connection to on-premises. Other networks, the spokes, can use this gateway through peering. This reduces costs and simplifies management. When should you choose virtual network peering? Here are the ideal scenarios. When you need direct private communication between Azure virtual networks for cross-region or cross-subscription resource access. When you want the lowest possible latency between networks. When you need simplified network architecture without additional gateways. However, peering might not be the best choice if you're using Azure Basic Load Balancers. They don't work across peered networks. You already have VPN or ExpressRoute connections that meet your needs. You need transitive connectivity across multiple networks. Best practices for implementation. Plan your IP address spaces carefully to avoid overlaps. Document your peering connections. Consider using hub-and-spoke topology for centralized management. Review network security group rules in both networks. Monitor peering state and traffic patterns. Let's explore the fundamental concepts of DNS and how Azure DNS implements this crucial Internet service. Think of DNS as the Internet's address book. It's what allows us to use memorable domain names instead of numerical IP addresses. Starting with the basics, DNS, or Domain Name System, is a foundational protocol of the Internet. When you type a website address like www.wideworldimports.com into your browser, DNS is what translates that human-friendly name into an IP address that computers can understand and route traffic to. The DNS resolution process works in three main steps. First, it checks the local cache. Think of this as your phone's recent calls list. If not found locally, it queries other DNS servers, like asking different phone operators. Once found, it updates the local cache and resolves the request, saving the number for future use. DNS servers have two primary functions. Cache management, maintaining a local directory of recent lookups. Domain resolution, managing authoritative records for domains they control. Let's talk about IP addresses. There are two standards, IPv4, the classic format, 127, 4 groups of numbers, 00255. Currently the most widely used limited address space becoming scarce IPv6, the newest standard, FE80, 11A1 AC15, E9GF, 884, EDB0, DDDE, FEA3. 8 groups of hexadecimal numbers, vastly larger address space designed for future growth. DNS settings come from different sources depending on your connection. On-premises networks use local server settings. External connections, like hotels or cafes, use ISP settings. Azure DNS brings several advantages. Global distribution uses Microsoft's worldwide infrastructure, provides fast resolution worldwide. High availability, built-in redundancy, automatic failover, integrated management, works seamlessly with other Azure services. Single management interface, dual IP support, handles both IPv4 and IPv6. Future-proof design, common implementation scenarios, corporate websites, public DNS records for external access, internal DNS for private resources, hybrid environments, integration with on-premises, DNS seamless name resolution across environments, global applications, distributed DNS resolution, geographic routing capabilities. Best practices. Regular cache maintenance proper. TTL, time to live. Settings, monitoring and logging. Backup DNS server security considerations. Let's explore DNS records and how they're implemented in Azure DNS. Think of DNS records as entries in a phone directory, each serving a specific purpose in routing Internet traffic. Let's start with the 4 most common record types. Records, address records. The most fundamental DNS record maps a domain name directly to an IPv4 address. Example, www.company.com, 192.168.1.1, like a direct phone number in a directory. CNAME records, canonical name, creates aliases for your domain points, one domain name to another. Example, blog.company.com, www.company.com, like having multiple phone numbers ring to the same line. MX records, mail exchange, directs email to the correct mail servers, can have multiple records with priorities. Essential for email routing. Think of it as the mail sorting center for your domain. TXT records. Text. Stores. Text information about your domain, commonly used for domain verification. Security policies and SPF records, like adding notes to your phone directory entry. Record sets are a powerful feature. allow multiple values for the same record type. Example shown in our slide. One domain pointing to two IP addresses, useful for load balancing and redundancy. All records in a set share the same TTL, time to live. Important limitations. SOA and CNAME records can't be part of record sets. Each record set must have consistent properties. TTL affects how quickly changes propagate. Azure DNS automatically creates two critical records. SOA, start of authority, contains authoritative information about your domain, includes administrator contact info, specifies refresh intervals and timeout values. NS, name server, points to the authoritative name servers for your domain, essential for DNS hierarchy. Automatically managed by Azure. Additional record types serve specific purposes. CAA controls which certificate authorities can issue. SSL certificates. PF helps prevent email spoofing. SRV defines location of specific services. Wildcards match multiple subdomains. Best practices for DNS record management. Plan your TTL values carefully. Lower values, not cache, faster updates but more DNS queries. Higher values, now some better caching but slower changes. Document your record sets. Keep track of what each record does. Note dependencies between records. Maintain change history. Regular maintenance. Review and clean up unused records. Verify record accuracy update. Security-related records. Security considerations. Use TXT records for domain verification. Implement SPF records for email security. Consider DNSSEC where needed. Let's explore the comprehensive feature set of Azure DNS and understand why it's a powerful choice for managing your domain names in the cloud. Think of Azure DNS as your organization's digital address book, but with enterprise-grade security and management capabilities. Core functionality: Azure DNS is Microsoft's globally distributed name server infrastructure. It's like having a worldwide network of telephone operators, each able to direct calls, or in this case traffic, to the right destination. However, it's important to note that Azure DNS doesn't handle domain registration. You'll still need a third-party registrar for that. Let's break down the key features. Security features: role-based access control, RBAC. Think of it as a sophisticated keycard system, granular control over who can access what. Perfect for large teams with different responsibilities. Activity logging, like having security cameras for your DNS. Tracks all changes and accesses. Essential for troubleshooting and compliance. Resource locking. Prevents accidental changes or deletions. Additional layer of protection for critical resources. Management capabilities. Multiple management interfaces. Azure Portal for visual management. PowerShell for scripting. CLI for command line control. REST API for custom integration. SDKs for application development. Private DNS zones. This is like having your own internal phone directory. Custom domain names. Use your preferred naming convention. No need to use Azure-provided names. VNet integration. Seamless connection with virtual networks. Automatic name resolution. Split horizon DNS. Same domain. Different responses based on where the request comes from. Alias records. Think of these as smart forwarding rules. Can point to Azure resources directly. Automatically updates if the underlying resource changes. Supports public IP addresses. Traffic Manager profiles. CDN endpoints. Key limitations to remember. No domain. Registration. Must use third-party registrars. Azure DNS only handles hosting and management. No DNSSX support. Use third-party providers if needed. Important for high security requirements. Integration benefits. Single authentication. Use existing Azure credentials. No separate login needed. Unified billing. Part of your Azure bill. Simplified cost management. Resource Manager integration. Consistent with other Azure services, use familiar tools and processes. Best practices for implementation. Plan your DNS hierarchy. Consider public and private zones plan for growth. Implement proper security. Use RBAC effectively. Enable activity logging. Set up resource locks. Monitor and maintain. Regular audits, performance monitoring. Keep documentation updated. Let's examine each question and understand the correct answers along with detailed explanations. Question 1. What does Azure DNS allow you to do? Correct answer. C. Manage and host your registered domain and records. This is correct because Azure DNS provides hosting and management services for your DNS domains. It allows you to manage DNS records using Azure's infrastructure. It integrates with other Azure services for comprehensive domain management. Why other options are incorrect? Option A, manage security and access to your website, is incomplete. While Azure DNS has security features, it's specifically for DNS management, not overall website security. Option B, register new domain names, is incorrect. Azure DNS explicitly doesn't provide domain registration services. You must use a third-party domain registrar. Question 2. What security features does Azure DNS provide? Correct answer. A. Role-based access control, activity logs, and resource locking. This is correct because these are the three primary security features of Azure DNS. Role-based access control, RBAC, provides fine-grained control over user access, allows management of permissions at various levels. Activity logs, track changes to resources, help identify issues and their sources, provide audit trail capabilities. Resource locking, prevents accidental modifications, adds an extra layer of protection, controls access to critical resources. Why other options are incorrect? Options B and C include features that aren't specific to Azure DNS's security features. Azure Threat Detection is a separate service. Azure Infrastructure Security is a broader concept. Question 3. What type of DNS record should you create to map one or more IP addresses against a single domain? Correct answer. B. A or AIA. This is correct because A records map domain names to IPv4 addresses. IEA records map domain names to IPv6 addresses. Both can be used in record sets to map multiple IP addresses to a single domain. Why other options are incorrect? Name, option A, creates an alias from one domain to another, not to IP addresses. So A, option C, is the start of authority record that contains administrative information about the DNS zone. Key learning points: Azure DNS capabilities, hosting and management of DNS domains, integration with Azure infrastructure, no domain registration functionality. Security features, comprehensive set of security controls. Integration with Azure Security Framework, multiple layers of protection. DNS record types, different records serve different purposes. Choose the appropriate record type for your needs. Understanding record sets and their limitations. Let's walk through the process of configuring Azure DNS to host your domain. Think of this as moving your domain's address book to Azure's globally distributed infrastructure. I'll break down each step and explain what's happening. Step 1. Create DNS zone. This is like establishing your domain's new home in Azure. Choose your subscription. Think of this as your billing account. Select Create Resource Group. This helps organize related resources. Enter domain name, your actual domain, e.g. wideworldimports.com. Location, where your resource group resides. Key point: you're not registering a new domain here. You're creating a space to manage an existing one. Step 2. Get name servers. After creating the zone, Azure provides 4 name servers. These are like the address book keepers. You'll need all 4 for redundancy. They'll be in format ns1xx.azuredns.com best practice. Document all 4 name server addresses for reference. Step 3. Update domain. Registrar. This is the critical step where you relocate your domain. Log into your domain registrar's portal. Find the NS record settings. Replace existing name servers with Azure's. Must use all 4 Azure name servers. This process is called domain delegation. Important: never delete existing NS records before adding new ones. Step 4. Verify delegation. Now we confirm the move was successful. Use ENS lookup to check SOA record command. ENS lookup, type soadomain.com. Allow at least 10 minutes for propagation. May take longer in some cases. Troubleshooting tip: if verification fails, wait 15 minutes and try again before making changes. Step 5. Configure custom DNS settings. Now you can set up specific records. A record's name, subdomain or host, name type, A for IPv4 addresses, TTL, how long to cache, in seconds, IP address, the destination IP example, configuration, copy name, web server, one type, A, TTL, 3600, 1 hour, IP, 20, 40, 60, 80 best practices. Planning, document all your DNS requirements. Plan your TTL values carefully. Consider future expansion implementation. Start with longer TTL values, 3600 plus. Test with lower priority services. First, keep original DNS settings documented. Verification. Test from multiple locations. Verify all critical services. Monitor for any issues. Common pitfalls to avoid: not using all 4 name servers, setting TTL too low initially, not waiting for propagation, forgetting to verify delegation. Let's explore 2 important aspects of Azure DNS: CNAME records and private DNS zones. Each serves a distinct purpose in your DNS infrastructure. First, let's understand CNAME records. Think of a CNAME as a nickname or alias for another domain name. It's like having multiple phone numbers that all ring the same phone. CNAME record components. Name the alias you want to create, e.g. www. TTL. How long to cache the record, e.g. 600 seconds. Target. The actual domain name it points to. Common CNAME use cases. Multiple domain access. www.domain.com. Domain.com. blog.domain.com. Domain.com both resolve to the same IP address. Azure Services, Azure Functions CDN Endpoints App, Services Load Balancers Resolution Process, Client Requests, www.domain.com DNS finds CNAME. Pointing to domain.com DNS looks up. A record for domain.com. Returns final IP address. Now let's dive into private DNS zones. Think of these as your internal company phone directory, not visible to the outside world. Step 1. Create private zone. Choose resource group, name the zone, e.g. private.wideworldimports.com. No domain registrar needed, completely internal to Azure. Step 2. Identify virtual networks. List all VNets needing name resolution. Consider future network additions. Document network dependencies. Step 3. Link virtual networks. Create virtual network. Links. Each VNet needs its own link. Links enable name resolution. Key features of private DNS zones. Internal only. Not visible on the Internet. Secure by design. Perfect for internal resources. Automatic registration. VMs can auto-register, reduces manual configuration, keeps DNS records current cross VNet. Resolution. Resources can resolve across VNet, supports hub-and-spoke designs, enables complex networking scenarios. Best practices. CNAME. Configuration. Use meaningful aliases. Set appropriate TTL values. Document all aliases. Regular validation. Private zone management. Plan naming convention. Document-linked networks, regular access, review, monitor, auto-registration. Common implementation scenarios. Development environments dev-interno.com test. Interno.com staging.interno. Com. Service infrastructure. dbinterno.com cache. Internal.com apsc.interno. Com. Let's explore Azure DNS alias records, a powerful feature that solves several common DNS challenges, particularly at the apex and root of your domain. First, let's understand what an apex domain is. It's the root of your domain, e.g., domain.com. Represented by IRMs in DNS records, can't use traditional CNAME at this level, requires special handling for modern cloud architectures. Alias records provide that special handling. Think of them as smart DNS records that know about Azure Resources update automatically, prevent common DNS problems, key components. Supported Azure Resources. Traffic Manager profiles CDN endpoints public IP addresses. Front door profiles supported record types. A records, IPv4. A records, IPv6. CNAME records for non-apex use. The benefits: prevents dangling records. Traditional DNS challenge. IP changes leave outdated records. Alias solution. Automatically tracks resource changes, like having a self-updating address book. Automatic IP updates. No manual intervention needed, zero downtime during changes. Maintains continuous service zone apex load balancing. Previously challenging with traditional DNS, now possible through alias records, enables high availability at domain root direct CDN integration. Clean CDN implementation. No workarounds needed, better performance. Common implementation scenarios. Load balancer. Setup copydomain.com. Azure Load Balancer. Automatic IP tracking. High availability. Zero downtime updates CDN. Implementation. Copydomain.com. Azure CDN. Direct endpoint connection. Global content delivery. Automatic optimization. Traffic management. Copydomain.com. Traffic manager. Global routing. Load distribution. Failover support best practices. Planning. Document resource relationships. Plan for scalability. Consider future growth implementation. Test in non-production. First monitor during transitions. Validate automatic updates, maintenance. Regular monitoring resource health checks. Documentation updates. Common pitfalls to avoid. Mixing with traditional records. Forgetting to monitor target resources. Not planning for scale. Let's explore Azure Virtual Network Routing, which controls how network traffic is directed within your Azure infrastructure. Think of it as a sophisticated traffic management system for your cloud resources. System routes. Azure automatically creates system routes for every subnet. These are like the default traffic rules of your virtual network. Address prefixes 0.0.0.0/0. Routes to Internet 10.0.0.08. Private network space 172.16.00012. Private network space 192.68.0016. Private network space 164.0.010. Shared address space. Next, hop types. Think of these as different paths your traffic can take. Virtual network. Direct communication within the VNet like internal building corridors internet. External communication default route for unknown destinations. None traffic is dropped. Like a dead-end additional system routes. Azure creates extra routes when you enable certain features. VNet peering connects different virtual networks like building bridges between networks. Service chaining routes through network virtual appliances like adding security checkpoints. Virtual network gateway connects to on-premises like creating secure tunnels, service endpoints. Direct connection to Azure services like private access roads, key routing concepts. Default behavior, automatic subnet to subnet communication, built-in internet access. Private network isolation, custom routes, override system routes, control traffic flow. Implement security requirements, best practices. Planning, document routing requirements. Consider security implications, plan for scale implementation. Start with system routes. Add custom routes as needed, test thoroughly. Maintenance, regular route table review. Monitor traffic patterns, update documentation. Common scenarios. Force tunneling. 0.0.0.000. VPN gateway. Route all internet traffic through on-premises. Enhanced security. Network virtual appliance. 10.0.0.016. NVA. Traffic inspection. Advanced filtering. Service isolation. Subnet routes. None. Restrict unwanted traffic. Enhance security. Common pitfalls to avoid. Overlapping routes. Improper route priorities. Incomplete traffic flow testing. Let's explore virtual network peering, service chaining, and custom routes in Azure. Think of this as building and controlling the highways between your cloud networks. Virtual network peering. Think of peering as creating a direct highway between two cities. Enables direct VM to VM communication, works across regions, creates automatic system routes. Low latency, high bandwidth connection service chaining. This is like adding checkpoints along your highway. Override, default routes, control traffic, flow implement, security measures, force traffic through specific paths. Network virtual appliances, NVAs, like security checkpoints, traffic inspection. Filtering capabilities, load balancing, custom routes. Types. Let's break down the available next hop types. Virtual appliance. Points to NVA's IP address. Requires IP forwarding. Can use internal load balancer. Example. Firewall appliance virtual network. Gateway. Connects to VPN gateway hybrid connectivity. Cross-premises routing. Example. Site-to-site VPN virtual network. Override system routes. Internal traffic control custom network paths. Example. For specific subnet routing. Internet. External routing public endpoints cloud services. Example. Force internet egress point. None. Drop traffic block communication security isolation. Example. Block subnet access. Implementation scenarios. Security. Inspection. Subnet A. NVA. Subnet B. Traffic inspection. Threat detection. Policy enforcement hub and spoke. Spoke VNets. Hub NVA. Internet. Centralized security, shared services, cost optimization, region connection. Region A, NVA, Region B, cross-region security. Traffic control. Performance monitoring. Best practices. Planning. Document traffic flows. Consider scalability plan for redundancy. Implementation. Test thoroughly. Monitor performance, implement gradually. Maintenance. Regular route reviews update. Documentation monitor. NVA health common pitfalls to avoid. Asymmetric routing, incomplete route tables. Missing health probes, improper NVA sizing. Let's explore Azure's route selection process, service tags, and BGP integration. Think of this as understanding how Azure makes traffic routing decisions and simplifies network management. Service tags. Think of service tags as smart address groups managed by Azure. Auto-updated IP ranges, always current. Reduced maintenance benefits, simplified management. Fewer routes to maintain, automatic updates. Regional specificity route selection process. Azure uses a sophisticated process to determine the best path. Longest prefix match. Example scenario. Target IP 10.0.0.2 Route 1. 10.00.0 16. 65,536 addresses. Route 2, 10.0.0.0.24, 256 addresses. Winner 10.0.0.0.24, more specific. Priority. Order, user-defined routes, highest. BGP routes, middle system routes, lowest. Border Gateway Protocol, BGP. Think of BGP as the postal service of the Internet. Key features: standard routing protocol, dynamic path selection, automatic failover. Path redundancy, common use cases. Express route, direct connection to Azure, high bandwidth. Low latency site-to-site VPN, over Internet, encrypted connection, cost-effective. Implementation, best practices. Service tags, use. Instead of explicit IPs, document usage. Regular validation, monitor updates. Route, selection. Plan prefix lengths carefully. Consider priority order document decisions, test failover BGP. Configuration, plan as numbers. Configure redundancy, monitor routes, regular health checks. Common scenarios, hybrid connectivity. On-premises, Azure, BGP route exchange. Dynamic updates, automatic failover. Multi-region, Region A, Region B. Service tag routing. Regional preferences, load balancing. Common pitfalls to avoid. Overlapping routes, incorrect prefix lengths, missing failover paths. Incomplete BGP configuration. Let's examine each question and understand the correct answers along with detailed explanations. Question 1. Why would you use a custom route in a virtual network? Correct. Answer. C. To control the flow of traffic within your Azure virtual network. This is correct because custom routes, user-defined routes, allow you to override Azure's default system routes. They provide granular control over network traffic flow. You can direct traffic through network virtual appliances or security devices. They enable implementation of specific security and routing requirements, while other options are incorrect. Option A, load balancing. Load balancing is handled by Azure Load Balancer, not custom routes. Option B, RDP SSH connections. These are handled by network security groups and network interfaces. Option D, connect to other VNets. This is achieved through VNet peering or VPN gateways. Key concepts. Custom routes enable traffic control through network virtual appliances. Security implementation, custom network topology, service chaining. Question 2. Why might you use virtual network peering? Correct answer. A. To connect virtual networks together in the same region or across regions. This is correct because VNet peering enables direct, private connectivity between virtual networks. It works both within the same region and across different regions, provides low latency, high bandwidth connection, allows resources to communicate as if they're in the same network. Why other options are incorrect? Option B, public IP assignment. Public IPs are managed independently of peering. Option C, load balancer control. Load balancers operate within their own VNet. Option D, custom reports. Reporting is an administrative function, not a networking feature. Important aspects of VNet. Peering, key features. Private communication cross-region support. Low latency high. Bandwidth common use cases. Resource sharing application. Segmentation. Hub and spoke networks cross-region applications. Best practices for custom routes. Document all custom routes. Consider impact on existing traffic plan for scalability. Regular route table reviews. For VNet peering, plan IP address spaces carefully. Consider security implications. Monitor peering, status document peering relationships. Welcome to our deep dive into Network Virtual Appliances, or NVAs, a cornerstone of modern cloud network security architecture. Today, We'll explore how these versatile tools can transform your Azure network security posture and optimize your cloud infrastructure performance. Let's begin with understanding what makes NVAs such powerful tools in our cloud security arsenal. At their core, NVAs are specialized virtual machines that combine multiple security and network optimization functions into a single, manageable package. Think of them as your network's Swiss Army knife, capable of handling everything from basic packet filtering to sophisticated application-level security controls. The security capabilities of NVAs are truly comprehensive. Starting with advanced firewall protection, these appliances can perform deep packet inspection, analyzing network traffic at both network and application layers. This means they can identify and block malicious traffic patterns, prevent unauthorized access, and protect your resources from various cyber threats. The built-in VPN gateway services enable secure communication channels between your cloud resources and external networks, ensuring data privacy and integrity. On the performance optimization front, NVAs really shine through their WAN acceleration capabilities. They can significantly improve network performance by optimizing traffic flow, reducing latency, and implementing efficient load balancing strategies. Quality of service (QoS) management ensures that critical applications receive the network resources they need, while traffic routing capabilities help create efficient paths for data flow across your network. One of the most powerful features of NVAs is their support for microsegmentation. This advanced security approach allows you to create isolated network segments, each with its own security policies and controls. By implementing microsegmentation, you can contain potential security breaches and prevent lateral movement of threats within your network. This is particularly crucial in today's zero-trust security environments. When it comes to deployment, flexibility is key. You can choose from various trusted providers in the Azure marketplace, including industry leaders like Cisco, Checkpoint, Barracuda, and Sophos. Each vendor brings their unique strengths and specialized features to the table. For instance, Cisco's offerings might appeal to organizations already invested in Cisco infrastructure, while Checkpoint solutions might be preferred for their advanced threat prevention capabilities. Speaking of deployment models, it's crucial to understand the importance of high availability in NVA implementations. For production workloads, always deploy NVAs in high availability pairs. This ensures continuous operation even if one appliance fails. Virtual machine scale sets can be utilized for environments requiring elastic scaling capabilities. Let's touch on some best practices that can make or break your NVA implementation. First and foremost, proper monitoring and alerting are essential. You need to know how your NVAs are performing and be immediately notified of any issues. Regular security updates and patches are equally crucial. An outdated NVA can become a vulnerability rather than a security asset. Integration with Azure native services is another area where NVAs prove their worth. They can work seamlessly with Azure Security Center, Azure Monitor, and other native services to provide a comprehensive security and monitoring solution. This integration enables centralized management and unified security policies across your entire Azure environment. When implementing NVAs, consider the network traffic patterns in your organization. The ability to inspect traffic at layers 4 through 7 of the OSI model means you can create very granular and specific security policies. For example, you can control not just which ports and protocols are allowed, but also which specific applications can communicate, and under what circumstances. Looking ahead, NVAs continue to evolve with new capabilities being added regularly. Features like AI-powered threat detection, automated response capabilities, and enhanced integration with cloud-native security. Tools are becoming increasingly common. Staying informed about these developments can help you make the most of your NVA investment. Remember, successful NVA implementation requires careful planning and ongoing management. It's not just about deploying the appliance, it's about creating a comprehensive security strategy that leverages all the capabilities these powerful tools offer. Let's break down these questions and understand the correct answers in detail. Question 1. The main benefit of network virtual appliances correct? Answer: C. To control incoming traffic from the perimeter network and allow only traffic that meets security requirements to pass through. This answer captures the primary purpose of an NVA. Let's understand why this is the most accurate choice. The key function of an NVA is to act as a security control point between different network segments. While it's true that NVAs can control outbound access, option A, load balance traffic, option B, and manage access control, option D, their primary benefit lies in their ability to inspect and control incoming traffic based on security requirements. Think of an NVA as a sophisticated security guard at the entrance of a secure facility. It doesn't just check IDs, basic access control, but also inspects all items being brought in, deep packet inspection. Enforces specific security protocols, security policies. Makes sure only authorized materials enter specific areas, traffic segmentation. Maintains detailed logs of all activities, security monitoring. Question 2. Deploying a network virtual appliance. Correct answer: A. Configure a Windows VM with IP forwarding after updating routing tables, user-defined routes, and subnets, or use a partner image from Azure Marketplace. This answer is correct because it outlines two valid deployment approaches. Let's analyze why this is the most complete and accurate answer. The DIY approach, first part of the answer. Configure a Windows VM enable IP forwarding update routing tables. Configure user-defined routes. Set up appropriate subnets. This method provides full control over the configuration, but requires more expertise and management overhead. The marketplace approach, second part. Use pre-configured partner images benefit from vendor support and updates. Get optimized configurations out of the box. This is often the preferred method for production environments. Why the other options are incomplete or incorrect. Option B, Linux VM deployment, is incomplete because it doesn't mention necessary networking configurations. Simply assigning a public IP isn't enough for NVA functionality. It lacks security considerations. Option C, Windows 2016 Server with Application Gateway, is incorrect because Application Gateway serves a different purpose, Layer 7 load balancing. It doesn't provide the security features required for an NVA. The configuration described wouldn't enable proper traffic inspection. Option D, downloading from Marketplace, is partially correct but oversimplified. It doesn't mention necessary configuration steps. Downloading isn't the correct term for deploying from Marketplace. It oversimplifies the network configuration requirements' key implementation considerations. When implementing either deployment method, remember to plan your network topology carefully. Let's dive into Azure Load Balancer, a critical service for building scalable and resilient applications in the cloud. I'll walk you through its key features, capabilities, and implementation considerations that make it an essential component of robust Azure architectures. At its core, Azure Load Balancer serves as an intelligent traffic distributor. Think of it as a sophisticated traffic controller at a busy intersection, ensuring that vehicles, in our case user requests, flow smoothly and efficiently to their destinations. But what makes it particularly powerful is its implementation methodology. Let's start with the hash-based distribution algorithm, which is the brain behind the load balancer's decision-making process. It uses 5 key components to make routing decisions. The source IP and port tell us where the request is coming from. Imagine this as the starting point on a map. The destination IP and port indicate where the request needs to go. Think of this as the destination. The protocol type, TCP or UDP, specifies how the communication should happen, like choosing between a highway or local road. This hash-based approach ensures consistent and predictable routing, which is crucial for maintaining session persistence when needed. The beauty of this system is that it's both sophisticated and efficient, capable of handling millions of concurrent flows without introducing significant latency. Speaking of performance, the load balancer's capabilities are quite impressive. It supports both inbound and outbound scenarios, meaning it can handle traffic flowing in both directions. The low latency and high throughput characteristics make it suitable for even the most demanding applications. Whether you're building a small departmental application or a large-scale enterprise system, the load balancer can scale to meet your needs. Now let's talk about availability options, which are crucial for maintaining service reliability. Azure offers two primary configurations. Availability sets provide 99.95% SLA and protect against hardware failures within data centers. This is like having backup generators in a building. If one fails, another takes over seamlessly. Availability zones offer an even higher 99.99% SLA and protect against entire data center failures. This is more like having your backup systems in different buildings across the city. Even if one location goes down completely, your service continues running. One of the most interesting aspects of Azure Load Balancer is that it's not a physical instance. Instead, it's implemented through configuration objects that tell Azure's infrastructure how to handle your traffic. This abstraction provides several benefits. Simplified management. You focus on defining your requirements rather than managing infrastructure. Automatic scaling. The platform handles capacity adjustments. Cost efficiency. You pay for what you use rather than maintaining dedicated instances. In practical implementation, the load balancer can automatically reroute traffic when it detects failures. For example, if one of your virtual machines becomes unresponsive, the load balancer will stop sending traffic to it and distribute requests among the remaining healthy instances. This happens automatically without any manual intervention required. Let's consider a real-world scenario. Imagine you're running a healthcare portal that handles appointment bookings. During peak hours, you might see thousands of concurrent users trying to schedule appointments. The load balancer ensures that requests are distributed evenly across your virtual machines. If any server fails, users are automatically redirected to working servers. The system maintains responsiveness even under heavy load. Users experience consistent performance regardless of their location. For optimal implementation, consider these best practices. Always use health probes to monitor your services. Implement proper monitoring and alerting. Consider using multiple load balancers for different types of traffic. Plan your capacity based on peak load plus a safety margin. Let's explore Azure's availability options and load balancer types, which are fundamental to building reliable cloud architectures. I'll guide you through the key concepts and help you understand how to make the best choices for your specific needs. Let's start with availability options. Azure provides two primary mechanisms for ensuring your applications remain available: availability sets and availability zones. Availability sets are like spreading your eggs across multiple baskets within the same room. When you place virtual machines in an availability set, Azure automatically distributes them across different physical infrastructure components. This distribution happens across multiple physical servers, different compute racks, separate storage units, independent network switches. This arrangement ensures that if there's a hardware failure or maintenance event, not all of your virtual machines are affected simultaneously. Think of it as having backup systems ready to take over instantly if one system fails. Availability zones take this concept to the next level. Instead of different racks in the same data center, we're talking about completely separate data centers within the same region. Each zone has its own independent power supply, separate cooling systems, distinct networking infrastructure. This setup provides protection against larger-scale failures. If an entire data center experiences issues due to power outages, natural disasters, etc., your applications continue running in other zones. However, it's crucial to note that availability zones aren't available in all Azure regions, and not all virtual machine sizes are supported. Always verify zone availability for your specific region and workload requirements. Now let's discuss load balancer options. Azure offers two product tiers, Basic and Standard, each with distinct capabilities and use cases. The Basic Load Balancer provides essential features: port forwarding for traffic distribution, automatic reconfiguration when resources change, basic health monitoring through probes, outbound connectivity through SNAT basic diagnostics through log analytics. However, it has limitations. You can only use it with a single availability set or scale set. The Standard Load Balancer includes all basic features and adds several premium capabilities. HTTPS health probes for more secure monitoring, support for availability zones, enhanced diagnostics through Azure Monitor High, availability ports for simplified configuration, outbound rules for better control, a guaranteed 99.999% SLA when using two or more virtual machines. When it comes to traffic direction, Azure offers two types of load balancers. External load balancers are your frontline traffic managers. They handle internet-facing traffic distribution. Client requests from browsers and mobile apps, public-facing application load balancing. Let's dive deep into these questions and understand the correct answers and their implications for Azure Load Balancer configuration. Question 1. Default distribution type correct. Answer: B. 5-tuple hash. This is a fundamental concept in Azure Load Balancer's traffic distribution mechanism. Let's break down why this is the correct answer and what it means in practice. The 5-tuple hash consists of source IP, where the request originates from, source port, the specific port on the client-side destination, IP, the target service IP, destination port, the target service port protocol, type TCP or UDP. Why this matters: provides consistent routing for established connections, ensures balanced distribution of traffic, maintains session affinity when needed. Why other options are incorrect. Source IP affinity, option A, is a different load balancing method that routes based only on source IP, which can lead to uneven distribution. 3-tuple hash, option C, would be insufficient as it wouldn't consider all necessary components for optimal distribution. Real-world application. Imagine a healthcare portal where multiple patients are accessing their records simultaneously. The 5-tuple hash ensures that each user's session remains stable. Traffic is distributed evenly across servers. Connection persistence is maintained when necessary. Question 2. Availability set benefits. Correct answer: B. It allows virtual machines to be available across physical server failures. This answer captures the primary purpose and benefit of availability sets in Azure. Let's explore why this is correct and what it means for your infrastructure. Key aspects of availability sets. Physical distribution. VMs are spread across different physical hardware, separate power supplies and network switches, independent storage units. Protection level. Guards against hardware failures. Protects from maintenance events. Ensures continuous service availability. Why other options are incorrect. Option A. Available across data center failures. This is actually a benefit of availability zones, not availability sets. Availability sets operate within a single data center. For cross-data center redundancy, you need availability zones, option C, grouped into logical categories. While availability sets do involve grouping VMs, this is not their main benefit. The grouping is a means to an end, not the primary advantage. The real value lies in the physical distribution of resources. Practical implementation. Consider a healthcare application with 3 web servers. Without an availability set, all servers might be on the same physical hardware. Single point of failure risk maintenance could affect all servers simultaneously. With an availability set, servers distributed across different physical hardware. Hardware failure affects only one server. Planned maintenance can be staged. Continuous service availability. Let's explore Azure Load Balancer's distribution modes and how to configure them effectively. This knowledge is crucial for ensuring your applications maintain proper session management and optimal performance. Let's start with the fundamental concepts of load balancer distribution modes. Azure Load Balancer offers two primary distribution modes, each designed for specific use cases and requirements. First, let's examine the default mode, the 5-tuple hash. This distribution method uses 5 key components to determine how traffic is routed. Source IP address, source port destination, IP address destination port protocol type, TCP/UDP. Think of the 5-tuple hash as a sophisticated traffic director that considers multiple factors before making routing decisions. The inclusion of the source port in this hash is particularly important because it changes for each session. This means that subsequent connections from the same client might be directed to different back-end servers, ensuring an even distribution of traffic across your infrastructure. However, there are scenarios where this default behavior isn't ideal. This brings us to our second distribution mode, Source IP Affinity, also known as Session Affinity or Client IP Affinity. This mode comes in two variations. 2-tuple hash uses source IP and destination IP. 3-tuple hash adds protocol type to the mix. Let's consider a practical example from our healthcare portal scenario. Imagine you're storing user profile information in memory on the server during their session. With the default 5-tuple hash, a user might be redirected to different servers during their session, losing their profile information. This is where Source IP Affinity becomes crucial. To implement Source IP Affinity, you have two options. Through PowerShell.lb, CAS, get as load balancer, name MyLB, resource group name MyResourceGroup, bulb load balancing rules, or load distribution, source ipset as load balancer or LB. Through the Azure portal, navigate to your load balancer resource. Access the load balancing rules section. Select your target rule change session persistence from none to client IP. There are several specific scenarios where source IP affinity is particularly important. Remote desktop gateway services. The default 5-tuple hash is incompatible with RDP services. Source IP affinity ensures consistent connection routing, maintains stable remote desktop sessions. Media upload scenarios. Client initiates TCP connection for session control, separate UDP connection for actual file upload. Source IP affinity keeps both connections on same server, ensures successful completion of uploads. Stateful applications. Applications maintaining session state in memory user profile. Caching scenarios. Shopping cart implementations. Multi-step form submissions. Best practices for implementation. Evaluate your application needs. Does your application maintain session state? Are you handling file uploads? Do you need consistent server assignment? Performance considerations. Source IP affinity may lead to uneven distribution. Monitor server loads regularly. Plan capacity accordingly. Configuration management. Document your distribution mode choices. Test failover scenarios. Monitor session, persistence, behavior scaling. Considerations. Plan for back-end pool changes. Consider impact on session affinity. Test scaling scenarios. Common pitfalls to avoid. Default mode. Assumptions. Don't assume default mode works for all scenarios. Test with your specific application requirements. Session state management. Consider distributed caching alternatives. Plan for server failures. Implement proper session, timeout handling configuration. Mistakes. Double-check distribution mode, settings verify rule applications, test configuration changes. Let's explore internal load balancers in Azure, a crucial component for building scalable and resilient multi-tier applications. I'll guide you through their configuration, use cases, and best practices, with a specific focus on healthcare portal implementation. Let's start with understanding what makes internal load balancers unique. Unlike their external counterparts, internal load balancers are designed to distribute traffic within your virtual network, making them perfect for multi-tier applications where back-end services need to be load balanced but not exposed to the internet. In a healthcare portal architecture, think of it this way. First tier. External load balancer handling patient portal traffic. Second tier. Internal load balancer managing database requests. The key differences in configuring an internal load balancer are type selection. You must explicitly select internal as the type. This setting ensures the load balancer's front-end IP isn't exposed to the internet. Perfect for maintaining security of sensitive back-end services. IP address assignment. Uses private IP addresses instead of public IP stays within your virtual network's address space. Maintains network isolation and security. Network placement must be placed in the protected virtual network. Typically resides in the same VNet as your back-end services. Can span multiple subnets within the VNet. Let's look at a practical implementation in our healthcare portal scenario. Front-end web tier. Handles user requests and UI interactions. Needs to access database services. Requires consistent and reliable back-end connectivity. Database. Tier. Multiple database servers for redundancy. Need to be load balanced for optimal performance. Must remain isolated from direct internet access. The internal load balancer sits between these tiers, providing even traffic distribution, automatic failover capabilities, health monitoring of back-end servers, scalability support. Regarding distribution mode choice for database tier load balancing, we recommend using the default 5-tuple hash distribution because database connections are typically stateless. Even distribution is more important than session affinity, allows for maximum scalability, provides better failover capabilities. Implementation. Best practices. Network security. Implement. Proper network security groups. Use subnet isolation. Control traffic flow with proper rules. Health monitoring. Configure appropriate health probes. Set realistic probe intervals. Define meaningful health criteria. Performance optimization. Monitor back-end pool utilization. Track connection distribution. Adjust configuration based on usage patterns. High availability. Deploy database servers across availability. Sets configure proper failover mechanisms. Test failover scenarios regularly. Common implementation patterns. Basic two-tier architecture. Internet. External LB. Web servers. Internal LB. Database servers. Advanced multi-tier design. Internet. External LB. Web servers. Internal LB1. Application servers. Internal LB2. Database servers. Key configuration points. Virtual network. Setup. Plan your address space carefully. Separate subnets for each tier. Proper route tables. Configuration. Security configuration. Network security groups on each subnet service endpoints where appropriate. Proper access controls. Monitoring. Setup. Azure Monitor Integration Log. Analytics configuration. Alert rules for critical metrics. Troubleshooting. Tips. Connectivity issues. Verify network security group rules. Check routing tables. Validate health probe configuration performance problems. Monitor backend pool. Health check connection. Distribution. Verify network capacity. High availability. Test failover scenarios. Verify health probe. Effectiveness monitor. Backend server. Availability. Let's dive into these questions about Azure Load Balancer configuration and understand the correct answers in detail. Question 1. Internal load balancer requirements. Correct. Answer. A. Virtual machines must be in the same virtual network. This is a fundamental requirement for internal load balancer configuration. Let's analyze why this is correct and why the other options are incorrect. Why same virtual network is required? Network connectivity. Internal load balancers operate within Azure's private network space. All communications happen over private IP addresses. Resources must have direct network connectivity. Security considerations. Maintains network isolation. Enables proper security group implementation. Allows for controlled access between tiers. Architectural benefits. Reduced latency between components. Simplified network security rules. Better resource organization. Why other options are incorrect. Option B. Virtual machines must be publicly accessible. This contradicts the purpose of internal load balancers. Internal load balancers specifically work with private networks. Public accessibility could create security risks. Option C. Virtual machines must be in an availability set. While availability sets are recommended for redundancy, they are not strictly required for load balancer configuration. You can have load-balanced VMs in different availability sets. Question 2. External load balancer. Characteristics correct. Answer. C. They have a public IP address. This correctly identifies a key characteristic of external load balancers. Let's explore why this is the right answer and analyze the incorrect options. Why public IP is essential. Internet accessibility. Allows external clients to reach your services. Enables global access to your applications. Facilitates public-facing services. Azure infrastructure. Public IP is assigned to the load balancer front end, can be static or dynamic. Supports IPv4 and IPv6 in some cases. Why other options are incorrect. Option A. They have a private front-facing IP address. External load balancers must have public IP addresses. Private IPs are used for internal load balancers. This would prevent Internet accessibility. Option B. They don't have a listener IP address. Load balancers require listener IPs to function. The front-end IP acts as the listener. This is essential for traffic routing implementation considerations. External load balancer setup. Requires public IP allocation. Need proper DNS configuration security rules for Internet traffic. Network security. Configure NSG rules appropriately. Consider DDoS protection. Implement proper access controls. Monitoring and management. Track public IP usage. Monitor incoming traffic patterns. Set up proper logging best practices. IP address management. Use static IP when possible. Plan for IP requirements. Document IP assignments. Security. Configuration. Implement proper firewalls. Use network security groups. Regular security audits. Azure Backup represents Microsoft's comprehensive solution for protecting your organization's critical data assets in the cloud. Let's explore its key aspects and understand why it might be the right choice for your data protection needs. At its core, Azure Backup is designed to eliminate the complexities traditionally associated with backup infrastructure. The service operates on a zero infrastructure model, meaning you don't need to worry about maintaining physical backup servers, storage devices, or tape systems. This approach significantly reduces both capital and operational expenses while simplifying your backup management. The centralized management interface stands out as a crucial feature for IT administrators. Instead of juggling multiple backup solutions for different workloads, you can define, monitor, and manage all your backup policies from a single console. This centralization is particularly valuable for organizations with diverse data assets spread across various platforms and locations. One of the most compelling aspects of Azure Backup is its versatility in supporting a wide range of data assets. Whether you're dealing with on-premises files and folders, Azure virtual machines, or sophisticated database systems like SQL Server and SAP HANA, Azure Backup provides consistent, reliable protection. The service seamlessly handles Azure native services, such as managed disks and file shares, while also supporting hybrid scenarios involving on-premises workloads. From a security and compliance perspective, Azure Backup incorporates robust features to address various scenarios. The self-service backup and restore capabilities empower application administrators to handle routine operations independently while maintaining overall organizational control. This is particularly useful in situations involving data corruption or potential security incidents involving privileged users. The service's architecture is designed with enterprise needs in mind. It automatically handles data encryption, both in transit and at rest, and provides built-in monitoring and alerting capabilities. The pay-as-you-go pricing model ensures that you only pay for the storage you actually use, making it a cost-effective solution for organizations of all sizes. For IT administrators responsible for maintaining compliance and data protection standards, Azure Backup offers comprehensive reporting and audit capabilities. These features help demonstrate compliance with regulatory requirements and internal policies, while also providing insights into backup operations and resource utilization. When implementing Azure Backup, organizations can start small and scale as needed. The service's flexibility allows you to begin with critical workloads and gradually expand coverage to include additional data assets as your requirements evolve. This scalability, combined with the service's reliability and ease of management, makes Azure Backup a compelling choice. Azure Backup's key features form a comprehensive framework that addresses the complex challenges of enterprise data protection. Let's explore these features and understand how they contribute to effective backup management. The zero infrastructure approach fundamentally changes how organizations handle backups. Traditional backup solutions require significant investment in hardware, storage, and maintenance. Azure Backup eliminates these requirements by providing a fully managed service where Microsoft handles the underlying infrastructure. This approach not only reduces capital expenses, but also simplifies operations by automatically managing storage allocation and scaling. At-scale management through the Backup Center represents a significant advancement in backup administration. This centralized console serves as a single pane of glass for all backup operations across your organization. IT administrators can discover resources, implement governance policies, and monitor backup status from one location. The platform's support for APIs, PowerShell, and Azure CLI enables automation of routine tasks, further improving operational efficiency. Security features are deeply integrated into Azure Backup's architecture. Data is protected both in transit and at rest through encryption, while private endpoints ensure secure communication within your virtual network. The service includes built-in protection against ransomware and malicious actions, with comprehensive alerting mechanisms to notify administrators of potential security incidents. Understanding recovery time objective, RTO, and recovery point objective, RPO, is crucial for effective backup strategy planning. These metrics help organizations balance their data protection needs with operational requirements. RTO defines how quickly you need to restore service after an incident. For example, if your organization sets an RTO of 4 hours for a critical application, your backup and recovery processes must be capable of restoring service within this time frame. This might influence decisions about backup storage location, restoration procedures, and automation requirements. RPO determines how much data loss your organization can tolerate. An RPO of 1 hour means you need backup copies no more than an hour apart. This directly affects backup frequency and resource allocation. For instance, A customer database with an hourly RPO requires frequent backup operations and sufficient storage capacity. To maintain multiple recovery points, the practical implementation of RTO and RPO requires careful planning. Consider a scenario where a customer database has an RPO of 1 hour and an RTO of 3 hours. This means backup operations must run every hour to ensure no more than 1 hour of data loss. Recovery procedures must be optimized to restore service within 3 hours infrastructure, and processes must be tested regularly to verify these objectives can be met. Monitoring systems should track backup success and alert on any issues that might compromise these objectives. When implementing Azure Backup, organizations should assess the criticality of different workloads to set appropriate RTO and RPO values. Leverage the Backup Center for centralized management and monitoring. Implement appropriate security measures using built-in features. Regular testing of recovery procedures to ensure objectives can be met. Document and maintain backup and recovery procedures for different scenarios. This comprehensive approach ensures that your organization can effectively protect its data while maintaining operational efficiency and meeting compliance requirements. Azure Backup employs a sophisticated multi-layered architecture to provide comprehensive data protection across various workloads. Let's explore how this system works and the different backup types it supports. The architecture consists of 3 primary layers, each serving a specific purpose in the backup process. The workload integration layer, implemented through the backup extension, interfaces directly with various data sources such as Azure VMs, blobs, and on-premises systems. This layer ensures consistent backup operations regardless of the underlying workload. The data plane handles the actual storage of backup data across 3 distinct access tiers. The snapshot tier provides rapid access to recent backups, ideal for quick recovery scenarios. The standard tier offers a balance between accessibility and cost for regularly accessed backups. The archive tier provides cost-effective long-term storage for rarely accessed backup data. For backup implementation, Azure offers multiple methods to accommodate different scenarios. The MAS, Microsoft Azure Recovery Services Agent, enables direct backup to Azure for Windows machines. Organizations can also utilize System Center DPM or Microsoft Azure Backup Server for more complex environments. Azure VMs benefit from seamless integration through the VM Agent extension. SQL Server backup support is particularly comprehensive, offering several backup types to meet various recovery needs. Full backups capture the entire database and can be scheduled daily or weekly. Differential backups store only changes since the last full backup, optimizing storage usage. Transaction log backups enable point-in-time recovery with 15-minute granularity. Enhanced features include multiple daily backups for Azure VMs, with RPO options ranging from 4 to 24 hours. This is particularly valuable for workloads requiring frequent protection. Selective disk backup allows organizations to focus on critical data by backing up specific VM disks, helping optimize costs and storage usage. The backup data is stored in vaults, either recovery services vaults or backup vaults, which serve as central management points. These vaults support various redundancy options, allowing organizations to replicate data across zones or regions based on their availability requirements. When implementing Azure Backup, consider 1. Choosing the appropriate backup method based on your workload type and location. 2. Setting backup frequencies aligned with your RPO requirements. Selecting appropriate storage tiers based on recovery needs and cost considerations. 4. Implementing the right redundancy level for your business continuity requirements. Understanding these components and their interactions helps ensure effective implementation of your backup strategy while optimizing costs and meeting recovery objectives. Azure Backup's technical architecture is built on multiple sophisticated layers that work together to provide comprehensive data protection. Let's explore each component in detail to understand how they create a robust backup solution. The workload integration layer forms the foundation of the backup process. At its core are workload-specific backup extensions that are installed either on the source VM or a worker VM. These extensions are designed to handle different types of backups: storage snapshots for Azure VMs and Azure files, providing point-in-time copies of data; stream backups for database workloads like SQL or SAP HANA, ensuring application consistency; secure data transfer through protected networks using NSGs, firewalls, and private endpoints. The data plane implements a tiered storage approach that balances recovery speed with cost-effectiveness. One snapshot tier provides the fastest recovery option. Stores snapshots in the customer's subscription. Ideal for immediate recovery needs. Eliminates data transfer time from Vault. 2 Vault Standard tier creates isolated backup copies in Microsoft Managed Storage. Provides protection even if source is compromised. Offers standard recovery time objectives. Maintains backup availability if source is deleted archive. Tier designed for long-term retention requirements. Cost-effective storage for compliance data, suitable for rarely accessed backups. Helps meet regulatory requirements. Data protection is enhanced through multiple redundancy options. Locally redundant storage LRS for cost-effective local protection. Geo-redundant storage GRS for cross-region disaster recovery. Zone-redundant storage ZRS for high availability within a region. The security framework includes several critical features. Azure RBAC for granular access control, end-to-end encryption for data protection. Soft delete functionality with 14-day recovery. Window private endpoints for secure network communication. The management plane provides comprehensive control through recovery services vaults for backup orchestration. Backup Center for unified management, cross-subscription and cross-tenant management capabilities. Policy-based backup management. When implementing Azure Backup, consider choosing appropriate access tiers based on recovery needs. 2. Implementing the right redundancy level for your requirements. Setting up proper RBAC permissions. 4. Utilizing Backup Center for centralized management. This layered architecture ensures that Azure Backup can provide enterprise-grade protection while maintaining flexibility and ease of management. Deciding whether Azure Backup is the right solution for your organization involves evaluating several key criteria and understanding how they align with your specific needs. Let's examine the decision framework and practical applications. Azure Backup's workload support is extensive and particularly valuable for organizations with diverse Azure resources. The service excels at protecting Azure native workloads, including complete VM backups with file-level recovery options, database protection for SQL Server and SAP HANA, specialized support for Azure Files and Blobs, integration with Azure Database for PostgreSQL compliance requirements are a critical factor in backup strategy decisions. Azure Backup addresses these needs through flexible retention policies supporting both short-term and long-term requirements, customizable backup schedules to meet specific regulatory demands, granular RBAC controls for access management, multi-zone storage options for geographic redundancy. For operational recovery scenarios, Azure Backup provides several key advantages. Self-service backup and restore capabilities for application administrators. Quick recovery options through the snapshot tier. Protection against data corruption and accidental deletion. Centralized management through Backup Center SQL Server protection, deserves special attention due to its critical role in many organizations. Azure Backup offers specialized features, support for all backup types, full, differential, log, 15-minute RPO with frequent log backups, second-level point-in-time recovery, database-level backup, and restore operations. Monitoring and administration capabilities include integration with Azure Monitor and Log Analytics, built-in job monitoring at the vault level, Backup Explorer for cross-estate visibility, detailed reporting through Azure Workbooks. When implementing Azure Backup, consider evaluating your workload types and their backup requirements. 2. Determining your compliance needs for retention and redundancy. 3. Assessing your operational recovery requirements. 4. Planning your monitoring and reporting strategy. Remember that while Azure Backup offers comprehensive protection, it's important to understand its limitations. Cross-region backup isn't supported for most workloads. Some features may require specific Azure service tiers. Retention periods and backup frequencies have service-defined limits. These considerations help ensure that Azure Backup aligns with your organization's data protection strategy while meeting both technical and business requirements. Let's go through each question and understand the correct answers and the reasoning behind them. Question 1. Which tier allows for quick restore operations on a backup? Correct answer: Snapshot tier. Explanation: the Snapshot tier is specifically designed for rapid restore operations. Here's why it's the fastest option. Snapshots are stored locally in the customer's subscription. No need to copy data from the vault before restoration. Eliminates data transfer time across storage tiers. Provides immediate access to backup, data, and contrast. Standard tier requires data transfer from the vault. Archive tier is optimized for long-term storage, not quick access. Question 2. What tool can you use to manage backups spanning multiple workload types, vaults, subscriptions, regions, and Azure Lighthouse tenants? Correct answer: Backup Center. Explanation: Backup Center is the comprehensive management solution because it provides a single pane of glass view across your entire backup estate, supports management across multiple subscriptions and regions, enables cross-tenant management through Azure Lighthouse, offers unified governance and monitoring capabilities. While Azure Monitor and DPM are valuable tools, Azure Monitor is primarily for monitoring and analytics. DPM is focused on on-premises backup management. Neither provides the comprehensive cross-estate management of Backup Center. Question 3. What must be present before you can back up an entire VM or content on an Azure VM? Correct answer: Backup extensions. Explanation: Backup extensions are essential for VM backup because they integrate directly with the VM's operating system, enable consistent backup operations, handle backup data streaming and management, provide workload-aware backup capabilities. The alternatives are not prerequisites. MABS is an optional component for on-premises backup management. Recovery point objective policies are important, but come after extension installation. The backup extension must be installed first to enable any backup functionality. When implementing Azure Backup, remember: choose appropriate storage tiers based on recovery time needs. 2. Utilize Backup Center for enterprise-wide management. 3. Ensure backup extensions are properly installed before configuring backup policies. This understanding helps ensure effective implementation of Azure Backup while meeting your organization's recovery objectives. Today we'll dive into the essential components and configuration settings of Azure Load Balancer rules. Understanding these elements is crucial for designing reliable and efficient load balancing solutions in Azure. Let's start with the three fundamental components that every load balancer rule must have. First, you need a front-end IP and port configuration. This is essentially your service's front door, where all client traffic initially arrives. Second, you need a back-end pool, which is your collection of resources that will actually handle the incoming traffic. Third, and equally important, is the health probe, which continuously monitors the health of your back-end resources to ensure traffic is only directed to healthy instances. Moving to configuration settings, you have several crucial decisions to make. The IP version choice between IPv4 and IPv6 affects your application's accessibility and compliance requirements. Your protocol selection, TCP or UDP, depends on your application's specific needs. TCP provides reliability and ordered delivery, while UDP offers speed with less overhead. Port mapping allows you to define how incoming traffic on specific ports is distributed to your back-end resources. The 5-tuple hash is particularly interesting. It's the foundation of how Azure Load Balancer makes its distribution decisions. This hash consists of 5 key components: source IP, source port, destination IP, destination port, and protocol. Understanding this helps you predict and control how your traffic will be distributed across your back-end pool. Session persistence is where things get really practical. Azure Load Balancer offers 3 distinct types. The None option means any VM in your back-end pool can handle any request, perfect for stateless applications. Client IP Affinity ensures that all requests from a specific IP address go to the same VM, useful for maintaining client-specific states. IP Plus Protocol adds another layer of specificity, directing traffic based on both the client's IP and the protocol used. Let's look at a real-world scenario. Imagine you're running an e-commerce platform. Your shopping cart functionality requires session persistence to maintain the cart state across multiple requests. In this case, you'd likely choose the Client IP or IP Plus Protocol persistence option to ensure all requests from a specific customer are directed to the same back-end server, preventing cart data from being lost or fragmented across different servers. These configuration choices directly impact your application's reliability, performance, and user experience. The key is matching these settings to your specific use case and requirements. Remember that while load balancer rules seem complex at first, they follow a logical pattern aimed at one goal: efficiently distributing traffic while maintaining application functionality. Whether you're setting up a simple web application, let's explore the Azure Recovery Services Vault, which serves as the cornerstone of Azure's backup and recovery infrastructure. Think of it as a highly secure digital vault where you store not just backup data, but also all the configuration information needed to protect your IT environment. The Recovery Services Vault is designed with versatility in mind. Let's explore its capabilities, starting with Azure Workload Protection. The Vault can protect a wide range of Azure services. Everything from your infrastructure as a service virtual machines, whether they're running Windows or Linux, to your Azure SQL databases. This native integration with Azure services means you get seamless protection without having to manage complex backup infrastructure. But what makes the Recovery Services Vault truly powerful is its hybrid capabilities. It's not just for cloud workloads. It extends its protection to your on-premises environment as well. Whether you're running Hyper-V, VMware, or need system state backups, the Vault has you covered. This is particularly valuable for organizations in their cloud journey, as it provides a single solution for both cloud and on-premises workloads. The integration capabilities are extensive. The Vault works seamlessly with System Center Data Protection Manager, DPM, Windows Server, and Microsoft Azure Backup Server, MABS. This integration means you can continue using your existing backup tools while leveraging the scale and security of Azure storage. Speaking of security, the Vault comes with robust security features built in. All data is encrypted by default, both at rest and in transit. Role-based access control, RBAC, ensures that only authorized personnel can access or modify backup configurations. The soft delete feature provides an additional layer of protection against accidental or malicious deletion of backup data. Let's talk about management efficiency. The Vault provides centralized monitoring of all your backup operations. You can implement policy-based backup management, which automates the protection of your resources based on predefined rules. The Vault automatically scales to accommodate your growing backup needs without requiring manual intervention. One of the most significant benefits is cost optimization. By centralizing your backup storage, you can better manage your backup costs. The Vault supports various storage tiers, allowing you to match your storage costs with your recovery time objectives. For instance, you might keep frequently accessed backups in hot storage, while moving older backups to cool storage for cost efficiency. Here's a practical tip. When setting up your recovery services vault, consider your compliance requirements early. The Vault supports features like long-term retention and geo-redundancy, which can help meet various regulatory requirements. You can configure these settings during Vault creation, and while they can be modified later, let's walk through the process of backing up Azure virtual machines. This is a straightforward three-step process, but each step has important considerations that can impact your backup strategy's effectiveness. Let's start with step 1, creating a recovery services vault. Think of this as establishing your backup's home base. The key decision here is choosing between geo-redundant storage, GRS, and locally redundant storage, LRS. If Azure is your primary backup destination, go with GRS. It's the default option and provides the highest level of data protection by replicating your data to a secondary region. However, if you're using Azure as a secondary backup location or need to optimize costs, LRS might be more appropriate. Remember, the Vault's location is crucial. You want to create it in the same region as your virtual machines to minimize data transfer costs and optimize backup performance. This is especially important when you're dealing with large amounts of data or tight backup windows. Moving to step 2, defining your backup policy. This is where you specify the rhythm of your backup strategy. Azure gives you impressive flexibility here. You can schedule backups up to 5 times per day. When setting this up, think about your recovery point objective, RPO. How much data can you afford to lose in a worst-case scenario? This will guide your backup frequency decision. The policy also determines how long you keep your backups. You're creating recovery points, essentially time machines for your VMs, that you can use to restore your systems if needed. Balance retention periods with storage costs and compliance requirements. For instance, you might keep daily backups for a month, but retain monthly backups for a year. Finally, step 3, executing the backup. This is where the Azure Backup Extension and VM Agent come into play. If you're working with VMs created directly in Azure from the gallery, you're in luck. The agent is already installed. However, for VMs migrated from on-premises environments, you'll need to manually install the agent. This is a critical step that's easy to overlook during migration planning. Here's a pro tip. Before starting your first backup, verify the VM agent's status. You can do this through the Azure portal or using PowerShell. It's much better to discover and resolve agent issues before you need to rely on your backups. Some practical considerations for implementation. Start with a pilot backup of a non-critical VM to validate your policy settings. Monitor your first few backup jobs closely to ensure they complete successfully. Document any custom settings or configurations for your team. Set up alerts for failed backup jobs to ensure quick response to issues. The beauty of this process is its simplicity, but don't let that simplicity fool you. Each step has been designed to provide enterprise-grade protection while remaining manageable. Let's explore the process of restoring Azure virtual machines from backup. While creating backups is crucial, The real test of any backup solution is how effectively you can restore your systems when needed. Let's walk through the restore process, which begins with your recovery options. Azure Backup provides remarkable flexibility in how you can restore your data. You have two primary paths: quick recovery from snapshots or point-in-time recovery using recovery points stored in your recovery services vault. The restoration timeline follows a logical progression. It starts with selecting your recovery point. This could be a recent snapshot for quick recovery or a specific point in time. Recovery point for older restores. Once you initiate the restore, Azure Backup creates a restore job to track the operation. This job creation is a crucial step because it provides the framework for monitoring the entire restore process. Speaking of monitoring, Azure Backup provides comprehensive visibility into your restore operations. You'll receive notifications at key points during the restore process. These notifications appear in the Azure portal and can be tracked through the Jobs section of your Recovery Services Vault. This monitoring capability is essential for keeping stakeholders informed during critical recovery operations. Let's talk about restore options in more detail. You have several choices. Full VM Restore creates a completely new VM from your backup. File Level Recovery allows you to restore specific files without restoring the entire VM. Disk Restore recovers just the virtual hard disks, which you can then attach to other VMs. Cross-Region Restore enables recovery to a different Azure region for disaster recovery scenarios. Here's a pro tip about restore operations. Always verify your networking requirements before starting a restore. If you're restoring to a new location or with a new network configuration, ensure all the necessary networking components are in place before initiating the restore. This includes virtual networks, subnets, and any required network security groups. Monitoring your restore operation is straightforward but important. The Jobs view in the Azure portal provides real-time status updates. You can track job progress percentage time, elapsed data transferred, any errors or warnings that occur during the restore. Best practices for restoration include regularly testing your restore procedures with non-critical systems, documenting your restore process, including any specific configurations needed, setting up alerts to notify key personnel of restore job status, validating restored VMs to ensure they're functioning correctly. Here's a critical consideration that often gets overlooked: permissions. Ensure that the operators performing the restore have the necessary RBAC permissions, not just for the backup vault, but also for creating VMs and networking resources in the target subscription and resource group. We're exploring Azure's soft delete feature for virtual machines, a crucial safety net that helps protect against accidental or malicious deletion of your backup data. Think of soft delete as a recycle bin for your VM backups. It gives you a 14-day window to recover deleted backup data. Let's start with a critical point. Soft delete only protects VMs that have been backed up. If a VM is deleted without having any backups, soft delete can't help you recover it. This underscores the importance of implementing a comprehensive backup strategy for all your critical resources. The soft delete lifecycle follows a specific sequence. It begins when you stop a backup job. When you choose to delete backup data instead of permanent deletion, the data enters a soft deleted state. This state preserves the backup data for 14 days, giving you a safety buffer to recover from unintended deletions. During this 14-day period, you can easily identify soft deleted items in your Recovery Services Vault. They're marked with a distinct red soft delete icon. This visual indicator helps you quickly spot items that are in the soft deleted state and might need attention. Let's talk about the recovery process. If you need to restore a soft deleted backup, you'll follow these steps. First, you must undelete the backup data. Then you can select a recovery point and restore your virtual machine. Finally, you can resume regular backups with your chosen policy. Here's a practical consideration that's easy to overlook. You cannot delete a recovery services vault if it contains any soft deleted items. This is a safeguard to prevent accidental data loss. If you need to delete a vault, you must first either recover or permanently delete all soft deleted items. When you undelete a backup item, it returns to the stop backup with retained data state. From there, you can resume backups, and the item will follow whatever backup and retention policy you select. This flexibility allows you to adjust your backup strategy as needed when recovering items. Some key best practices for managing soft deleted items. Regularly monitor your vault for soft deleted items. Document the process for undeleting items. Set up alerts for when items enter the soft deleted state. Consider automated inventory tracking of soft deleted items. A word of caution about the 14-day retention period. This is a fixed window that cannot be extended. Make sure your operational procedures account for this limitation. If you need longer-term protection, consider implementing additional backup strategies or retention policies. Here's a pro tip. Consider implementing a process to review soft deleted items regularly, perhaps weekly. This helps ensure that no critical backups are accidentally left in the soft deleted state until they expire. The real power of soft delete lies in its simplicity. It's an automatic safety net that requires no additional configuration, but provides crucial protection against data loss. Now we're diving into Azure Site Recovery, a comprehensive disaster recovery service that's revolutionizing how organizations approach business continuity. Let me share a real-world scenario to illustrate its importance. Imagine you're running an e-commerce platform that processes thousands of transactions daily. Your primary data center is humming along smoothly when suddenly a natural disaster strikes, perhaps a major storm or power outage. Without proper disaster recovery, you're looking at significant downtime, lost revenue, and damaged customer trust. This is where Azure Site Recovery becomes invaluable. At its core, Site Recovery provides three fundamental capabilities. First, it offers continuous replication of your workloads, ensuring your data stays synchronized between locations. Second, it provides orchestration of the entire failover process, automating what would otherwise be complex manual procedures. Third, it enables you to test your disaster recovery plans without impacting production workloads, a feature that's often overlooked, but crucial for maintaining confidence in your DR strategy. The service supports an impressive range of scenarios. You can replicate Azure VMs between regions, which is perfect for meeting regional compliance requirements or managing geographic redundancy. For organizations with on-premises infrastructure, it supports VMware, Hyper-V, and even physical servers. Interestingly, it also supports AWS Windows instances, making it a valuable tool for multi-cloud strategies. Let's talk about some key features that set Site Recovery apart. The 30-second replication frequency is remarkable. It means you can achieve recovery point objectives, RPOs, measured in seconds rather than hours. The app-consistent snapshots ensure that when you fail over, your applications remain functional, not just your servers. The business benefits are compelling. First, there's significant cost reduction. You're eliminating the need for a secondary data center while only paying for the compute resources when you actually fail over. The simplified management through a single portal reduces operational overhead and the potential for human error. And because you're leveraging Azure's infrastructure, you get enterprise-grade scalability and resilience built in. Integration capabilities are particularly impressive. You can reserve IP addresses to ensure your applications maintain network consistency after failover. Load balancer configuration is automated, and the integration with Azure Traffic Manager means you can maintain intelligent traffic routing even during a disaster scenario. Here's a pro tip about testing. Take advantage of the zero-impact testing capability. You can run a full failover test without disrupting your production environment. This allows you to validate your recovery plans and meet compliance requirements without risk. We're exploring Azure Monitor, Microsoft's comprehensive solution for collecting, analyzing, and acting on telemetry data across your entire cloud and on-premises infrastructure. Think of it as your central nervous system for monitoring, gathering signals from every corner of your environment and helping you make sense of them. Let's start with the three core capabilities that make Azure Monitor so powerful. First, there's monitoring and visualization of metrics. Azure Monitor automatically collects numerical data points from your resources, everything from CPU utilization to request rates. This gives you real-time visibility into your system's performance and health. Second, we have query and analysis of logs through Azure Monitor Logs, formerly known as Log Analytics. This capability goes beyond simple metrics to provide deep insights into your system's behavior. You can write sophisticated queries to analyze everything from application traces to security events. Third, there's the alerting and action framework. This is where Azure Monitor transforms from a passive monitoring tool into an active management platform. You can set up alerts based on any metric or log query and trigger automated responses when conditions are met. The data sources feeding into Azure Monitor are comprehensive. It collects data from Azure resources, built-in metrics and logs from your cloud services, applications, custom telemetry from your code through application insights, operating systems, both Windows and Linux performance, and diagnostic data custom sources, any metrics or logs you choose to send to the platform. This data is stored in two fundamental types of stores: the metrics database, optimized for time series numerical data, the logs database, designed for complex query and analysis of textual and structured data. But collecting data is just the beginning. Azure Monitor's insights capabilities transform this raw data into actionable intelligence. Application Insights, for example, provides deep application performance monitoring (APM) capabilities. You can track request rates, response times, and dependency calls, helping you identify bottlenecks and optimize performance. The visualization options are particularly powerful. Azure Workbooks allow you to create interactive reports combining metrics, logs, and text. You can build custom dashboards that give you exactly the view you need of your environment. And with Power BI integration, you can create sophisticated visualizations for stakeholders at all levels. Here's a practical example of how these capabilities work together. Imagine you're running a critical web application. Azure Monitor can track your application's performance metrics in real-time, detect when response times exceed your thresholds, automatically scale up your resources or fail over to a backup system, notify your team, and provide diagnostic information. Record the incident and resolution for future analysis. We're diving into the two fundamental types of data in Azure Monitor, metrics and logs. Understanding the distinction between these two types is crucial for effective monitoring and troubleshooting in Azure. Let's start with metrics. Think of metrics as the vital signs of your system. Numerical values that tell you how your resources are performing at any given moment. Just like a doctor monitoring a patient's heart rate or blood pressure, metrics give you immediate insight into your system's health. Metrics have several key characteristics that make them particularly valuable. They're lightweight and collected in near real time. They have a structured, predictable format. They're perfect for real-time monitoring and alerting. They work well with automated responses like auto-scaling. For example, when you look at an Azure VM's overview page, you'll see metrics like CPU utilization, network throughput, and disk operations. These metrics are automatically collected and displayed in easy-to-read charts. The Metrics Explorer is your primary tool for working with metrics. It allows you to combine multiple metrics on a single chart, apply filters, and grouping create custom visualizations, pin charts to dashboards for ongoing monitoring, Now, let's talk about logs. If metrics are like vital signs, think of logs as the detailed medical history. They provide rich context and historical data about what's happening in your system. Logs can contain detailed event records, application traces, performance data, custom diagnostic information log. Analytics is your workshop for working with log data. It uses a powerful query language, KQL, Custo query language, that might feel familiar if you know SQL or Splunk. With log analytics, you can write complex queries to analyze data, combine data from multiple sources, create custom visualizations, set up sophisticated alerts. Here's a practical example of how metrics and logs complement each other. Imagine you're troubleshooting a performance issue. Metrics show you that CPU usage spiked at 2 a.m. Logs tell you what events occurred around that time. Together, they give you the complete picture of what happened. A pro tip about working with metrics: start with the overview page for your resources. The pre-configured charts give you immediate insight into common issues. Then use Metrics Explorer to dive deeper or create custom visualizations. For logs, here's a valuable practice. Learn the basics of KQL, Custo query language. While the language is powerful and complex, even basic queries can provide valuable insights. Azure Portal includes interactive guides to help you learn KQL step by step. Remember that metrics and logs serve different purposes. Use metrics for real-time monitoring and automated responses. Use logs for deep analysis and troubleshooting. Combine both for complete operational visibility. We're exploring Azure Monitor's data collection tiers and how they work together to provide comprehensive monitoring coverage across your entire Azure environment. Think of these tiers as layers of an onion, each providing deeper insight into different aspects of your system. Let's start at the outermost layer, the application tier. This is where you collect data about your application's performance and functionality. What's particularly powerful about this tier is that it works regardless of where your application runs, in Azure, on-premises, or in another cloud. It captures things like request rates and response times, exception details, custom application metrics, user behavior analytics. Moving inward, we have the Guest OS tier. This layer focuses on the operating system hosting your application. Through the Azure Monitor agent, you can collect performance counters, event logs, system logs, custom log files. The Azure Resource tier is particularly interesting because it starts collecting data automatically as soon as you create a resource. It captures resource health information, performance metrics, diagnostic logs, resource consumption data. The subscription tier provides a broader view of your Azure environment. It includes Administrative Action Service, health autoscaling, operations, security and compliance data. Finally, at the core, we have the tenant tier, which monitors your tenant-level Azure services like Microsoft Entra ID. This gives you visibility into identity operations, access management directory services. What makes Azure Monitor powerful is how it collects this data. There are several collection methods. Automatic collection starts immediately for platform-level metrics. The Azure Monitor agent extends collection to operating system and application data. Diagnostic settings enable detailed resource-level logging. The Data Collector API allows for custom data integration. Here's a pro tip about data collection. Start with the automatic collection capabilities and gradually enable additional data sources based on your monitoring needs. This approach helps you manage data volumes and costs effectively. A practical example of how these tiers work together. Imagine troubleshooting a slow application. Application tier shows high response times. Guest OS tier reveals high CPU usage. Resource tier indicates resource constraints. Subscription tier shows recent configuration changes. Tenant tier confirms no authentication issues. One often overlooked feature is the Data Collector API. It allows you to send custom metrics and logs, integrate third-party monitoring data, create unified monitoring solutions. Remember that different tiers have different retention periods and costs. Consider how long you need to keep different types of data, the granularity of data you need, the volume of data you're collecting. We're exploring the Azure Activity Log, which serves as your subscriptions audit trail, capturing all subscription-level events in Azure. Think of it as your system's journal, recording who did what, when, and with what result. Let's start with what makes the activity log special. Unlike other logs that focus on specific resources, the activity log provides a subscription-wide view of all operations. It captures every write operation, that's your put, post, and delete actions, performed on your resources, along with important platform events. The activity log retains data for 90 days, which gives you a substantial window for investigating security incidents, troubleshooting operational issues, meeting compliance requirements, understanding system changes. Let's break down what information you can find in the activity log. Operation details. What action was taken, timestamp. When the action occurred, user identity. Who performed the action? Resource information. What was affected, operation status. Whether it succeeded or failed. This information answers 5 critical questions. What happened? Who did it? When did it occur? What's the current status? What was the impact? Here's a practical example of how to use the activity log. Imagine you're investigating why a virtual machine stopped working. Check the activity log for recent operations on the VM. Identify who made recent changes. See the exact timing of events. Review any error messages or status changes. Understand the sequence of events leading to the issue. The activity log is accessible through multiple interfaces. Azure Portal for interactive exploration, Azure CLI for command line queries, PowerShell for scripted analysis, REST API for custom integration, SDKs for application integration. A pro tip about working with activity logs. Set up regular exports to a storage account or event hub. This allows you to retain data beyond 90 days, perform detailed analysis, integrate with security information and event management, SIEM systems, meet compliance requirements. Here are some key business scenarios where activity log proves invaluable. Audit and compliance. Track all resource changes. Monitor administrative actions. Document configuration changes, security. Investigation, identify unauthorized changes. Track access patterns. Detect suspicious activities. Operational troubleshooting. Debug deployment issues, understand service health impacts. Track resource modifications. One often overlooked feature is the ability to create custom queries and views. You can filter by operation, type search by specific users, focus on particular resources, create custom dashboards. Remember that while 90 days of retention is provided by default, you should export critical data for longer retention, set up automated analysis, create regular review processes. Welcome to our deep dive into log analytics in Azure Monitor. This powerful tool serves as your window into the wealth of data collected across your Azure environment, enabling sophisticated analysis and proactive monitoring capabilities. Let's start with the core capabilities of log analytics. At its heart, it's a robust query engine powered by the Kusto Query Language, or KQL. This isn't just any query language. It's specifically designed for handling large volumes of log data efficiently. Whether you need to search through millions of records or join data from multiple sources, KQL makes these complex operations surprisingly straightforward. One of the most compelling features is the ability to perform what we call pattern recognition. Imagine being able to spot unusual behavior across your entire infrastructure before it becomes a problem. This is where log analytics truly shines. Let me share a real-world scenario that demonstrates the power of log analytics. Consider the challenge of system updates and patching. In the traditional IT world, scheduling updates was often a game of educated guesses. But with Azure's log analytics, we have access to something unique: crowdsourced timing data from across the Azure ecosystem. This means you can predict with remarkable accuracy how long your specific updates will take based on actual data from similar environments. The security monitoring capabilities are equally impressive. Log Analytics acts as your security command center, helping you identify suspicious account activities that could indicate a compromise, unauthorized software installations that might introduce vulnerabilities, unexpected system behaviors that could signal problems, potential security breaches in their early stages. Issues in complex distributed applications. A particularly powerful feature is the ability to correlate data from multiple sources. Think of it as having multiple security cameras covering different angles of the same space. You get a complete picture that helps you understand not just what happened, but why it happened. The best part, you don't always need to be a query expert to get value from log analytics. Many insights and solutions come with pre-built analyses that process your log data automatically, giving you actionable insights without writing a single line of code. Remember, log analytics isn't just a monitoring tool. It's your partner in maintaining a healthy, secure, and efficient Azure environment. Whether you're troubleshooting an incident, planning maintenance, or monitoring security, log analytics provides the visibility and insights you need to make informed decisions. Let's walk through the process of creating a log analytics workspace, which serves as the foundation for your Azure Monitor logging infrastructure. Think of this workspace as your central command center for log data management. The creation process requires careful consideration of several key parameters, each serving a specific purpose in your monitoring strategy. First, let's talk about naming your workspace. This isn't just any name. It needs to be unique within your resource group. Think of it like creating a new email address. You can't use a name that's already taken. Choose something meaningful that reflects its purpose in your organization. The subscription selection is crucial as it determines both billing and access control. This choice affects who can access the workspace and how the costs are managed. Similarly, the resource group selection helps with organizational structure and management. An important requirement here is that the resource group must contain at least one Azure virtual machine. This ensures you have actual resources to monitor. When it comes to region selection, there's an important caveat. Not all Azure regions support log analytics. Always verify regional availability through the Azure Monitor product page. This decision is particularly important because it can impact data residency requirements and compliance needs. The pricing tier defaulting to pay-as-you-go offers flexibility. You only start incurring charges when you begin collecting data. This model allows you to scale your monitoring costs with your actual usage. Each workspace can have its own pricing tier, and you can adjust this as your needs evolve. After creation, you'll need to configure your data sources, determining what information flows into your workspace. 2. Set up solutions, implementing the specific monitoring tools you need. 3. Begin the actual monitoring process, starting data collection and analysis. A pro tip: while setting up your workspace, consider your organization's data retention requirements, access control needs, compliance regulations, performance monitoring goals. This initial configuration sets the stage for effective monitoring and management of your Azure environment. Welcome to our deep dive into the Kusto Query Language, or KQL, the powerful engine behind Azure Log Analytics. Today, we'll explore how this versatile language can transform the way you analyze and understand your cloud infrastructure. Think of KQL as your Swiss Army knife for data analysis in Azure. Just as a skilled craftsperson needs the right tools, An Azure administrator needs powerful querying capabilities to effectively manage and monitor their environment. That's exactly what KQL provides. A robust set of tools wrapped in an approachable syntax. Let's start by examining the structure of a basic KQL query. On our slide, you can see a practical example. Le perf where time generated ago want where counter name one under CPU summarize AVG counter value by computer. Render time chart. This isn't just a random sequence of commands, it's a logical flow that tells a story. We begin with our data source, perf, filter for recent data, focus on CPU metrics, calculate averages for each computer, and visualize the results. Each pipe symbol represents a step in our data processing journey, making complex analysis surprisingly straightforward. The real beauty of KQL lies in its practical applications. Let's explore some real-world scenarios. For performance monitoring, you might track CPU spikes across your virtual machines. Instead of manually checking each server, a simple KQL query can show you exactly where and when performance issues occur. By saving this query, you can reuse it whenever needed, saving valuable time during troubleshooting. Security analysis becomes more manageable with KQL. Rather than sifting through countless log entries, you can create targeted queries to identify suspicious patterns. For instance, you could track failed login attempts or unusual access patterns, helping you stay ahead of potential security threats. The automation capabilities are particularly exciting. Imagine having your most important queries run automatically, alerting you only when specific conditions are met. This proactive approach transforms KQL from a simple query tool into an intelligent monitoring system. You could automatically detect when services are approaching capacity, when suspicious activities occur, or when system performance degrades. What makes KQL especially powerful is its integration capabilities. Once you've analyzed your data, you can export findings to Power BI for executive-friendly dashboards, send regular reports to stakeholders via Excel, create custom visualizations directly in Azure Portal, set up automated alerts based on query results. Here's a pro tip that many administrators overlook. Start building a library of commonly used queries. Think of it as creating your personal toolbox. When an incident occurs, you'll have ready-to-use queries for quick investigation. For example, keep queries handy for performance bottleneck analysis, security incident investigation, resource usage trending, Azure Network Watcher, your comprehensive toolkit for network monitoring and diagnostics in Azure. Today, we'll discover how this powerful service can help you maintain a healthy and secure network infrastructure. Think of Network Watcher as your network's health monitoring system. Just as a doctor uses various tools to diagnose a patient's condition, Network Watcher provides multiple tools to understand and troubleshoot your network's health. Let's explore these tools and their practical applications. First, let's look at IP Flow Verify. Imagine it as your network's traffic cop. When you're facing connectivity issues, this tool quickly tells you whether traffic is being allowed or blocked by your security rules. For example, if a critical application suddenly can't reach its database, IP Flow Verify can immediately tell you if a security rule is blocking the connection. This saves precious time in troubleshooting by identifying the root cause quickly. The next hop feature acts like your network's GPS system. When network traffic isn't reaching its intended destination, Next hop shows you exactly where the traffic is being redirected. This is particularly valuable when dealing with complex routing configurations. For instance, if traffic meant for your production database is accidentally routing to a test environment, Next hop will reveal this misrouting immediately. VPN Troubleshoot is your specialized diagnostic tool for hybrid connectivity. When your connection to on-premises resources becomes unstable, this feature collects comprehensive diagnostic data including Connection statistics, CPU and memory usage, security-related errors, packet drops and buffer issues. This data is automatically saved to your storage account, providing a detailed history for analysis and troubleshooting. NSG Diagnostics through flow logs serves as your network security camera system. It records all traffic flowing through your network security groups, providing invaluable data for security compliance auditing, network traffic pattern analysis, incident investigation, optimization of security rules. IP Flow Verify, one of the most practical troubleshooting tools in Azure Network Watcher's arsenal. Think of IP Flow Verify as your network's traffic detective. It helps you quickly determine whether network security rules are allowing or blocking specific communication patterns. Let's start with a real-world scenario. Imagine you've deployed a new application, but users can't access it. Is it a security rule blocking the traffic? Is it something else? IP Flow Verify helps you answer these questions quickly and definitively. The tool works by simulating network traffic and checking it against your network security group NSG rules. It's like having a test packet that can safely probe your network security without actually sending real traffic. Let's break down what you need to configure for an IP Flow Verify test. First, you need to identify your target resources. Which virtual machine are you testing? Which network interface should be used? These details help focus the test on the exact communication path you want to verify. Next, you'll specify the connection details, the local source port number, the remote IP address and port number, the protocol being used, TCP or UDP. Think of these as the from and to addresses for your test communication. Finally, you'll specify the traffic direction, inbound, testing if traffic can reach your VM, outbound, testing. If your VM can reach other resources after running the test, IP Flow Verify provides clear results. If access is allowed, you know the NSG rules are correctly configured. If access is denied, the tool tells you exactly which security rule is blocking the traffic. Here's a pro tip. When troubleshooting connectivity issues, always start with IP Flow Verify before diving into more complex networking tools. Why? Because it quickly tells you if the problem is related to NSG rules or if you need to look elsewhere. Understanding the default security rules is crucial. When you deploy a VM, Azure automatically applies certain security rules. These rules allow internal virtual network communication, permit Azure load balancer traffic, block all other inbound internet traffic. You can override these defaults or add your own rules, but sometimes this leads to unexpected behavior. IP Flow Verify helps you understand exactly how your rules are being applied. Let's look at some practical applications. Testing a new application deployment. Verify that web traffic can reach your application servers. Confirm database connections between tiers. Check if management traffic is properly restricted, validating security changes. After updating NSG rules, quickly verify the impact. Ensure critical services remain accessible. Confirm that restrictions are working as intended. Troubleshooting existing applications. Identify why traffic is being blocked. Verify if recent changes affected connectivity. Next, hop diagnostics in Azure Network Watcher. This powerful feature serves as your network traffic GPS, helping you understand and verify where your data is flowing within your Azure infrastructure. Let's start with the core concept. NextHop is essentially a verification tool that checks if your network traffic is reaching its intended destination. Think of it as a network route inspector that tells you the next stop your data packet will make on its journey through your network infrastructure. The configuration process is straightforward but requires attention to detail. You'll need to specify your Azure subscription and resource group, which sets the scope of your investigation. Then you'll identify the specific virtual machine and its network interface that you want to analyze. The source IP address is crucial as it's your starting point, and optionally, you can specify a destination IP address if you're troubleshooting connectivity to a specific target. When you run a next hop test, it returns 3 key pieces of information: the type of next hop, which could be Internet, virtual network, or a service endpoint, the IP address of the next hop if one is available, and the associated route table, which helps you understand the routing decisions being made. One of the most powerful aspects of next hop is its handling of different routing scenarios. If you've configured user-defined routes, UDRs, the feature will show you these custom routes. If not, it falls back to showing the system routes that Azure automatically creates. There's also a special case where the next hop type shows as none. This doesn't necessarily mean there's a problem, but it indicates that while a valid system route exists to your destination, there isn't a next hop available to route the traffic. This brings us to practical applications. Next hop diagnostics really shines when you're troubleshooting network issues. Imagine a scenario where a virtual machine suddenly can't communicate with other resources. Instead of manually tracing the network path, you can use next hop to quickly identify where the communication breaks down. This is particularly valuable in complex networks with multiple subnets and custom routing rules. Azure's networking infrastructure includes default outbound routes that handle traffic from all your deployed resources. While these default routes work well for many scenarios, you might need to override them or create additional routes for specific requirements. Next hop helps you validate these custom configurations and ensure they're working as intended. Here's a practical example. Let's say your web application running on a VM suddenly can't reach your database server. Using next hop, you can examine the path between these two resources by specifying the web server's IP as the source and the database, server's IP as the destination. The test results will show you exactly where the traffic is being directed, helping you identify if there's a misconfigured route, a blocked path, or another networking issue. Remember, network troubleshooting is often about eliminating possibilities and narrowing down the problem area. Next hop diagnostics gives you the visibility you need to do this efficiently, saving you valuable time in maintaining and optimizing your Azure network infrastructure. Network topology, visualization in Azure. Network Watcher is a powerful tool that transforms complex network configurations into clear, visual representations. Imagine walking into a maze without a map. That's often how administrators feel when dealing with unfamiliar virtual networks. Azure Network Watcher's topology tool serves as your network map, providing a clear visual guide to your infrastructure's layout and connections. The beauty of this tool lies in its comprehensive visualization capabilities. It doesn't just show you individual components, it reveals the entire ecosystem of your virtual network. Think of it as an architectural blueprint of your cloud infrastructure, where you can see how every piece fits together. Let's look at what you can visualize. The tool shows you virtual machines, which are like the buildings in your network city. Network interfaces act as the doors to these buildings, controlling how traffic flows in and out. Public IP addresses are like street addresses that make your resources accessible from the Internet. Network security groups serve as your security checkpoints, controlling who gets in and out. Route tables are your traffic directors, determining which way the network traffic should flow. And subnets are like neighborhoods within your virtual network, organizing your resources into logical groups. One crucial point to remember is the regional requirement. You need an Azure Network Watcher instance in the same region as your virtual network. Think of this as having a local guide who knows the territory. This local presence ensures that the topology tool can accurately map and display your network infrastructure. The tool's practical value becomes apparent in several scenarios. For instance, when troubleshooting connectivity issues, you can quickly trace the path between resources and identify potential bottlenecks. When planning network changes, the visual representation helps you understand the impact of your modifications before making them. It's particularly valuable during handovers, allowing new team members to quickly grasp the network architecture. Each component in the topology diagram is interactive, allowing you to drill down into specific details when needed. You can see not just that a network security group exists, but understand its rules and how it affects traffic flow. You can trace connections between virtual machines and understand how they relate to other network resources. The visual nature of the tool makes it invaluable for documentation and communication. Instead of trying to explain network architecture through text or tables, you can share a clear, visual representation that speaks for itself. This is particularly useful when collaborating with team members or stakeholders who might not be deeply familiar with network configurations. Let's walk through the answers and explanations for our knowledge check questions about Azure Network Watcher. Question 1. How does Azure Network Watcher support graphical visualizations for networks? Correct answer: Topology Tool Explanation. The Topology tool is Azure Network Watcher's dedicated feature for creating visual representations of network infrastructure. This tool generates interactive diagrams showing the relationships between network resources, making it easier to understand complex network configurations. The tool displays various components including virtual machines and their connections, subnets and their organization, network security groups, routing tables, network interfaces. This visual representation is particularly valuable when working with unfamiliar networks or explaining network architecture to stakeholders. Question 2. What Azure Network Watcher feature can help you quickly troubleshoot the issue reported by the help desk? Correct answer: IP flow. Verify explanation: IP flow. Verify is the ideal tool for this scenario because it specifically verifies whether traffic is allowed or denied to from a virtual machine. It helps identify security rule issues that might be blocking network traffic. It provides quick validation of network security group rules. It can pinpoint exactly which security rule is causing connectivity problems. The other options, while useful, serve different purposes. Connection. Troubleshoot is more focused on latency and routing issues. Packet capture is better for detailed traffic analysis rather than quick security rule verification. Question 3. Which scenario is a good use case for Azure Network Watcher? Correct. Answer: diagnose network traffic filtering problems to or from a virtual machine. Explanation: this is a perfect use case for Azure Network Watcher because Network Watcher is specifically designed for network monitoring and diagnostics. It provides tools like IP Flow Verify and Security Group View that are ideal for troubleshooting traffic filtering issues. It can analyze traffic patterns and identify security rule conflicts. The other options are less suitable because log activity events are better handled by Azure Monitor or Log Analytics. Pass monitoring and web analytics are more appropriate for application insights or other specialized monitoring tools. Key learning points. Azure Network Watcher provides specific tools for specific networking tasks. Topology tool for visualization. IP Flow. Verify for security rule verification. Various diagnostic tools for different networking scenarios. When choosing a tool, consider the specific problem you're trying to solve, the type of information you need, the scope of your investigation. Network Watcher is most effective for network diagnostics, security rule verification, connectivity troubleshooting, network topology visualization. Let's dive into Azure Monitor's alert system, a crucial component for maintaining the health and performance of your Azure resources. Azure Monitor serves as your central nervous system for Azure operations. collecting and analyzing data from multiple sources. Understanding its alert types and components is essential for effective monitoring. First, let's explore the three fundamental alert types. Metric alerts. Think of these as your vital signs monitor. They trigger when numerical values cross predetermined thresholds, for example. CPU usage exceeding 95%, available memory dropping below 10%, response time increasing beyond 5 seconds. These alerts are ideal for real-time monitoring of quantifiable resource behaviors. 2. Activity log alerts. These are your change monitors, tracking modifications to your Azure infrastructure. They notify you when resources are created or deleted, service health issues occur, configuration changes are made. They're perfect for maintaining security and compliance by tracking who's doing what in your environment. 3. Log alerts. Consider these your pattern detectors. They analyze log files for specific conditions or trends such as application errors, security incidents, performance anomalies. They're particularly useful for complex scenarios requiring detailed analysis. The composition of an alert rule follows a consistent structure. Resource component defines what you're monitoring, can include multiple resources, determines available signal types. Condition component specifies the signal type, metric, log, or activity, defines the alert logic, sets thresholds or criteria. Action component determines what happens when an alert triggers, can include multiple notification methods, email notifications, SMS messages, webhook integrations, action groups for coordinated responses, alert details, name and description for clear identification, severity level for proper prioritization. The 5 severity levels help teams understand the urgency. Level 0, critical, requires immediate attention. Level 1, error, needs urgent attention. Level 2, warning, requires attention soon. Level 3, informational, for awareness. Level 4, verbose, detailed debugging information. Monitor conditions provide the current state of an alert. Fired indicates the alert condition is currently active. Resolved shows the condition has cleared best practices for implementation. 1. Start small. Begin with critical metrics. Gradually expand monitoring scope. Fine-tune thresholds based on observations taught. Use action groups effectively. Create different groups for different scenarios. Include escalation paths. Consider time zones for international teams. 3. Regular maintenance. Review alert effectiveness. Adjust thresholds as needed. Clean up obsolete alerts for documentation. Maintain clear descriptions. Document expected responses. Keep contact information. Let's explore Azure Monitor's Metric Alert System, a powerful tool for proactive monitoring and issue prevention in your Azure environment. Understanding metric alerts. Metric alerts are your early warning system for performance issues. They monitor specific metrics at regular intervals and notify you when values cross predefined thresholds. Think of them as your infrastructure's vital signs monitor. 2 types of metric alerts. 1. Static threshold alerts. These are your straightforward, predictable monitors. Like setting a thermostat, you define exact values that trigger alerts. Direct threshold values, e.g., CPU 85%. Simple to configure and understand. Immediate triggers when conditions are met. Best for metrics with consistent, well-known limits. Example configuration. Metric, CPU usage. Threshold, 85%. Evaluation period, 10 minutes. Check frequency, every 2 minutes. 2. Dynamic threshold. Alerts. These are your intelligent, adaptive monitors. They use machine learning to understand normal behavior patterns. automatically adjusts thresholds based on historical patterns, requires additional configuration. Look back period. Historical data range to analyze. Number of violations require deviations before alerting. Better for metrics with seasonal or variable patterns. Example configuration. Metric, network, traffic. Look back period. 3 periods. Evaluation. Period. 10 minutes. Violations required. 2. Check frequency. Every 2 minutes, core components of metric alerts. 1. Statistical analysis. Choose from multiple types. Minimum, lowest value in the period. Maximum, highest value in the period. Average, mean value over the period. Total, sum of values in the period. 2. Evaluation period. Defines the time window for analysis. Typically ranges from 1 to 30 minutes. Balances responsiveness with stability. Check frequency. How often the condition is evaluated. Should be shorter than the evaluation period. Impacts resource usage and alert timeliness. Advanced features. Dimensions. Monitor multiple related instances. Individual alerts for each instance. Use wildcards, buying, for automatic inclusion. Example, monitor all VMs in a scale set. 2 scaling, currently limited to Azure VMs. Single rule for multiple resources. Region-specific monitoring. Individual alerts per resource. Best practices for implementation. 1. Start conservative. Begin with wider thresholds. Adjust based on false positive negative rates. Use dynamic thresholds for unknown patterns. Choose appropriate time windows. Shorter for critical metrics. Longer for stable, slow-changing metrics. Consider business impact timing. 3. Use dimensions effectively. Group-related resources. Use meaningful instance names. Document wildcard usage. 4. Plan for scale. Consider alert volume. Group similar resources. Use action groups efficiently. Welcome to our deep dive into log search alerts in Azure Monitor. Let's explore how these alerts can help you detect and respond to important events in your applications and infrastructure. Understanding log search. Alerts. Log search alerts are your historical data analysts, examining log files for patterns, trends, and specific events that might indicate problems. Unlike real-time metric alerts, these focus on analyzing recorded data to identify issues or patterns that have already occurred. Core components of log search. Alerts. Log query. The search criteria defining what to look for. Uses Custo query language, KQL. Can be simple or complex patterns. Examples: error codes, system events, performance data. 2. Time period. Historical window to analyze. Typically ranges from minutes to days. Balances detail with performance. 3. Frequency. How often the query runs. Must be less than the time period. Affects resource utilization. Threshold. Trigger point for alerts. Varies by alert type. Can be simple or complex. 2 types of log search alerts. Number of records. Ideal for event-based monitoring where each record is significant. Key characteristics. Simple counting mechanism. Triggers on raw number of matches. Best for discrete events. Stateless evaluation. Example uses security events, monitoring, error, log tracking. Application crash reports. Failed login attempts. Configuration. Example query. Error events in last 30 minutes. Threshold. Yup, 5 records. Result. Alert triggers when 5+ errors found. Metric measurement. Suited for analyzing trends and patterns over time. Components. Aggregate function. Count average sum. Applied to result set. creates aggregated value. Group field organizes results. Example, by server, by application, enables focused monitoring. Time interval, data aggregation period, affects alert granularity, balances detail and noise. Threshold, based on aggregated values, includes violation count. More complex conditions. Example, configuration. Query, CPU usage logs aggregate, average group. By server, interval, 10 minutes, threshold, 85% for 5 intervals, important considerations. 1. Stateless nature. Alerts trigger each time conditions are met. No awareness of previous alerts can lead to alert storms. Requires careful threshold setting. Query, performance. Complex queries impact resources. Balance frequency with detail. Consider data volume. 3-time windows, longer windows, more data. Shorter windows, quicker response. Match to business needs, best practices. Query design. Keep queries focused. Optimize for performance. Test with sample data. Document complex queries. Alert configuration. Start with conservative thresholds. Adjust based on experience. Group-related alerts. Use appropriate time windows. 3. Alert management. Implement alert grouping. Set up proper routing. Plan for escalation. Regular review and clean up common use cases. Application monitoring. Error patterns. Performance trends. User behavior analysis. Security events. 2. Infrastructure management. System logs. Resource utilization. Configuration changes. Backup status. 3. Ports. Security monitoring. Access patterns. Security events. Compliance violations. Threat indicators. By properly implementing log search alerts, you create a powerful system for analyzing historical data and identifying patterns that might indicate problems. Remember to regularly review and adjust your alert configurations based on actual experience and changing business needs. Let's explore activity log alerts in Azure Monitor, a crucial tool for monitoring changes and events within your Azure infrastructure. Activity log alerts serve as your infrastructure's event monitoring system, providing visibility into 2 key areas. 1. Specific operations alerts. These alerts monitor changes and activities within your Azure subscription. Key characteristics: subscription-specific monitoring, resource-level granularity, administrative action tracking, configuration change detection, common use cases, virtual machine deletions, role assignment changes, security group modifications, resource creation events, configuration updates. 2. Service health alerts. These focus on Azure platform events that might affect your resources. Components, service issues, ongoing incidents, service disruptions, performance degradation. Planned maintenance, scheduled updates, infrastructure improvements, service upgrades, health advisories, proactive notifications, recommended actions, security updates, alert attributes, deep dive, category selection, administrative, user and system actions, service health, platform level events, auto-scale, resource scaling operations. Policy, policy compliance and violations. Recommendation, Azure Advisor suggestions. 2. Scope levels, resource level, individual resource monitoring. Resource group level, group-wide monitoring. Subscription level, entire subscription coverage. 3. Alert, configuration, resource type, target resource namespace, operation name, specific action to monitor, level, severity classification, status, Operation Outcome Tracking, Event Initiator, Action Originator Implementation, Best Practices. 1. Resource-specific alerts. Start by filtering relevant events. Use Azure Monitor to identify patterns. Test alert conditions thoroughly. Document alert purposes, service health alerts. Configure for critical services. Include relevant regions. Set appropriate notification channels. Plan for maintenance Windows alert management strategy and categorization group-related alerts. Establish severity levels. Define ownership. Set response procedures. Notification management. Configure action groups. Set up escalation paths. Define notification methods. Establish response. SLAs 3. Maintenance and review. Regular alert audit update notification lists. Adjust scope as needed. Review effectiveness. Practical examples. Infrastructure changes. Alert. VM creation scope. Production resource group level. Informational action. Email to infrastructure team. 2. Security monitoring alert. Role assignment scope. Key resources level. Critical. Action. Security team notification. Taunt service. Health. Alert. Service issues. Scope. Regional services. Level. Warning action. Operations team alert. Integration considerations. ITSM. Integration. Ticket creation automation. Incident management workflow. SLA tracking resolution documentation. Communication flow. Alert routing rules. Notification grouping. Escalation paths. Status updates. Documentation. Alert configurations. Response procedures. Contact information. Recovery plans. By properly implementing activity log alerts, you create a comprehensive monitoring system that keeps you informed about important changes and events in your Azure environment. Remember to regularly review and adjust your alert configurations to maintain their effectiveness and relevance to your business needs. Common scenarios and solutions. Change management. Monitor resource modifications. Track configuration changes. Audit access modifications. Document system updates. 2. Security compliance. Track role assignments. Monitor security changes. Log access attempts. Record policy modifications. Cost management. Monitor resource creation. Track scaling events. Alert on high-cost operations. Monitor usage patterns. Remember, effective activity log alerting is about finding the right balance between staying informed and avoiding alert fatigue. Regular review and adjustment of your alert configurations will help maintain this balance and ensure you're focusing on what matters most to your organization. Let's explore action groups and alert processing rules in Azure Monitor. Powerful features that determine how alerts are handled and notifications are distributed. Action groups overview. Think of action groups as your alert response playbook. They define what happens when an alert fires, allowing you to create standardized response patterns across your monitoring infrastructure. Available actions, communication actions, email notifications, custom messages, HTML formatting, multiple recipients, SMS messages, short alerts, on-call notifications. Geographic targeting, voice calls, critical alerts, emergency notifications, escalation paths. Push notifications, mobile app alerts, real-time updates, interactive responses. 2. Automation actions, Azure functions, custom code, execution complex logic handling, integration with other systems, logic apps, workflow automation, multi-step responses, cross-platform integration, webhooks, third-party integration, custom endpoints, external system triggers, 3.ETSM, integration, ticket creation, automated incident creation, work item, generation problem tracking, runbook automation, .vm management resource scaling, automated remediation alert processing rules. These rules act as your alert traffic controllers, determining how alerts are handled after they're generated. Key capabilities: action modification, add actions, append new notification channels, include additional automation, expand response scope, suppress actions, maintenance windows, planned downtime testing periods, management at scale, common logic, standardized responses, consistent handling, simplified management, resource scoping, single resource targeting, resource group coverage, subscription-wide rules. The 3. Scheduling options, always active, continuous monitoring, default state, persistent rules, one-time window, temporary changes, special events, limited duration, recurring schedule, weekly maintenance, regular patterns, predictable suppression, implementation, best practices, action group design, create logical groups, by team responsibility, by severity level, by response type, layer actions, primary notifications, escalation paths, automated responses. 2. Processing rule strategy, maintenance windows, planned downtime, system updates, testing periods, scale management, resource grouping, common patterns, efficient handling. Notification management, avoid alert fatigue, proper thresholds, appropriate grouping, meaningful filters, clear communication, descriptive messages, action requirements, response expectations, common scenarios. 1. Critical system monitoring, action group, immediate SMS to on-call, email to team, create ITSM ticket, trigger automation. 2. Maintenance window processing rule, suppress notifications, schedule, weekly window, scope, specific resources, cost management, action group, email notifications, create cost report, trigger scaling, runbook integration considerations, external systems, ITSM platforms, communication tools, custom applications, automation, resource management, problem remediation, system recovery. 3. Documentation, rule configurations, action group mappings. Response procedures. By effectively implementing action groups and alert processing rules, you create a robust and efficient alert management system. Regular review and adjustment ensure your alert handling remains aligned with your operational needs and organizational requirements. Welcome to our deep dive into Azure VM monitoring. Let's explore the comprehensive monitoring capabilities that Azure provides for virtual machines. Azure Monitor serves as the foundation of VM monitoring, offering 2 primary components, metrics and logs. Each plays a crucial role in maintaining optimal VM performance and health. Starting with Azure Monitor Metrics, this system automatically collects numerical data at regular intervals. Think of it as your VM's vital signs: CPU usage, memory utilization, disk operations, and network throughput. These metrics are retained for 93 days, giving you a substantial window for trend analysis and performance optimization. Azure Monitor Logs complements metrics by providing detailed event tracking. While metrics tell you what is happening, logs tell you why it's happening. These logs capture everything from system events to application-specific data, stored in a log analytics workspace where you can query them using Query language, KQL. Looking at the monitoring layers, we have 4 distinct levels. The host VM layer focuses on the fundamental infrastructure metrics. 2. The guest OS layer monitors the operating system itself. The client workloads layer tracks applications running on the VM. 4. The Applications layer monitors custom applications. Key host metrics deserve special attention. CPU usage helps identify processing bottlenecks. Disk usage monitors storage performance and capacity. Network Operations track communication efficiency. VM Insights provides an integrated monitoring experience with automated agent deployment, pre-configured data collection, ready-to-use performance dashboards, dependency mapping for complex applications. When setting up monitoring, consider retention requirements for your metrics and logs, performance impact of data collection, cost implications of data storage, regulatory compliance requirements for effective monitoring. 1. Start with host-level metrics to enable guest OS monitoring for deeper insights. 3. Configure alerts for critical thresholds. Port. Use VM Insights for comprehensive visibility. The real power of Azure Monitor comes from its integration capabilities. You can forward logs to long-term storage, create custom dashboards, set up automated alerts, integrate with third-party tools. Remember, effective monitoring is not just about collecting data. It's about turning that data into actionable insights that help maintain optimal VM performance and reliability. Let's walk through the process of setting up and utilizing VM host monitoring in Azure. This practical guide will help you implement effective monitoring for your virtual machines. Starting with VM creation, we'll use Ubuntu Server 20.04 LTS as our example. First, activate the recommended alert rules. These are pre-configured thresholds for important metrics like CPU usage and disk space. Make sure to set up email notifications to stay informed about any issues. Boot diagnostics is a crucial feature that provides insights into VM startup behavior. By enabling it with a managed storage account, you gain access to two valuable tools: screenshot captures from the hypervisor and serial console logs. These are invaluable for troubleshooting startup issues. Azure automatically begins collecting platform metrics as soon as your VM is running. The key metrics to monitor include VM availability, tracks uptime and availability status. CPU usage, monitors average processor utilization. Disk, bytes, measures total disk I/O. Network traffic, tracks, total network operations, disk operations, monitors, I/O operations per second. The activity log provides a detailed audit trail of all operations performed on your VM. This includes creation events, configuration changes, and status updates. You can access this information through the Azure Portal, PowerShell, or Azure CLI. Best practices for effective monitoring include regularly review performance metrics to establish baselines. 2. Configure alerts for critical thresholds before issues arise. Use boot diagnostics to quickly identify startup problems. 4. Monitor activity logs for security and compliance. For deeper analysis, use the Monitoring tab to view detailed performance graphs. Compare metrics across different time periods. Correlate multiple metrics to identify patterns. Export data for custom analysis. Remember, while guest OS metrics aren't collected by default, you can enable them later through VM Insights and data collection. Rules for more comprehensive monitoring. Let's explore how to use Azure Metrics Explorer effectively to analyze VM performance, particularly focusing on the relationship between traffic flow and CPU utilization. Azure Metrics Explorer is a powerful tool accessible through multiple paths. Directly from the VM's monitoring menu, through the See All Metrics link on the Overview page, via the Azure Monitor dashboard. When working with Metrics Explorer, you'll interact with 4 key configuration fields. 1. Scope. By default, this is set to your VM when accessed from the VM menu. 2. Metric namespace. Defines the category of metrics you're viewing. 3. Metric, the specific measurement you want to analyze. 4. Aggregation, how the data should be processed and displayed. For our specific example of analyzing CPU usage and inbound traffic, let's walk through the process. First, locate percentage CPU in the metrics drop-down. While the default aggregation is average, we'll switch to maximum to see peak CPU usage. This helps identify potential performance bottlenecks. Next, use the Add Metric button to include inbound flows, keeping the aggregation at average. This combination lets us correlate network traffic with CPU performance. The time range selection is crucial for meaningful analysis. For real-time troubleshooting, the 30-minute window provides detailed recent data. However, you can adjust this from 30 minutes to 30 days depending on your analysis needs. Metrics Explorer offers several aggregation functions. Count, useful for event frequency analysis. Average, best for general performance trends. Maximum, identifies peak usage periods. Minimum, spots resource utilization lows. Sum, totals cumulative values. Best practices for effective metric analysis. 1. Compare related metrics to understand cause and effect relationships. Choose time ranges appropriate to your investigation. 3. Select aggregation methods that match your analysis goals. 4. Consider granularity based on your time range. Remember, this visual correlation between CPU usage and network traffic can help identify patterns and potential performance issues before they impact your applications. Let's explore VM Insights, Azure's comprehensive solution for monitoring the software and processes running on your virtual machines. VM Insights goes beyond basic host monitoring by providing visibility into your VM's guest operating system and applications. This feature streamlines the setup of client monitoring through 3 main components. 1. Azure Monitor Agent Installation Automated Data Collection Rule DCR configuration. 3. Pre-configured workbooks for data visualization. The setup process is straightforward but thorough. Start by navigating to the Insights section under your VM's monitoring menu and selecting Enable. This initiates the deployment of necessary components. During configuration, you'll notice the creation of a DCR with specific settings for process and dependency mapping. You can enable these features based on your monitoring needs. A key decision point is the Log Analytics workspace assignment. VM Insights will either create a new workspace or use an existing one to store your monitoring data. This workspace becomes the central repository for all your VM's performance data. Once configured, which typically takes 5 to 10 minutes, verify the installation by checking the Extensions Plus Applications section of your VM's properties. You should see the Azure Monitor Agent listed there. Additionally, the Monitoring tab should now show active collection of guest OS metrics. VM Insights provides 2 main views for analyzing your VM's performance. The Performance tab offers customizable time range selections, detailed performance graphs, multiple aggregation options, access to additional workbook templates. The Map feature, when enabled, provides visual representation of running processes, network connection mapping, dependency visualization between components. The workbook functionality is particularly powerful, offering pre-built templates for common monitoring scenarios. Customization options for specific needs. Performance trend analysis, process monitoring and mapping. Best practices for using VM Insights include regular review of performance metrics. 2. Customizing time ranges based on analysis. Needs 3. Utilizing both performance and mapping features. 4. Creating custom workbooks for specific monitoring requirements. Remember, while VM Insights provides an excellent starting point for client monitoring, you can always extend its capabilities by creating additional DCRs or customizing workbooks to meet your specific needs. Let's walk through the process of setting up and utilizing VM Client Event Log Collection. which is crucial for root cause analysis of performance issues. The setup process involves two main components. First, we create a data collection endpoint, which serves as the gateway for log data transmission. When creating the endpoint, name it descriptively, e.g. Linux logs endpoint. Ensure it's in the same subscription and region as your VM AD. This endpoint becomes the destination for your log data. Next, we establish the data collection rule, DCR, which defines what data to collect and how to process it. 1. Create a new rule named Collect Events Linux. Specify Linux as the platform type. 3. Add your VM as a resource. 4. Configure syslog data collection. Link it to your data collection endpoint. The DCR configuration offers flexible options, custom performance counter selection, adjustable sampling rates, various log types and severity levels, custom log schemas when needed. For log analysis, Azure provides several access methods. Through the VM's overview page under Logs, 2 via Azure Monitor's main log sections, directly in the Log Analytics workspace. The basic Kusto query language, KQL, usage is straightforward. Simple syslog query returns all events. Add filters like where severity level, warning for specific events. Customize time ranges for targeted analysis. Best practices for effective log collection and analysis. Regularly review collected logs for patterns. 2. Configure targeted data collection to manage costs. 3. Design efficient queries for faster analysis. 4. Properly scope queries to relevant resources. Remember that while VM Insights provides basic performance monitoring, custom log collection through DCRs gives you deeper insights into system behavior and issue root causes.